Okay, welcome everyone to this year's workshop on autonomous driving. We have a really packed program today. So we have in fact 9 speakers from both industry and academia. We have 4 very competitive challenges which will be present, and then to wrap everything up, we also have 11 papers which we will present during our workshop. But before I go and give a quick overview of the program, let me thank all the co-organizers. These are people from both academia and industry. So we have people from Waymo, NVIDIA, Oxford, and then like myself from ETH. Yeah, I would like to give a special thank to Yuning, which is really taking care that everything works in the background. So with him, this workshop would not be possible and this live stream would not be possible. I would also like to thank Jose, which really took care of the whole paper track, I think a fundamental part of our workshop. And yeah, again, huge thank to all the other organizers as well. Now, for the program, you can already see the first few marks. So it will start with Alex Candel, which you can already see the video of, I think. And then we will have 4 invited talks in the morning and the Waymo Open Set Challenge combined with the spotlight talks and poster sessions for our papers. At 11:30, we'll have then a lunch break for 45 minutes. And afterwards, we have again 5 talks in the afternoon and the challenge by Argo, the Argoverse challenge. So this was way quicker than I actually thought. So I don't know. I think, Alex, would you like to start early and answer more questions, or should we wait for the exact time spot your talk starts in the hope that everyone shows up on time for the talk and actually not for the welcoming remarks? Okay. Yuning, can you unmute Alex? Ah, wait. Okay, good. Yeah, then.
Sorry, I couldn't speak. I'm happy to get started if you prefer.
Okay. So then, Alex, are you ready? Or okay. Can you say something?
Sure. Happy to get started.
I can't hear you.
You can't? You can't hear me? I can hear you. Can you see me?
Okay. It seems to be a problem on my side as everyone else can actually hear you.
Okay.
Then that's something I have to fix, but let me introduce Alex. He's actually a co-founder and CEO of Wave, a London-based startup which really focuses on end-to-end autonomous driving. So how to really solve autonomous driving directly based on neural networks. As I'm working on similar topics, I'm really looking forward to this talk. And Alex, the stage is yours.
Great. Hey, thank you so much for the introduction, and what a fantastic array of content today. I thought I'd start and comment. I'm actually taking this talk from our workshop. This is not a, I know segmentation has come a long way since I used to work on it, but this is not a background segmentation. So I thought it'd be fun to speak here in our workshop. So hello from London. So to dive in, I think now is the time for us as a community to bring embodied agents out of simulation, out of the virtual world, and really give them an embodied intelligence, a presence in the physical world. And I really see a vision of embodied agents interacting with us to really enrich our lives across all of society, and doing so in a way that doesn't take away our agency, but really allows us to focus on what matters most. And so at Wave, we're building this starting with autonomous driving. If you think about current solutions to autonomous driving, I think there are two key reasons that are really holding us back: adaptability and scalability. If you look at AV 1.0, or the first generation of autonomous driving technology, I think it was really brute force to a solution through HD maps and hand-coded rules. And this is super inspiring to me, and I'm sure many of you. But what we've seen is it really struggled to adapt to the complexity of urban environments and others that you or I likely need to move around in this world. On top of that, we've seen a reliance on really expensive and complicated sensor stacks that I think more have the idea of, for each new edge case, put a new sensor in place to resolve that, rather than really focusing on the underlying intelligence. And then perhaps most importantly, the future of mobility needs a complete array of solutions, from micromobility to public transport, to ride hailing, to delivery. And I think we need to be able to iterate and adapt to these different vehicle platforms with speed and move at the pace we're used to moving at with hardware as we are with software. And I think that this really requires a super advanced level of adaptability. That's what we're focusing on, and really looking to reimagine what's possible and move us to AV 2.0, what we consider the next generation of autonomous driving, and doing so with end-to-end deep learning. Let me show you an example just to set the scene of what we're able to demonstrate with this technology. This is our system driving in central London, under full automation through a quite unstructured and unknown scene. It's never seen this intersection before. It doesn't have an HD map. In fact, I challenge you to actually describe where the lanes are in this kind of unstructured environment. But our system is driving through there with entirely online reasoning, with machine learning from monocular computer vision. Here again, we're driving in quite a heavy rainstorm in London, in fairly heavy traffic. And I just wanted to show this to give you an idea of some of the diversity of scenes that we learn to drive in across many different types of weather, many different types of road environments. And you know, the size of the state space is really enormous. And you know, it's quite exciting when you first get in the vehicle to see this in the real world. This example is driving in central London down Oxford Street. If you've visited, many of you may know it as the main shopping district in London. And this just gives you an example of what our system has been able to learn and generalize to. If I skip forward in this video, this is my favorite moment, because here is what I would consider real multi-agent interaction and control. And this is what's needed for autonomous agents to coexist with humanity. We can't have an autonomous vehicle that just stops and waits for the traffic to clear before proceeding. We need to be able to jointly predict how we're behaving and others behave. And in this example, you can see our vehicle essentially predict how others are going to move around it and know jointly how it should move its way through this very busy traffic. Know when it's going to move and nudge others out of the way, or in this example, know when someone's going to come in front of us. And I would really challenge you to define where the lanes are there. That really does motivate the need for a high dimensional state representation of the world and the ability to control from it. And in this final example, here's a red light intersection in an urban area, and our system's learned to stop. It hasn't been told the exact XYZ location of the light, it's just detected it through end-to-end reasoning. And then when it goes green, it knows to drive through and has noticed that there's an offset to the following lane, and it's able to correctly navigate around and drive through this. So I think this is more starting to look like the future for me. And just to show one final example, here's again some very busy traffic, oncoming traffic that we've got to navigate through past double park vehicles. And if you try and code up the rulebook of the road code, I think you'll find many times that these rules need to be bent or flexed to be able to interact with society as driving cultures dictate. And that's really motivating why we think we need to learn to get to these sort of complex environments. To talk about scalability, just to show one other result here, we trained that agent with about 5,000 hours of London-based driving data. We can take it all over the UK. So for example, we've taken it to Cambridge, a city a couple of hours drive from London. And this model has been able to drive with a similar set of performance metrics, despite having never seen that environment before. Now, what I see for the system is when we go from UK cities to Paris, Tokyo, Mumbai, as we go to more and more diverse sets of driving cultures, I think we'll need exponentially less data to go to each one, but really build this underlying driving intelligence that can adapt across these driving domains. That's what I think is the future. Let me share a bit about how we build this driving intelligence. So to set the framework up, our system has a state input, which is based on monocular cameras that surround our vehicle, 6 of them, along with GNSS, basic sat-nav map, and a vehicle state like odometry, IMU data, and the like. This is about 10 to the 8 dimensions when you consider those cameras against time. And our output state is a motion plan, about 10 to the 1 dimensions, which has a parameterized motion plan, which you can do in many ways, as well as vehicle controls like indicator control. How do we tend to solve very complex high-dimensional problems? Well, I don't think there's a better technology on the planet than deep learning. And so what we do is we put an end-to-end network in this place to model from that high-dimensional input to the low-dimensional output. And we learn end-to-end to optimize this model. And of course, we can also take a number of intermediate representations, not bottleneck representations, but decoded representations to give us some structure and interpretability in this model and to give us data-efficient learning. Everything from semantics, motion, and geometry. And these we really strive to make as self-supervised as possible. How do we train it? Well, we've built a fleet learning platform that really gives us large-scale training and verification. We're able to put petabytes of data into this fleet learning platform to learn to drive at scale, everything from synthetic data to off-policy data that's really important to build up that robust world model of the driving dynamics. And also, of course, on-policy data. We have over 100,000 disengagements that we've collected to date, and this gives us a really powerful platform for learning. The largest autonomous driving operations in urban environments in Europe. We see all of the applications, whether it's across the use case or the city or the vehicle platform, all of these are just examples of different data distributions. And it's really important to us that our system can adapt across all of them and build an underlying adaptable driving intelligence. So now that I've talked about the platform, let me talk about a couple of threads of ideas that we've been pursuing over the last couple of years that have been really important to us. The first one is on learning temporal and 3D geometric representations for driving. This comes from a large body of work that we've been pursuing for some time, and I've put some references here if any of you want to read further or understand where and how and why we came to these conclusions. To motivate this, let me start by showing you this image. How many of you would think that this car on the left is yielding to us, or how many of you think it's going to pull out in front of us? I don't know what you think, but it's really hard to tell from a single image. And as soon as I give you motion, it becomes apparent that this car is waiting and is stationary, is yielding. So this illustrates the importance for temporal context in decision-making. What we've been able to put together is a system that gives us 3D reasoning in an end-to-end model that can also understand the temporal state and jointly predict our motion and others' motion in this 3D space. And this has led to some of the results I showed earlier of driving robustly and doing multi-agent interaction in traffic. Let me walk you through some of this work. So how do we construct this architecture? First of all, we start with a number of historical state inputs, and we lift them into 3D. We then project them into a high-dimensional bird's eye view and form a sequence of past states. You can then aggregate these into a temporal state S using a temporal model, and you can use anything from a conditional convolutional network to a recurrent net to a transformer. I mean, we've tried them all, and you can probably guess what works best. We then form 2 probability distributions, the present and the future distribution. The present distribution is conditioned on all of our previous state inputs, and the future distribution gets to see the future states. Of course, this is only present during training time, And we use it to guide the system to predict the future that is actually observed in the data so we can learn from it. But at inference and test time, we don't have access to the future distribution. So we train a present distribution and minimize a divergence loss between these two in order to learn an accurate and representative present distribution that can then predict the future. We then unroll these states into future states over time, and then we can decode them into the outputs we care about, everything from semantic segmentation to depth, geometry, pick your choice. Now, to give you a bit of insight behind this architecture, and if we ablate some of these components, so I started off by claiming that it's really important to have 3D geometry and temporal reasoning. Well, this ablation really shows that. If we remove the ability to reason over temporal states, we get a large hit in performance. And I should mention that this is looking at numbers across the future video panoptic quality metric. So panoptic quality, the quality of our instance and semantic segmentation in 5 seconds in the future. Without temporal knowledge, we have a large hit in performance. And again, without a 3D transformation, we have a similar hit in performance. So these two factors are really important. If you look at unrolling or going from a deterministic to a probabilistic policy, we again get some further benefits in performance, but this gives you an idea of what is really important to make this work. And we've found it really was the 3D structure and the temporal reasoning. To show you some more results, what you're seeing here is our system able to predict multimodal and diverse futures of all the agents around us. So you can see it jointly predicting agents in front of us with some multimodal decisions going into this intersection until they commit to a turn. Here's another one you can see where our system's able to predict a U-turn going into this intersection. You can see that the agent in front of us is unsure whether it's going to go straight or make a U-turn until it commits that turn, and then the distribution collapses on that behavior. Here's another example that shows with 3D geometry, we're robust to quite dynamic ego motion. And as our vehicle turns, you can see that we're able to robustly reason across some of the other agents in the intersection around us. And then finally, here's an example overtaking some double parked cars and driving down a lane. So that's a start. That shows an idea of world modeling with 3D geometry and motion. The next step is how can we actually action condition this model so that we can learn to drive. And so the next thing I want to talk about is moving towards model-based reinforcement learning, which we think is the future, and how we're going to learn a robust and scalable driving agent from off-policy data. I've again listed some works that have motivated this, both from our work and some other seminal work in this area. If you want to read further, please dive into these references. A lot of great papers that inspired us there. So how can we extend this model to learn from data and learn to imagine and control our vehicle? Well, again, we can take a state input and encode it into a latent representation Z. We can decode that into an output representation we care about, such as semantics, motion, or geometry. We can take this hidden state and learn a dynamics model that's able to learn to take the hidden state and the action that was taken and predict the next state. Now, this dynamics model, the important thing here is that we're learning from observation. So we can take large-scale off-policy data. If you have to learn from online data or online learning, you're going to be very limited by the number of robots you have. But by learning from off-policy data, we can observe as much data as we can get our hands on, and that's truly very large scale, and we can learn some very complex representations. So this is observing offline, off-policy data. We take that state action pair and we learn a dynamics model to predict the next state. And then of course we can look at the next observation and encode that, and again form this divergence loss between our present and future distributions. And this gives us that ability to learn a multimodal and probabilistic representation that's so important in driving to deal with the quite diverse behaviors that we see. So again, we can learn to predict an output and roll this forward recurrently. Then when it comes to learning to control, again, we have this encoding framework, but now instead of using the observed actions, we can now predict our own action. And this is where we imagine to act. This is very similar to how we as humans learn to drive, also learn to behave. I mean, if you go to kick a football, you might try in number of times in the real world, but your hippocampus will replay this many times in your mind to essentially imagine and ablate the different parameters so that you learn a robust control policy through your neuromotor control. Now, we can do the same thing in machine learning, which is what we do here. We take this encoding and take an action and learn, we learn to output an action, and we can then use our dynamics model and learn to predict the next state and run this forward recurrently. And this lets us use an action that we've learned, whether it be through distribution matching, adversarial imitation learning, or through a reward. You can learn a policy and you can actually unroll it through time and start to get closed loop driving and closed loop ability to learn and interact with the world from off policy data. And this imagining to act is a really powerful idea. Let me show you some results. So as you saw previously, you saw a number of animations of our system predicting the future in a static sense. Well, now we're predicting futures that are conditioned on our own policy or our own action. So let me explain these videos. On the left, in the first one, you can see a base policy where we have in this case, a view of the world, a perspective projection looking forward, and a control policy that just drives down this road and makes a left turn. Now, if we augment this policy, let's say we turn it to 0 speed, you can see in the middle example, we've learned to stay stationary. Or on the right example, you can see if we now multiply that policy by 1.5 speed, you can see our vehicle drives forward, goes a bit too fast, so drifts to the right-hand side of the road before correcting and driving back. And so you can see how it will behave under different policies. And we've got now a world model that can imagine and be conditioned on action. To show you another example, here's some multimodal and diverse behaviors. So I mentioned why it's so important to get that probability distribution. So here you can see that we've been able to predict different multi-agent behaviors. So on the left, you can see a car approach us from the left of the intersection. In that middle video, you can see an oncoming car come past us. And on the right, you can see much less traffic in the environment. And so this lets us really predict the diverse or the distribution of futures that is possible so that we can learn to make a safe action. And then finally, which is really important from an optimization perspective, is we've been able to learn over a long time horizon. You can see here really stable and robust recurrent future prediction, in this case over more than 12 seconds, which given we've got such high dimensional state input, I think this is really exciting so that you can cover not just the simple actions, but the complex multi-agent interaction that you need for urban driving. So let's look to the real world. What happens when you put this actually on a vehicle? I think this is really exciting when I sat in the car. Let me show you some logs from the last couple of weeks. So in this example, we've got a double-decker bus coming towards us. And you'll notice, if I just restart this video, you'll notice our car knows to stop and actually wait, because it can see and predict that this bus is going to come in front of us and enter our lane. So it knows we've had to stop and wait to let it pass. But now once it's passed, our car knows it should be nudging forward to actually make its way through traffic. And you can see this blue car and the following sedan sort of move out of our way to let us through. And it's that kind of multi-agent control. And for me, that's really higher level reasoning and the ability to predict over a long time horizon that gives us this intelligence. And I think that's pretty exciting. So let me just play it one more time. So we've stopped, we've anticipated this double-decker bus is going to come into our lane in an unstructured sense. And then we know that we need to nudge forward and actually jointly be able to predict how our behavior and others' behaviors is going to interact to be able to get through this traffic scene so we're not blocked off. And then I can keep playing this. Our vehicle will continue. We're going to drive through a traffic intersection. Let me just jump forward to, I think there's another moment that's worth looking at here. So you can see here we've learned to slow down, and we can predict this pedestrian crossing at the zebra crossing, wait for them to leave before continuing on. So it's this kind of multi-agent prediction is really important when you get to complex urban driving scenes like what we have in London. Let me show you another example. In this demo, maybe this motivates why we should not be relying on HD maps, because here we're going to find a traffic light, but this traffic light is transient. It's been put there through roadwork scenarios. And so our car can reason about the scene and know that it should stop and wait, even though another human disobeyed the light and drove past. But if I keep going into the future, so that traffic light is put there by roadworks. We don't know it's there a priori, but we've been able to reason that there is a traffic light here. It makes sense. It's not, it actually is something we need to obey as a vehicle. And I think it should go green shortly. Not only when it goes green, in the UK, we drive on the left. And so you're not allowed to go on the right, but we know our system's able to reason here that it should break that rule and actually go on the right-hand side of the road to be able to travel through this roadwork scenario. And so here you can see we're driving on the right to get through this, what looks like a underground mains roadworking scenario, before then again returning to the left-hand side of the road and continuing to drive. So there's just another example where we need a system that can really reason in a complex manner, that deals with multi-agent interaction and knows rules beyond what they're written in the rulebook, but really how they're applied in complex driving scenarios. So I guess let me finish by going through what we see as some grand challenges for autonomy. I'd like to talk through these because we see them as some fundamental challenging problems for us to solve to be able to get this technology be proliferated through society. And I share them because hopefully they can motivate some of your own work. And also if you share a passion for them, then maybe there's opportunity for us to collaborate. But we have 7 grand challenges that we think about at Wave. And let me go through them. So the first one we've spoken a lot about today is adaptability. This is the problem of being able to adapt very quickly to different sensors, vehicle platforms, use cases. And why this is so important is because it's not just about getting autonomous driving to the world, to market, but dealing with the ever-changing society. It's not just about getting it there, but then maintaining it over time as needs adapt, whether it's different road rules, a policy change, or different vehicle platforms that are needed for what we value as consumers. For me, this is so important that we have a system that can do this. And the key challenges here are things like being able to do online 3D reasoning. Can you estimate your intrinsics and extrinsics so you don't have to go through some detailed calibration step each time you want to deploy a vehicle? Can you can you reason about dynamics online, or can you learn a really robust representation? Off-policy learning is key, and we talked a little bit about that with the dynamics models, but we need to move away from a world where we need to design and develop with on-road testing. We've seen many people in this industry build safety cases through millions of miles of on-road testing, and while there's certainly merit to that, I think we can do something more intelligent, where can we move to a world where you can train, validate, and deploy through an over-the-air update and update your autonomy on a daily or a weekly basis. And to do that, you really need a robust and reliable off-policy training and evaluation metric. This lets you unlock very scalable data sources. We just use cameras today, and you can deploy that kind of sensing framework on very large-scale fleets. And so to be able to use off-policy learning and evaluation, I think, is what's really going to unlock scale. World modeling is something we spend a lot of time on, and is an area that I think is so important to be able to deal with interactions with humanity, understanding complex dynamics worlds with joint, both prediction and planning. You can't do them separately because they really do need to interact, and you need to reason about that interaction. Something I've spoken a lot about in this talk. Uncertainty is close to my heart. It's a topic that I've worked on personally, and is really important from I guess a learning, a data curriculum, and a evaluation perspective. But not only that, but it's also important when we're actually running an inference, because we need to know, is our control policy safe to execute? Not only about building the safety case to deploy it, but when it's actually running on the vehicle, is the motion plan that we output really safe and valid for us to execute on the road? We have a unique opportunity here because we rely on a deep learning representation where we can take things like epistemic or model-based uncertainty, we can take Q values, things like that out of our model, and really use them to verify and validate our vehicle's proposed trajectory before going and executing on the road. So knowing when we're out of distribution or when there's a scenario that we can't handle, that's really important for safety. Interpretability is another key one of how can we get a disentangled, orthogonal, linear representation of the factors we care about. This is absolutely critical to be able to, I guess, from an engineering perspective, and as well as building trust and making a trustworthy system. This is something that there has been a lot of progress in our community in the last few years. I think people are less interested these days in chasing another 9 on leaderboards and Cityscapes or Kitty or one of these offline data sets, but now it's about how can we understand and interpret and build a robust representation. Generalization is the next one. By this I mean it's likely intractable to collect a training example in every single enumeration of our state space. We need to be able to learn a system that can be really, really robust, and by that I mean be able to be intelligent at states that are far from our training set, and effectively reduce that outer distribution set of states to as small as possible. So I think the motivation should be clear in terms of how diverse and dynamic our world is. And then finally, the most important piece is what are we trying to optimize here? What is the reward? If you think about a human feedback or a 5-star rating at the end of a journey or a delivery, that's a really sparse level of feedback, not one that can provide you with well, at least today's technology. I think it's very hard to learn from such a sparse level of feedback with a reasonable amount of data. So how can we build a more dense reward? How can we use ideas like distribution matching, preference learning, inverse reinforcement learning, the interventions that we have, or other heuristical factors that we might think about, like minimizing acceleration and jerk and actually progress in a journey. Bringing all of these things together in a scalable and robust reward. That doesn't mean we've just gone from feature engineering to architecture engineering to reward engineering. I think that is, again, going down the slippery slope of trying to enumerate rules. But how can we actually rely on things like self-supervision, scalable feedback, automatic feedback of our system to give a scalable optimization objective? I think that's really critical to figure out. So let me conclude. I firmly believe that the way that we're going to solve autonomous driving is by framing this as a problem that can be solved by data, by building a really large-scale data source, and by building a driving intelligence that's flexible enough to learn the complexities of the environment we're trying to operate in. Put those two together with a very large fleet learning platform, and for me, that's what's going to produce autonomy in AV 2.0. And that's what we're absolutely focused and thrilled to be working on at Wave. Hey, so this is some of our team here in our HQ in London. All of this work here is, I'm absolutely proud to work with this bunch, and it's all a reflection of the hard work and perseverance that our whole team has put together over the last few years. So I want to thank them all, and I feel privileged to work with them every day. And hey, if you share our vision or have any questions about this talk that aren't answered today, feel free to get in touch. Here's our contact address, and we'll be happy to respond. But with that, let me again thank the organizers of this amazing workshop, and I'll conclude the talk. I'll be happy to take any questions. Thanks, everyone. I guess while the question's going, let me pull up.
Hey, Alex, great talk. Sorry, we had some technical difficulties and my microphone didn't turn on. So we actually got quite some questions, and if that they are not enough, I have quite a bit more myself. So the first one we got is actually on the different scale of data. So the question is, let's say that for training a prediction model, you need significantly more data than, for example, for a detection model. I mean, I think there was even a good example of, a parked car doesn't teach you a lot for a prediction model, but it's it's as good as any other car for a detection model. So now to the question, would this be a critical reason why we want to train separate models for different tasks?
Yeah, so I think the key thing when it comes to your data distribution is the diversity and quality of it, less so the magnitude, although of course you do need a fairly chunky magnitude of data to learn from. The reason why I say that is, I mean, we're already collecting too much data for us to store and train from. And so how you select the subset that is most informative, that isn't noise, but really provides learning signal to your system, I think that's a really important question to answer. Ultimately, I don't think putting together 30 neural networks where one does double park vehicle detector, one does traffic light detector and all of that, the reason why I think that can fall over is because enumerating that state output that you need from all of them in a hand-coded way can be very hard to do in a way that's necessary and sufficient for making safe driving decisions. So I think ultimately you need to optimize these together. I guess another maybe controversial thing I'd say is multitask learning is, I think, an ill-posed problem. You do need an overall single driving objective. And that's why I believe in order to make the necessary trade-offs, you need to be optimizing for a single overall reward and doing all of that jointly to get the most flexible and powerful learning architecture.
Maybe a bit less technical one. We saw a lot of videos driving in London. What is kind of the challenge of deploying a car in London compared to one maybe in a US city?
Yeah, I think let's look at some of the US cities we've seen deployments. And if you look at Mountain View, areas in Arizona, Texas, and urban environments, I think the differences there is really around, this is why I should try and show these videos, because it's around the structure of the lanes. It often in US environments, and I've lived in Menlo Park in Silicon Valley, and I've visited some of these places, you get very structured lanes and you get very clear signals and junctions. Whereas in European and UK cities, you often have a very unstructured environment. And I think it's having to tackle this that has in some ways motivated us to go after the solution that we have for autonomous driving. So of course there's the regulatory and operational things, but I think we've got a fantastic set of regulation here in the UK. But for me, I just point out the fact that how unstructured and diverse the environments are. They're non-Manhattan grids. The weather is sometimes crazy here, and you get a lot of multi-agent interactions with things like roundabouts, lane changing, multi-lane scenarios, and the like.
Okay. Thanks. Yeah, maybe a short one to end. In your world model approach, you use kind of segmentation masks as a output. Now, in a standard world model, you would go for, kind of the input to, you would just do an autoencoder style mapping. How important is this kind of for autonomous driving? Is this a fundamental feature, or is this just it worked a bit better?
Yeah, this is why I think you need that signal going end to end, because you might say that, oh, we don't need to know the color of a vehicle, so who cares about RGB as a autoencode the original signal. But then maybe your segmentation doesn't include things like indicator lights. So having to human prescribe that output state is I think a very brittle thing to do, and why I do think you need that signal going end to end to build a state representation that's optimal for control. In general, you can augment that by giving it intermediate states, and we find state spaces like semantic segmentation to be a lot more robust than pixel space, which is a lot more noisy, especially when you think about simulation and sim to real problems.
Yeah. No, I think I see your point there. Okay, thanks a lot for the great talk and answering all the questions. It was a pleasure to have you here. And I think we can try to start over and give over to Deva, our next speaker.
Thank you very much.
Thank you very much. Hopefully folks can hear me.
Yes, we can hear you.
Awesome. Okay. Thanks again, Alex and the organizers for setting up this workshop and giving me a chance to talk. Happy Father's Day to the folks that celebrate that. So I'll talk about perception and action in the open world, kind of a loaded title. And really what I'll use this as an excuse to do is to talk about some recent work that's been going on in our lab, that some of which will appear at the CVPR. And just to give a little sort of background, so a faculty at CMU, but I also am a director of Autonomous Vehicle Research Center at CMU, and also a principal scientist at Argo AI. So I kind of, in some ways, come at this problem wearing both an academic and industry hat and sort of a bridge thereof. Okay, so clearly, given the nature of the workshop, we don't have to motivate while we're looking at this. And like I said, I'll kind of use this as kind of an opportunity to talk about some recent ways we've been thinking about this problem and sort of highlight recent work that hopefully, if folks want more information about, they can look at in the proceedings. Okay, so how do we sort of set the stage and motivate ourselves for tackling some of these challenges? And I roughly split them into three parts. How do we, process a streaming suite of sensors to understand what's happening in the world? How do we deal with the kind of long tail of all the crazy things that could happen? Then finally, even though let's say all of us come at this from more of a perception or vision perspective, how do we sort of open that up to really think about the full autonomy stack? And I think this dovetails nicely with the previous talk of, so one approach for doing that is really end-to-end reinforcement learning, and I'll try to give another flavor of that here. Okay, so first, let's motivate ourselves. So one of the kind of remarkable properties of working in a space like this is that, of course, it's a safety critical challenge. There's tremendous oversight at the federal level, and so we can kind of do a bit of navel gazing, and we can look at cases of autonomous vehicles of failures, and look at the NTIS, the National Transportation Safety Board report about what failed, and sort of try to understand, okay, given the current ways we're tackling this problem, how do we think, what are the real safety critical challenges? And so here's a case of people may know of a vehicle in autonomous mode that stroke, and unfortunately it was a fatality, killed someone walking a bicycle across the street. And I think there's a lot of lessons that can be learned about how to sort of set up the safety apparatus, which is a difficult thing to do. But from the vision perspective, there's actually a lot of technical discussion, like what were the challenges of understanding the world. And I like this phrase right here. The automatic driving system changed the pedestrian's classification several times, alternating between vehicle, bicycle, and other, because the system never classified the pedestrian as such. And the system's design excluded tracking history for non-persisting objects, those with changed classifications. It was unable to correctly predict the pedestrian's path. So what is here is actually a timeline of T minus seconds up until the collision of the actual classification of essentially the vision system. And so the reason why I sort of highlight this is that I think that, in my view, one of the fundamental challenges here is that it seems very difficult to build stable interpretations of a dynamic world. And one instantiation of that is this notion of, oftentimes, if we look at the output of a vision system or even a prediction system applied to a stream of frames from a video, we might see flickering. So the interpretation of what happens in one frame is different than the other. And usually this is an argument for why we need some kind of temporal processing. In one way we can kind of enforce temporal stability is essentially some kind of low pass filter or smoother that says the world shouldn't change too much. But from another perspective, you could interpret flicker as a good thing, in that it's showing the system self-correcting itself. That it could be that the previous interpretation of the world was incorrect. And because there is a person or a vehicle moving out from behind an occluder in this frame, the world has changed. But then it seems resoundingly difficult to build stable interpretations of this dynamic world. And so what we've been trying to think about is, what are other perspectives that allow us to do this? I think this is one of the reasons why single frame processing is still so popular and kind of frustratingly popular, because it allows you to kind of self-correct. as opposed to building models that integrate over long time spans. So one way to sort of try to build stable interpretations of a dynamic world is to really, I would kind of argue what tends to happen now is that we tend to focus on very accurate, sort of instantaneous measurements of the world. So this is, the output of running a detector on frames from a video sequence. And if you buy the argument that I made before, or that I'm sort of implicitly suggesting, is that, okay, we should just try to build better single frame predictors with high accuracy, because that allows us to accurately understand the world. And we want to do this as fast as possible. So from one perspective, I'm not saying anything new. So in fact, it's readily agreed upon. And if you sort of open up recent papers on various flagship vision tasks like detection or segmentation, they often have graphs like these, where in one axis they'll have accuracy, and the other axis they'll have inference time, how long it takes to process a frame. But what I argue is that this is actually not the whole picture, and that doing well with this kind of graph won't help us solve the problems that we showed in the previous slide. And one way to try to illustrate this is the kind of visualizations that we tend to show on the left-hand side. But if you actually go sit in a car and look at the live stream of sensor data and interpretation that's happening, what you see is something very different. And what you see is something that looks a little bit like the right-hand side. And for the longest time, this confused me. Of like, is this just a visualization bug? Are we not sort of showing the right frame with the right output? But I argue that the right-hand side is not a visualization bug, and that it reflects this undeniable fact of what I would call sort of embodied perception, and that by the time an algorithm finishes processing a sensor measurement, the world has changed. And that is what's causing this misalignment. Now, you can artificially make the right-hand side look better by showing a historical image of the world as it was when the algorithm started processing that frame. But that's not really real-time embodied recognition. The right-hand side is we have to act in the world that's instantaneously in front of us. The argument that we want to sort of motivate here is that there's actually, I think, kind of a subtle, perhaps confusion or a subtle question about what does it even mean to be real time? And so there's various benchmarks that have been defined, oftentimes in the tracking community, and also in recent AV benchmarks that I think we'll talk about in this workshop as well, where one definition of real time could be you must finish processing before you get the next sensor measurement. And I would call this like a fast detector. But then what I argue is that at some level, it seems like this can't be the right, at least theoretical way of thinking about this, because this is tying the definition of real time to your frame rate. But the frame rate is not a constraint. It's a design choice, just like we choose the hardware and we choose the camera sensors and we ultimately choose the acquisition rates. And furthermore, different sensors have very different frame rates. LiDAR famously typically works at 10 hertz. And so, if we have a person or a child that appears behind an occluder in between two sensor measurements, I don't think it's appropriate to say that, oh, we're not responsible for perceiving or acting in response to this person that appeared behind an occluder until the next clock cycle. Like, ultimately, we have to sense and act in a continuous world. And so there's this, we're sort of building on a body of work that we presented at ECCV 2020 called Towards Streaming Perception, where we advocate for a different perspective on how to think about this. And that is, we require an algorithm to report the state of the world at all time instants, even if it's not done processing the previous frame. And what that means is you can choose to run a more accurate detector that's slower, let's say, but when the detector is running, it can't be, it doesn't have access to, or rather the right way of saying it is that when the detector is running, it still is responsible for outputting the state of the world at all time instants, because essentially that's the way in which we have to act. And if you think about how to actually define this as a benchmark, it's actually rather simple. So we're showing you on the left-hand side, the real-time prediction of just running a detector on a live stream of data. On the right-hand side, we're showing you, let's say, a visual of ground truth. So offline, we can label every single frame on that data with what the state of the world is. And now we can literally measure the accuracy of this prediction. We can benchmark it against the ground truth, given on the right-hand side. And so what this allows us to do is essentially turn any kind of single frame metric into a streaming metric. And this is very much related to work on real-time or anytime algorithms. But historically, that body of work suggests that oftentimes that views compute through a contract lens that says your algorithm must finish by the next frame. And so even if it's not done, it has to output a partial answer about the world. And in our view, what we're saying is the algorithm can decide when it finishes. But if it chooses to take longer to process a frame, well, then it has to spit out some intermediate answer about what the world is doing. So essentially, just to give you like a preview of results. So the left-hand side is if you just run a detector that's, let's say, been optimized either for speed or for accuracy, it ends up being not great in terms of this real-time metric. But then if you actually optimize for this streaming accuracy, you end up sort of trading off between not running a detector that's so fast that it compromises accuracy and not running a detector that's so slow that it ends up lagging behind the world. So if you define this as just a criteria, it turns out you can optimize for this. So instead of having essentially a cross entropy loss that's minimized, you can minimize a streaming cross entropy loss. And when you do that, a number of surprising behaviors emerge from systems optimized in this way. I'll mention that this award, this paper won the Best Paper Honorable Mention Award in ECCV, the same one that NERF won, but NERF has clearly had a lot of fanfare. But what we've done is we've actually held, Martin, the student behind this, has put together a benchmark competition that I'll talk about in the next few slides. And so we're hoping folks kind of gravitate onto this view of real-time processing, which we think is sort of a fundamental property of, I think, any embodied perception system, including self-driving vehicles. So ultimately, there's this, so what are some of the interesting behaviors that emerge if you take this perspective? So these plots that we see in commonplace that trade off accuracy versus latency, it turns out that, you could imagine, optimizing one side of this where you build very fast detectors that operate within the frame rate. And you could imagine optimizing the other side of this where you build very accurate detectors, but end up being really slow. You have to skip a lot of frames. At this, if they take 200 milliseconds, you'll have to skip on the order of 6 or 7 frames. And it turns out neither of these end extremes actually optimize the streaming accuracy. It turns out something in the middle does. So there's actually a sweet spot that trades off sort of accuracy versus the reactiveness of the system. And if you think about this a bit more, the sort of simplest thing you can do if you're still trying to, if you've analyzed the state of the world the last time that you saw a frame, but you're still responsible for reporting the state of the world while you're processing this next one, the simplest thing you can do is say, all right, I'm just assuming the last time I opened my eyes, this is where I saw the objects, this is where I saw the semantic labels. I'm going to assume that holds still. But you can imagine that that's almost like a zeroth order model. And what is arguably much more effective is a first order model that says, well, if I've seen things move a certain way, I'm going to assume that all things being equal, that the world is ballistic, that it continues to change the way that it has been changing. So what that suggests is if you really want to optimize this sort of streaming real-time accuracy, tracking and forecasting, meaning you sort of estimate how things are changing and you propagate those estimates forward in time while you're busy processing the next frame, they emerge as things that that optimize this streaming AP, which is kind of neat because ultimately this is just a single frame metric. But it turns out that tracking and forecasting helps you achieve this better accuracy in the single frame metric. But in order to do this, you have to have extremely lightweight tracking and forecasting solutions. And one of the things that we saw is that when we try to evaluate, current trackers and current forecasters, they become incredibly, it ends up, if they take a lot of compute, they slow you down and they make the system lag even more. So it's sort of this way of sort of formalizing it forces you to be honest. And there's some other sort of surprising results that emerge from this perspective. And one thing that was kind of shocking to me was that you could imagine that current systems, they oftentimes in sort of a robotic environment, you operate in sort of an asynchronous fashion. So if you're busy processing the frame and then you finish processing your last frame, then you go and you grab the next frame that's available on some buffer and you start processing that. And what we find is that actually might not be the optimal thing to do if you define this metric and really optimize it. And that sometimes it's better to wait and sit idle and wait for a new frame to arrive, as given by this orange region here. Wait for a new frame to arrive rather than start processing an existing frame that will soon become stale. So this has again, to me, kind of a very surprising result that if you really want to maximize responsiveness and reactiveness, sometimes the best thing you can do is actually to sit idle and wait for a fresh sensor measurement to arrive rather than just kind of grab one that exists right now. And so what this really suggests is that to really optimize this sort of streaming metric, you need to asynchronously schedule when you decide to compute. So what ends up happening is that there's a lot of kind of behaviors that emerge by sort of formalizing this metric in this online fashion, and then actually optimizing architectures for this. And then finally, even though it motivated this very much from the AV perspective, another sort of personal motivation of mine is that I think this is very much true of human vision and biological vision. So it's very well known that human reaction time is roughly around 200 milliseconds. So the time it takes from when you perceive something on the retina to when you can sort of manipulate your hands through sort of neurological commands is 200 milliseconds. And so what that means is that if athletes are performing highly skilled maneuvers, such as hitting a fastball that's moving 100 miles per hour, what that means is when they are actually moving or controlling their hands and bodies, they're actually using a stale measurement from their eye. Essentially, if I'm trying to hit a ball that's moving 100 miles an hour, the image that I have of the ball is actually 30 meters offset from where the bar will be when I'm able to move my hands to strike it with a bat. And so what that suggests is that humans must fundamentally be making use of tracking and asynchronous forecasting. And there's lots of evidence that suggests this is the case as well. So I kind of mentioned that we think this is a pretty kind of, or we hope that this is an interesting way of evaluating algorithms in a latency-aware fashion, and it kind of allows for sort of creative architectures to kind of bubble up. We actually held a streaming benchmark that Martin and collaborators will talk about later on today, where instead of optimizing average precision, you optimize streaming average precision. And there's a lot of sort of frameworks that have been built up for how do you, one of the annoying things about, so in full disclosure, one of the annoying things about this perspective is that now when we talk about the accuracy, the average precision of an algorithm, it depends on the hardware that you use. Because if you have access to more GPUs or better GPUs, the algorithm won't lag as much, and so it will have better accuracy. And so from one perspective, you think this is really frustrating because now it complicates our discussion and evaluation of accuracy. But from another perspective, I would argue that that's fundamental to embodied perception. When you go run things on a car, it does matter, the hardware that you use. And essentially embodied perception means that the body depends, the way in which we sort of measure accuracy and develop algorithms should be intimately tied to the bodies that we use. So this is both a blessing and a curse. And historically in vision, we haven't really embraced this kind of evaluation. But I think this is sort of needed to, as we move toward, implementing real systems and creating safety critical settings. So I hope folks would consider sort of joining in on this, because I think it does offer some interesting perspectives. And one of the things that we found, for example, is that attentional processing, not in the sort of transformer notion of attention, but this is more in the human vision notion of attention, that we should spend more effort on certain pixels in the image where we think interesting things are happening and less effort on others. It turns out that attentional processing also emerges as a very effective strategy for optimizing streaming accuracy. And again, this is sort of, to me, very comforting in that it seems like that's in some ways a fundamental part of human biological perception. We attend and we saccade, we focus on certain things. And that kind of adaptive processing is not as common in practical AV systems. Okay. Riffing off of this notion of sort of tracking and forecasting emerge as sort of first-class citizens, even if you care about single frame accuracy. We also have some pretty extensive efforts of creating a large-scale tracking challenge that really looks at diverse data, and even not just AV data, but sort of as much kinds of video content as we could. And so I've urge folks to look at this as well. And the hope is to sort of create kind of a large-scale test bed for the unique perspective that we're trying to sort of focus on. This is that focus on the fact that rather than sort of work with or fixed small-scale ontologies, if we really believe in perceiving things in the open world and urban corridors, we need to be able to detect and track and react to almost anything. So really, essentially, this is a large vocabulary tracking setup, which we find is relatively rare. Usually, we tend to focus on, just cars or people, but in reality, we have to handle everything. Okay, I'll just quickly sort of finish with a couple more sort of thoughts. Sort of riffing off of this last comment I made as well about knowing that some object is present is super crucial. I feel like this is maybe another big lesson I've learned from my time in the AV industry, which is I feel like a lot of vision is really focused on sort of semantic classification. We work with ontologies and lists of labels. And the example I like to give is pretend like a trash can rolled over in the street and debris and clutter rolled out of it. It somehow doesn't make sense that we have pre-built detectors and semantic labels for each of these things. And it feels like instead it's much more important to note that there's some object here that exists and that is moving. So one thing that we've been focusing on a lot is the role of motion in trying to build generic open world systems. And so I'll sort of make perhaps a controversial claim or perhaps not. When I show the examples in this previous frame of just weird debris that's lying on the road, and how do we build models that can react to any sources of such debris, I think it's very natural to think about geometry and shape. So this is where if we can understand that there's some 3D obstacle, that we can avoid it. And so this is why 3D sensors are so ubiquitous. And clearly sensors have a incredibly huge role to play here. And something that we've been exploring as well is, well, how far can you get with a camera? And so there's been an enormous amount of work in the field on how to build systems for inferring 3D shape and structure from images. And the perspective that we've been trying to advocate is, let's not do it just from a single image, but from multiple frames. And in some ways, that's a very old perspective. This is what Structure for Motion, or SLAM, does. But historically, those methods have really been tuned for rigid scenes. And I go back to the motivating scenario of, I think the crucial question here is, how do you build, I guess, 3D models of a world that's dynamic and changing? And so we've been focusing a lot on sort of extracting motion as a first-class primitive. So there's been some work on estimating. Here's kind of an interesting phenomenon that's always intrigued me. The fact that low-level primates and insects and rodents can navigate quite well, like a fly. But then it doesn't seem like they would do that by semantically recognizing things that are happening. And in fact, there's lots of sort of evidence to suggest that motion plays a huge role in lower level organisms for navigation. So one thing we've been looking at is, motion is clearly a very historic task that's been examined at length in the vision community. So optical flows, the classic problem of estimating how pixels move in the U and V direction. one thing that we've been looking at as well is there's an extension of optical flow, which surprisingly in the computer vision community hasn't really been examined that much, which is called optical expansion, which is not only you can track a pixel as it moves left or right, you can track a pixel as if it gets bigger or smaller. And the reason why that is so useful is that reveals something about the change in the depth of that pixel. As things get closer, they get bigger. And so, in fact, what I'm visualizing on the bottom image here, although it looks kind of like a depth map, what it's actually visualizing is the rate of expansion of every pixel. And so this is optical expansion. It's fairly readily extracted from image pairs. And what this gives you is actually, you can do some sort of back of the envelope calculations from your intro vision class. And what this really tells you is time to contact for every pixel. Because things that are getting bigger, you're more likely to hit. And so what's interesting is that I think time to contact is something that we haven't been looking at a lot in the vision community, but it's related to, but it's different than these other flagship low-level tasks like depth estimation or motion estimation. The canonical example I would give is that, if you're moving slow toward a close-by wall, or if you're moving fast toward a far-away wall, it could be that both of these things have the same time to contact, but they both have different depths. They both have different motions. But what's interesting is that the way in which you interact with them, the time to contact value is the same. And that's actually in some ways a more robust quantity to extract than either of the other two. So we've done some work on sort of trying to advocate this as perhaps another flagship low-level or maybe even mid-level vision task. I want to point out that this is not our work, but a nice piece of work also looks at time to contact, and this was one of the best paper finalists this year in the CVPR. So it's the derivation is sort of, there's math behind it, but the intuition hopefully is natural, that if things are moving closer to you, they get bigger, and so you can measure that. And in fact, we've been building off of this work to build systems that can detect and segment and track any kinds of objects, but essentially using motion as the key as opposed to appearance. And one of the things that we sort of encountered along the way, this is surprising to me, was that if you have two frames with like what kinds of moving objects can you detect and segment? So here's a very common case. You're driving down the street and there's another car moving in the opposite direction. And so we asked this interesting question, can you segment out this car? Can you identify that this is all the pixels on the car are moving in a different way than all the pixels on the rigid background? And it turns out that you can't. The way I should say that is that there is a 3D interpretation of those two frames that is consistent with a purely rigid world. And that 3D interpretation pretends that car is floating above the ground. So it turns out that you can't strictly just from image measurements figure out if that is a stationary object or a moving one. But of course, the reason why we are able to resolve that is that we have geometric priors. We don't believe cars are floating above the road. And it turns out you need to sort of insert those in to resolve these ambiguities. So we have almost a sort of a theoretical work that looks at when can you segment out objects from a moving flow field and actually build these observations into a network. That essentially is an object detector that based purely on motion. And so it's essentially a rigid object detector. And you can kind of see the behavior of this thing here. Not only does it detect rigid objects that are moving, but it also estimates sort of overall camera motion. And the goal is that this kind of thing can help you identify objects without needing to name it. Apologies here, the reference shouldn't be archived, it's a CVPR paper. The other thing that this points out that the earlier speaker mentioned is that this points out the subtlety in identifying moving versus stationary things, which turns out to be an incredibly important and surprisingly difficult task. As a car is parked and slowly starting to move, the way that you should interface or react to it is very different. So estimating very small motions is incredibly important. And so I think that sort of building better flow and motion estimation modules I think will be an important part of the final answer. And it can now allow you to, now we can sort of do things of, detect and track people on e-scooters, even if we've never seen that before. We don't have to have a training data set where we have these kinds of special mobile pedestrians, just by virtue of how we've designed this thing. And one more cool thing that we've done with this, I'll sort of, in the shameless advertisement, I'll maybe stop here, is that we've used these motion estimates to build models for essentially inverse graphics processing of video sequences. So what I'm showing here are essentially it's 3D models that have been fit to video sequences, just using essentially very classic almost analysis by synthesis or inverse graphics rendering engines. And the trick to getting all of this to work was essentially using flow as an input to all of these systems. So the reason why I'm sort of super intrigued by this is that at least historically, when we've seen videos like this, in my experience, to get this level of accuracy and fidelity of a person with clothing, you either need lots of cameras in some capture studio, or you need very strong prior models. You've built up scans of people, and you expect the person that you see here to look somehow like the database of scans that you've built up. Here, nothing like that was used. It literally is starting from a generic sphere interpretation of the object that's in the scene, and it just keeps deforming this to an inverse graphics rendering engine to match the data in the scene. So this thing can now essentially detect and track camels, even though it's never seen one before, just by virtue of essentially matching to the flow data that we see in the image. So I think this is also...
Hey, Deva?
Yes.
Your time is actually up, and our time is quite tight.
No
is there something you really wanted to kind of highlight?
I'll just end here. So sort of like the 30-second view summary was that so in terms of temporal streaming processing, we think there's other ways of looking at the problem that really embraces this notion of like online real-time analysis, which I think is fundamental to embodied perception and self-driving in particular. And then in terms of the building systems that can really understand what's happening without requiring massive amounts of training data, open world systems that make use of motion and shape as first class primitives. So I'll end there. Thank you.
Okay, thanks a lot for the talk, and sorry for interrupting.
No problem at all.
Yeah, there is unfortunately no time for questions, and I think it's time to hand over to the Waymo Open Challenge.
Got it.
Yeah, it was a pleasure to have you here, and yeah, I'm looking forward to look at your CVPR papers the next few days. And with this, it's a pleasure to hand over to Zoe and the Waymo Open Dataset Challenge.
Thank you, Alex. Hi, everyone. Good morning, good afternoon, and good evening, depending on where you are in the world. Welcome to the Waymo Open Dataset session at the workshop on autonomous driving. My name is Zoe Young, and I'm from Waymo Research. I'm here to share about the datasets that we have built and to announce the winners of the Open Dataset Challenges. Many thanks to the workshop organizers for providing this platform. First, I'd like to give an overview of Waymo Open Dataset. Our team first launched the Open Dataset in August 2019, which includes our very first version of the perception dataset. In March 2020, we continued to expand the perception dataset and launched 5 challenges focused on perception tasks. We then announced the winners at last year's CVPR workshop. This year, in March 2021, we launched our motion dataset, which targets tasks like motion forecasting and planning. We launched 4 challenges this year, 2 focused on perception and 2 focused on motion prediction. And now the challenges have concluded, and we're here to announce the winners of this year's challenges. We're happy to share some stats on the Open Dataset. So far, we have over 20,000 registered users for the Open Dataset, and it has spurred over 200 publications from the talented research community. Our team is really happy to see that the datasets we have built have supported so much research. Our team's goal is always to contribute to the research community with one of the largest and most diverse autonomous driving datasets. And we also wanted to say thank you for all the amazing work you have done with Waymo Open Dataset. In case you don't know, here are the highlights of our datasets. Our perception dataset has 1950 scenes at 20 seconds each. The sensor data are synchronized and wanted to be diverse, so we included scenes across different weathers and road conditions. Our motion dataset is what we just released this March. We have three main ideas when building this dataset. First, it should be big, so we included over 1,000 scenes in it. Second, it should be interesting, so we specifically mined for interactions when selecting leads from our driving log, and also include data from various regions. And third, it should be high quality and useful. We included 3D bounding boxes for each object and included 3D maps. The model that was used to generate the 3D bounding boxes is published. In our colleague's paper, Off-Board 3D Object Detection, you can see it below, which is a paper right here at CVPR this year. Feel free to check it out if you're interested. Now let's talk about the challenges. 4 challenges were held this year with 2 on prediction using our motion dataset and 2 on perception using the perception dataset. A quick note here, although the challenges have ended, the leaderboards will remain open for future submissions. We hope our dataset and leaderboards will continue to serve the research community. So if you weren't a part of the challenges, feel free to check out the datasets and submit to the leaderboards anytime in the future. Before announcing the winners, I would like to make another announcement on our dataset. I'm happy to say that we will be releasing version 1.1 of the motion dataset this summer. This version includes lane connectivity, such as lane neighbors, which is a very useful signal when it comes to predicting road agent behavior. And in addition to that, we're also making some map improvements. We're also always working to expand the open dataset to contribute more to the research community. So please stay tuned for more updates on our datasets. Now let's go to the part that many people are waiting for, announcing the winners. Let's start with the perception challenges. This year's perception challenges are modified a little bit from last year's with the latency constraint. This is to make the challenge a little more relevant to autonomous vehicles onboard use case. For this challenge, the task is to perform 3D detection of objects with a model that runs faster than 17 milliseconds on a NVIDIA Tesla V100 GPU. The methods are ranked by accuracy, which is mean average precision with heading. All right, coming to the winners. So the first place for this challenge is AFDET V2 from Yihan Hu, Zhang Zhuangding, Renzhou Ge, Wenxin Shao, Yi Huang, Kun Li, and Qiang Liu. Congratulations to you all. This is fantastic work. The second place for the real-time 3D detection challenge is Centerpoint++, and the authors are Tianwei Yin, Jingyi Zhou, and Philip Krahenbull. Great work. Congratulations to you. The third place for this challenge is X Autonomous 3D, and the authors are Lu Tian, Jin Zhangpeng, Rongzhang Zheng, and Han Liu. Many congratulations, team. So for 3D detection challenge, there is another track with a different evaluation criteria. Although it is not eligible for winning an award, the model with the lowest latency and average precision, about 70%, will be given the special title of most efficient model. And this special title goes to the method AFDET V2 base, which is also from Yihan Hu, Zhang Zhuangding, Renzhou Ge, Wenxin Shao, Li Huang, Kun Li, and Qiang Liu. Congratulations again on gaining this title. Let's move on to the next challenge, real-time 2D detection. The task here is very similar, perform 2D detection of objects with a model that runs faster than 70 milliseconds on an NVIDIA V100 GPU. So the methods are ranked by accuracy, which is mean average precision. And the first place for this challenge is Leap Motor Det. The authors are Fenfen Wang, Tiankun Xie, Lin Dongli, Yao Nong Wang, Hong Tao Zhou, Han Xu, Yu Wang, Xiu Bo Ye. Congratulations, team, for winning this challenge. The second place is DD Map Vision, and the authors are Yueming Zhang, Xiaolin Song, Bingbai, Peng Feixing, Chao Liu, Jin Gao, Zhihui Wang, Ya Wei Wen, Hao Jing Liao, Guo Shan Zhang, Peng Fei Xu. Fantastic work, and congratulations to you all. The third place is Dearly Self Ensemble, and the author is Nikolay Sergevsky. Congratulations to you for winning the third place. Okay, now let's take a look at the prediction challenges. For motion prediction, the problem definition here is that given historical data of road agents, predict the positions of up to 8 agents for 8 seconds into the future. The main metric here is mean average position, which is a metric that our team proposed and detailedly explained in our paper for motion dataset. I will skip the definition for the sake of time, but please feel free to check out the paper and our website. Let's go to the winners. So the first place for this challenge is Tsinghua Mars since TNT. The authors are Junru Gu, Xiao Sun, and Hang Zhao. This fantastic work, and congratulations to you for winning this challenge. The second place method is Rico app. The authors are Xiaoyu Mo, Zhiyu Huang, and Chen Lu. Great work. Congratulations, team. The third place goes to Simple CNN on raster. The authors are Stepan Konev, Artyom Senekoyev, and Kiro Brat. Congratulations. Last but not least, the interaction prediction challenge. The task here is to predict joint future positions of 2 interacting agents, given agents' historical data on a corresponding map. The main metric is also mean average position, the same one as motion prediction challenge, but a little more generalized. The first place of this challenge is Heat IRM4, and the authors are Xiaoyu Mo, Zhiyu Huang, and Chen Lu. Congratulations. Congratulations again to all the teams. You have done fantastic work. These teams have described their models and methods in their technical reports, which are now publicly available on this workshop's website at CVPR'21.wad.vision. So please feel free to check out these amazing reports. For all the teams that have submitted to the Open Dataset Leaderboards, I wanted to say thank you. Thank you for the work that you have put into this. Many more teams have very high quality work. All of us at Waymo Research are very impressed, and we're so happy to see the datasets we built leading to such great models. Many people might be interested in hearing about these teams' methods. And now I will give the stage to some of these teams to talk about their models. We'll first have the first place for each challenge to present. And after that, we will have a special guest, David Wu, who is a student from Green Middle School, to talk about his experience with Open Dataset, although he could not be a part of this year's challenges. Now let's welcome the first team, AF.V2 and their presenter, Qiang Liu. Turning it over to Qiang.
Okay. Hello, everyone. My name is Qiang Liu. I'm glad to be here to present our solution to the real-time 3D detection track in the Waymo Challenge this year. We won the first place and also the title of the most efficient model. And this is our team: Zhuang Ding, Yihan Hu, Runzhou Ge, Wenqin Shao, Li Huang, and Kun Li. We're all from Horizon Robotics, and we make the software and hardware solutions for ADAS and autonomous driving. And this is the outline for my talk. I'm going to introduce the framework of our solution, some methods we use to improve the performance, and then results. So our solution is an anchor-free single-stage model, which is extended from our last year's model, AFDET. There's 4 major components in this model: point cloud voxelization, 3D feature extraction, region proposal network, and anchor-free detector. So the first step is the voxelization. And for the voxelization, we take the mean value of all the points that falls in a voxel, and we do not limit the number of points per voxel. In the second step, we use the sparse convolution to do the feature extraction. And we modified our last year's model to reduce the latency. For example, at the early stage, we reduced the number of residual blocks. And also, for the z-axis, we do a downsample of 8 instead of 16. And we found these tricks are effective to get a good trade-off between the network capacity and the latency. And the third step is the RPN, in which we used a self-calibrated convolution. So the main idea of this self-calibrated convolution is to split the channels into different groups, and each group going through different convolutions and also resolutions. So the resulted RPN has a larger receptive field and also can handle semantics better. And this is our detector, which is composed of 7 subheads. So of all the 7 subheads, we have 5 heads, the same as our last year's model, AFDET, which includes a heat map and the z-value, the 3D size, the orientation, and the offset. And this year's model, we added 2 new subheads, which are the IOU prediction head and the key point subhead. So the IOU prediction head would predict a IOU value, which is used to rescore the classification score and give us an IOU aware confidence. And this subhead can effectively deal with the misalignment between the classification score and the localization maps. And for the key point subhead, we use it as a auxiliary supervision. It is not used for the inference time. And for the losses, we use the focal loss for the heat map and the key point auxiliary. And for the IOU prediction, we use the smooth L1. And for all the others, we use L1 loss. And for further improvements, we use the point cloud densification. And in this case, we used only the previous frame, which is transformed to the current frame coordinate system to densify the point cloud. For data augmentation, we used both the global level and instance level augmentation. For the global, we do the random rotation, scaling, and translation on the entire point cloud. And for the instance level, we do the rotation, translation, and randomly manipulate, copy and paste the instances to the point cloud. Okay, the final trick we used is it's called the stochastic weight averaging, in which we first get a baseline model trained, and then we keep training for 5 additional epochs. And in each epoch, we used a cyclic schedule for the learning rate. And our final model is an average of these additional trained checkpoints. And to improve the latency, we re-implemented the voxelization, as we found that voxelization is a bottleneck for the latency. So for each point, we accumulate for each point to the corresponding voxel, and we do the accumulation and counting on GPU. And then for each point, we have index for the voxel, and this list of indices has duplicates because some points may correspond to the same voxel. And we remove the duplicates on CPU. And then we use this unique list of voxel index and gather and calculate the mean to form the sparse voxel. And this can give us about a 17 millisecond boost for the overall inference. And here are the results of our solution. And we trained 3 models: AFDET v2, the base, and the light. All 3 models use the same network structure. And for the AFDET v2 and the base, we used densification, which used 2 frames. And the other differences between these 2 models are the number of training epochs and the grid size that we used. So AFDET v2 got the highest MAPH score, and it runs at 60 milliseconds. And the base runs at 55 milliseconds, and it won the most efficient title. And I'd like to mention that we have a light model which can run much faster at 46 milliseconds, but the MAPH is 69.95, which is 0.05 less than the required 70 MAPH. Okay, to compare the modifications that we've done for the model, we did an ablation study, which include the comparison between with and without the IOU rescoring, and also the key point supervision, the data augmentation, the self-calibrated convolution. And we found that with IO rescoring, we can get the most significant improvement. And secondly, the self-calibrated convolution. So it might be better seen from this chart that when use the self-calibrated convolution in the RPN, we have about one point improvement, and on top of that, with the IOU branch, we get almost a 3-point improvement. Yes.
Sorry to interrupt, but we're running out of time. So
okay.
Just to remind you to wrap up with your presentation. Thank you.
Okay, this is a visual display of the final results. And I'd like to just summarize that our AFDET v2 is a single stage anchor-free model extended from our previous model. And if we made a few modifications, among which the most significant one is the IOU aware branch, which rescored the classification score. Okay, and we thank for all the prior arts based on which we made our solution. Okay, I'll stop. Thanks.
Thank you, Qiang, for your presentation. Wonderful talk. And next, I will pass it on to Team Leapmotor Det and their presenter, Fenfen Wang.
Okay, stop sharing.
Hi, everyone. This is Fenven Wang from Leap Motor Technology Company. It is my honor to be the speaker today. I'll present our 2D detection. This is a joint work with Qiankun, Lingdong, Yaonong, Hanxu, Yuwang, Xiubo, and Hongtao. Basically, my presentation will be divided into 3 parts. At first, I'll be speaking about our motivations, then the methods we used, namely the 3 steps to do the experiment will be introduced. Lastly, I'll show our results submitted to test dataset. The main reason that inspired us to do this job is that compared to last year, there's an added latency requirement that the model must run faster than 70 milliseconds per frame. So we try one stage detector at first. Now let's start with our methods. It is well known that Waymo Open Dataset is a very large dataset. We want to do more experiments. So for one thing, we extract 10% of dataset from chain and validation dataset to form a sub-chain and sub-validation dataset. For another thing, we adopt a small backbone ResNet 18. ATSS is adopted as a baseline detector. The training hyperparameters are almost the same as default hyperparameters to train COCO. Validation results are all in level 2. Here, WAP means official, Waymo official MAP, and CAP means COCO MAP. The baseline is trained on sub-train dataset and evaluated on sub-validation dataset. We focus on small boxes which account for a lot of bounding boxes. Firstly, we add P2 feature map. As you can see from this picture, P2 is a green block we add. To make sure the flopes wouldn't increase too much, we decrease FPN channel to 64. After adding P2 and the decreasing FPN channel, CAPS increased obviously. Secondly, we use multi-scale training, which can increase CAPS by a large gap, and also WAP. Since the hyperparameters are referenced from COCO training, which is actually not very suitable for our task, we set initial learning rate higher and use cosine learning rate. This can also help increasing WAP. Then we compare ATSS to another 3 strong detectors. As shown in this table, GFLv2 performs best. However, the enhancement module of GFLv2 costs a lot of time, so we choose GFLv1 as our final one-stage detector. Considering the latency requirement, we choose a GPU-efficient backbone, VOVnet v2 39. Inference phase is running in half-precision floating point, that's FP16, and fused batch normalization. The table shows the result submitted to test set. As you can see, latency time is 53.8 milliseconds. There's 16 milliseconds redundancy. What we to adopt a 2-stage algorithm based on the former 1-stage detector. You can see the network architecture here. We replace RPN with ATSS in faster RCN for providing proposals. Since ATSS is only for proposals, the regressed boxes don't need to be very accurate. Here's 2 modifications. First, we remove Sentinel's branch. Second, heads for objectness and regression are shared. We adopt double head for RI head. For final score, it's determined by objectness from RPN head and classification score from ROI head. This is experimental settings for two-stage detector. It's almost like previous settings. In this experiment, dataset for training is train dataset, and we've evaluated on both sub-validation dataset and validation dataset. Evaluation indicators don't differ much on these two datasets. So in next experiment, the sub-validation will be evaluated. You may notice WAP of baseline here. With the mouse. It's not exactly as same as the one I mentioned last slide. This one. That's because we applied fusing batch normalization and using half precision floating point to evaluation here. To further ask three strategies on inference stage. First one is calibration. Considering evaluation metrics, it's better for score distribution over classes to be softer. Temperature T is set to 2. Second one is per class NMS. WAP adopts different IOU thresholds for each class. Last but not least, we increase maximum output boxes to 150. This is our final submission to test set. You can also see from the leaderboard or our technical report. Here are some strategies that don't work for us. In our head, we tried IOU balanced sampler and OHEM sampler. In our pooling, we changed feature mapping level. And in inference, we tried soft NMS and box voting. We believe that two-stage detector can perform better than one-stage detector and also run faster by careful designing. Little effort has been put into inference of the model. We surely believe it could perform better with other inference tools like TensorRT. I'd like to thank Waymo for providing this challenge, and the greatest thank goes to all the staff of Waymo Open Dataset who are very kind and helpful, replying questions very instantly and in details. And I would also thank our company. That's the end. Thank you very much.
Thank you, Feng Wang, for your presentation. And next, it would be Hang Zhao from Tsinghua Mars DenseTNT to talk about their model for motion prediction.
Okay. I guess you can see my screen already. Hi, everyone. This is Hang. I'm currently an assistant professor at Tsinghua University. It's a great pleasure to meet a lot of friends here. And I would also like to thank all the organizers for putting this amazing challenge and this amazing workshop together. I'm presenting our winner method called DenseTNT on behalf of our team. In our team, we have Junru Gu, undergrad student at Tsinghua University, and who is also an incoming PhD student of mine, and he did most of the work here. And Qiao Sun, he's an intern in our lab, and myself. Okay, let's have a quick overview of motion prediction models. Due to the stochastic nature of future, it is now more popular to predict multiple future trajectories in autonomous driving. And one of the popular classic method is based on generative models. We have models like VAEs, GANs, and flows. And more recently, anchor-based models has gained popularity. Anchor-based methods such as multipath and CoverNet, they use trajectory anchors. And the TNT, which use goal-based anchors. And in our work, we basically propose an anchor-free model called dense TNT. And we'll go into details later. One of the prominent work in the trajectory prediction is TNT, proposed last year, where they decomposed the trajectory prediction task into multiple interpretable and end-to-end trainable modules. First, they encode the scene context to get the features, and then to predict the goals. And finally, to complete the goals to form a trajectory. The intuition behind the TNT model is that the goal or the target, that is the endpoint of each trajectory, captures most of the uncertainty of a trajectory. So instead of directly predicting the whole trajectory, it is easier and more straightforward to estimate the probability and the location of the target. And our work is built on top of this. The one characteristic of the TNT model design is that they use a sparse set of goal anchors from the map. As you can see, these goals or targets are sampled from the center lines of the lanes. However, the sparse anchors bring a couple of issues. The first issue, one anchor can only generate one goal. So it is difficult to make multiple goal predictions around one anchor. Second, it cannot make use of fine-grained information on the road. For example, it's hard to model the relative distance between an ordinary point position, just an ordinary point on the road, and its relationship or its distance to the road boundaries. So we propose to use dense goal candidates to improve the performance. And as you can see, comparing these two methods, the sparse candidates only samples very few number of anchors as the goal candidates, and our dense candidates scoring methods try to sample all the points on the road so that we don't miss any locations on the road. This is very similar to pixel-based object detection methods. We call our model dense TNT. It generates goals without using predefined anchors. And it encodes maps in a sparse to dense manner. I'll tell you how. And this is our model architecture. First, the model encodes the scene context, including the maps and the agents. And then it goes through a sparse to dense encoding module to output dense probability on the map. The dense probability are about the goals of the trajectories. And finally, we have a trajectory completion module so that we can get continuous and complete trajectories. And we split the whole architecture into 4 parts and explain them one by one. The first part is called the sparse context encoding. The sparse context encoding, we directly get ideas from the paper called VectorNet, which instead of encoding the maps as rasterized images, we encode them as vectorized lines and polylines. And the second step is called dense goal encoding. Basically, we get sparse features from the lanes on the maps. And then we use an attention module to get the features for each location on the map. And the next step is called dense probability estimation. It's basically for each location on the map, we go from the features to its probability of being a goal of our interested agent. So after this step, we basically get a heat map of the go probabilities. And the last step is called go selection. We also follow TNT using a non-maximum suppression method to select the final set of sparse goals. And the last step is a trajectory completion. We basically connect our targets and our starting point with a simple MLP neural network. Okay, and here are the results of the performance of dense TNT model. We first compared its performance on the Argoverse motion forecasting dataset. This is a smaller dataset, which is easier for us to compare and debug. The first row is there's a tick on the sparse, which is the classical TNT model. And the second row is our dense TNT model. And we can see that we can achieve a good improvement over on the two metrics, mean FDE and the miss rate. Okay, and then the next problem is how to apply dense TNT onto the Waymo prediction task. There's one issue that we have found challenging is about the long-term prediction. As we know, in other data sets, the future prediction is usually about 3 seconds, which is pretty short, and goal-based methods perform really well. But we found that directly applying goal-based methods on these long-term predictions are not ideal. So the reason is that the assumption behind TNT is that for each prediction, as long as the goal is fixed and our trajectories, as long as our goal is fixed, our trajectory is also fixed. However, for long-term prediction, for each goal, there could be multiple possible trajectories. So to deal with this issue, we basically apply an autoregressive goal prediction method to make the final predictions of long-term prediction into the future, like 8 seconds or even more. And here's the result of our dense TNT model on Waymo Open Dataset Motion Prediction Challenge. And we achieve a mean AP of 32.81, which is very impressive on the leaderboard. And there's one drawback of our current model is that the mean FAD is not very good. And we think it's because that's at the deadline of our challenge, we did not have enough time to tune our trajectory completion module. And we believe that with more efforts, it could be much better. And here's a breakdown on different categories of motion prediction. And we can see that the cyclist gives the lowest mean AP because we found that cyclist is the most, it is really hard to handle. First, it moves faster than pedestrians. And on the other hand, it does not always follow the lanes as the vehicles. And here are some visualizations of our results. And this is an interesting case of U-turn. The orange lines are our predicted trajectories, and the green lines is the ground truth future trajectories. And then we show our rollout prediction results over the time. And here is another interesting case where the vehicle turned into maybe a garage or a parking lot. And we can see that our model, some of our model's predictions follow the curves, and some others that go into the roads. And here is another case of making turns at the intersection. And this is a big left turn at the intersection. We can see that our predictions can make predictions into different lanes. Okay, that's all. Thank you.
Thank you, Han, for your presentation. It's a wonderful talk. So we see some questions in the chat for both Zoom and for YouTube live stream for the teams that just presented. So just a reminder to those presenters at the session to check out those questions. And next we have Xiaoyu Mo for model HEAT IRM4. Passing it on to you.
Hello, I'm now sharing my window. Thank you for the introduction and thanks for having me here. My name is Xiaoyu. It's a great honor for me to introduce our solution to the Waymo interaction prediction challenge. Our method is called heterogeneous edge-enhanced graph attention network. First of all, I would like to introduce our team and our research lab. Our team consists of 3 people, me, Zhiyu, and the director of our lab, Professor Chen Liu. Our lab is called Automated Driving and Human Machine System Lab, or in short, AutoMan. Our lab is called Automated. We mainly focused on autonomous driving and human machine collaboration. Our research topics fall into 3 categories: human-like autonomous driving, human machine collaboration, and human-in-the-loop learning. We are dedicated to fusing machine learning with classic methods like planning and control to deliver a human-centered and collaborative autonomous driving system. Now let's go to our method, and we'll first explain the data processing. Our task is to predict the possible joint trajectories of 2 interactive agents 8 seconds into the future and the probabilities of these trajectories. The information we have is the historical states of the target agents in the past 1 second, as well as the trajectories of its surrounding vehicles. We also have the detailed road graph, which we have processed as bird's eye view images. Specifically for each target agent in a scenario, we translate its states into a local coordinate system. The origin is placed as the target agent's current position, and the horizontal axis is aligned with the agent's current heading. The local image is rotated accordingly, and the historical states up to 14 surrounding agents are also placed in their exclusive coordinate systems. We also construct an interaction graph of the agents to model their interactions. Now let's get to the HEAT method. After pre-processing, we get 3 types of inputs: historical states, interaction graph, and the local map. The left column shows agents' historical states, where our target agents are in green and blue. And the agents in orange are the surrounding agents. For each considered agent, its historical states is the sequence of its positions, velocity, and yaw angle over the last 1 second placed in its own exclusive coordinate system. The interaction graph shows in middle is constructed with close connections, where each node represents an agent and the directed edge from node J to node I, indicating that node J is a neighbor of node I, and it impacts the behavior of node I. The directed edges are assigned with attributes and types. Attributes of an agent from J to I contains relative measurements between node J and node I. That is the relative position, the node type, and the relative position, the relative velocity, and the relative yaw angle. Edge type from J to I contains concatenated node type of the source node and the target node. In our case, the node type is an indicator vector. We also have the local map on the right side. With these 3 kinds of inputs, we designed an encoder-decoder architecture with 3 encoding channels and 2 decoders. Let's begin from the dynamics encoder. The dynamics encoder is implemented with a GRU network. The dynamics encoder is shared across all agents. It extracts dynamics features from each agent's individual historical states. The dynamics feature is shown a bar with dots. We save the dynamics feature of target agents for later use. We then assign dynamics features of each agent to its corresponding node in the interaction graph as node feature. We design a heterogeneous edge-enhanced graph attention network. In short, we call it HEAT. To model the interaction among heterogeneous agents, the designed HEAT will be introduced in the next slide. The HEAT network models all agents' interaction with their neighbors in parallel, but we only save the letter of the target agent for this task. Interaction features is shown in bar of stars. We also design a rotation-sensitive map encoder for the local map of target agents. The map encoder is a simple 3-layer CNN without max pooling operations. The encoded map feature is shown in bar of squares. In the decoding part, we jointly consider these 3 kinds of features to predict multimodal trajectories with assigned probabilities. The joint feature of agent 1 is sent to shared multimodal LSTM decoder. Then the decoder produces 4 possible future trajectories of agent 1, the same for agent 2. Predicted trajectories of agent 1 and agent 2 are paired as indicated by the numbers. The F1 in green is paired with F1 in blue as the joint prediction of model 1. The concatenation of joint features of both agents are fed to a multi-layer perception to estimate the probabilities of the predicted trajectory pairs. P1 is the estimated probability of model 1. Let's see the designed HEAT layer. The designed heterogeneous edge-enhanced graph attention layer mainly have 3 steps. It first transforms the node feature, edge feature, and node feature, edge attribute, and edge type to a higher dimensional space. The edge-enhanced mask attention mechanism then calculates the attention coefficients using transformed features. For the edge J to I, we combine edge attribute and edge type as the edge feature, and the concatenation of edge feature and the node feature as edge-enhanced node feature. Then the designed masked attention is applied to node I's neighborhood to estimate the importance of its neighbors. Finally, node I's feature is updated by aggregating edge attributes and node features from its neighborhood. We also support multi-head attention for aggregation. More details about the HEAT layer, please refer to our preprint on arXiv. This page shows the performance of our method on the test set comparing the LSTM baseline. You can see that the proposed method improves the baseline in terms of matrix. Details about matrix can be found on the web page of Waymo Open Dataset. We also visualize our method's prediction results for vehicle-vehicle interaction, vehicle-cyclist interaction, and vehicle-pedestrian interaction. We can see that the proposed method is able to predict the joint future trajectory of 2 highly interactive agents, no matter they're vehicle to vehicle or vehicle to cyclist or vehicle to pedestrian. Okay, that's all for our methods. Thank you.
Thank you, Xiaoyu, for your presentation. Fantastic work. Thank you for sharing. So our last presenter for this session is a special guest. His name is David Wu, and he is a 7th grade student. Although he was not able to enter the challenges, his submission R² ranked highly on the interaction challenge leaderboard. And now let's welcome David to talk about his team's method.
Hello, everyone. My name is David, and I'm a middle school student, so I'm not eligible for the competition, but we built a model that would have ranked first place in the Interaction Prediction Challenge. And I would like to thank Waymo for giving me this opportunity to present. But before I begin, I'd like to first describe the key ideas behind a typical motion prediction approach, since the problems of interaction prediction and motion prediction are closely related. So a typical motion prediction approach is the multipath approach. So the model takes in an image centered at the ego agent and runs it through CNN in order to get a set of trajectories and confidences that correspond to anchor trajectories, which we can obtain through k-means clustering. For example, one of these might correspond to turning right, one might correspond to turning left, etc. And then during training for each example, the anchor assignment of the ground truth trajectory is calculated. And for example, suppose the ground truth says that the car went right and our model predicted it with probability 0.1. Then the weights in the model would be tweaked through SGD, and then maybe now it predicts it with probability 0.2 and predicts a trajectory slightly closer to the ground truth trajectory. So we repeat this process millions of times in a large data set, and boom, the neural network figures it out. So now let's get back to the problem of interaction prediction. So for interaction prediction, our model takes in an image centered at one of the interacting agents with both interacting agents colored in green. And we feel that this is enough information for the model to make predictions while considering interactions, since it can figure out which agents it needs to predict and then use the rest of the information in the scenario in order to make educated predictions while considering interactions. So the model takes the image and runs it through CNN, and it gets a confidence matrix instead of a confidence vector, like for motion prediction. Each grid cell corresponds to an anchor for the ego agent and an anchor for the other agent. So for example, one of these might correspond to agent 0 going right and agent 1 going left, and another one might correspond to agent 0 stopping, agent 1 going forward, etc. So we can get this grid for both agents by running both images, each centered around one of the interacting agents through our model. And then we transpose the second grid in order to make the two grids consistent and from one agent's perspective. And then we can average them, which creates a natural ensembling effect since we're averaging two predictions from different perspectives. So during training for each example, the anchor assignments of the ground truth trajectories are calculated. And then, for example, suppose the ground truth says that the vehicle went right and the pedestrian went forward, and our model predicted it with probability 0.05. Then the weights in the model will be tweaked through SGD, and maybe now it predicts it with probability 0.07. So this slide essentially captures the key idea behind our approach. And you can see that it's really similar to our approach for motion prediction. And in addition, you can also think of it as a 2D extension of multipath. So now you may be asking, that covers the confidences, but how do we get our trajectories? So for trajectories, we take the simplest approach possible. We just take the two sets of trajectories that we can obtain by running both images, each centered on one of the interacting agents through our model. And then we just take a Cartesian product in order to get our matrix of trajectories. So now, having covered the key ideas, let me jump into the boring details. So our motion prediction model is named AIR, but why is it named AIR? So AIR stands for three things. So A stands for anchored, meaning that our model predicts a set of trajectories and confidences that correspond to anchor trajectories, which we can obtain through clustering. In addition, predictions are supervised based on the anchor assignment of the ground truth. This breaks our problem down into intent classification and regression given intent, and also introduces a clean division of responsibility, since each mode is only responsible for predicting the trajectory and confidence that correspond to its anchor. I stands for interpolated, meaning that our model predicts 8 control points instead of full 80 time step trajectories. These control points are then splined to get our full 80 time step trajectories. And the intuition behind this is that we as humans know that trajectories have to be smooth, and then using splining helps encode that knowledge into our model. And we can implement this easily using TensorFlow graphics.maths.interpolation.bspline. R stands for rasterized. So our model is a rasterized model, and we feel that rasterization is an intuitive way to take all relevant information about a scenario and place it onto one single input that we can directly feed to our model. As the old saying goes, an images were 16 by 16 words. And then in addition, these images are human interpretable. They actually make sense. So we as humans can look at the image on the screen and figure out what's going on. So machines can do it as well. So this is basically a detailed version of what I covered on slide 2, but the only details that I would like to point out are, first of all, that we have separate per object type heads after shared FFN. And the intuition behind this is that different object types behave very differently. And this allows our model to specialize in all of them while avoiding competition and parameter learning driven by different object types. In addition, clustering is done separately based on object type. Again, the intuition is that different object types have different overall behaviors. And then inside a head, we add the centroid for each anchor to our prediction, which makes our model predict the residual and helps us avoid a hockey stick-like learning curve. And then lastly, predictions are transformed into world coordinates since our model has been working in ego coordinates up until now. So this is basically a detailed illustration of what I outlined on the interaction prediction in nutshell slides. But again, the only detail that I would like to point out is that we have separate per object type heads after a shared FFN. And again, the intuition is that different object types behave differently. So we considered two main input representations in our solution. The first of them has both interacting agents colored green and is centered around one of them, as you can see on the left. And the other one has a re-rasterized trajectory for the other agent, as you can see on the right. So for re-rasterization, we take the top prediction output by a motion prediction model for the other agent and draw it onto the image before feeding it to our model. So the intuition behind this is that we're giving the model some hints about what other agents in a scenario are doing. And it's kind of similar to how human drivers think, because like when I'm crossing the street, I can visualize what other agents are doing and modify my actions accordingly. So one of the other features of our solution is how we deal with data imbalance. So we train on a custom data set created by sampling from separate vehicle, pedestrian, and cyclist data sets with equal probability. And we can implement this easily using tf.data.experimental.sample from data sets. And then also we have a regression loss and we have a classification loss, but we need to figure out how to weight them. And a simpler approach to determine these weights would be through trial and error, but that would take too much time and require too much computational resource. So we created an empirical method that we call metric loss sensitivity analysis that allows us to determine these weights efficiently. So what we do is we partially reveal to the model the correct trajectories or confidences using the equations at the bottom of the slide, where alpha is a small positive constant like 0.1, p refers to the confidence vectors, and x to the trajectories. We then measure the decrease in loss and the corresponding change in MAP when we reveal the trajectories versus the confidences and weight our regression and classification losses to generate a similar amount of MAP for the same decrease in classification loss versus regression loss. And this helps us to avoid a scenario in which we're spending a lot of time and energy trying to decrease the regression loss to get a small boost in MAP when we could have decreased the classification loss by a small amount to get a bigger boost in MAP. So in conclusion, we developed a solution that we call AIR squared that uses rasterized images to, here are the results. So for submissions, we ensembled 4 models and also trained on the first 100 files of the validation data set. And we're currently conducting an ablation study, but we have not completed it yet due to time constraints and also constraints on computational resources. But we will post our ablation results to our GitHub repository after we release our code. So in conclusion, we developed a solution that we call AIR squared, which uses rasterized images to predict joint probabilities in the anchor Cartesian product space. And then for trajectories, we just take a simple Cartesian product of the 2 sets of trajectories from a marginal model that we obtain by running both images through our model. And then this gives us our matrix of trajectories. So in the future, we could explore extending our solution to using TNT as motion prediction for motion prediction, as since we learned about it yesterday, and we feel that it's a strong approach for motion prediction. And TNT breaks the problem down into where do you want to go and how we'll get there, and we can apply our squaring technique to the where do you want to go part. And then in addition, we could explore ways to model interactions between all agents in a scene, and that would help our model better understand the environment as a whole. And then We will share our code after the conference at our GitHub repository that you can see at the bottom of the slide. Okay. So thank you for listening to our presentation. Feel free to email me at the email on the slide if you have any questions. Thank you.
Wonderful. Thank you, David. This is a great presentation. Thanks again to all the presenters for sharing your methods. And thank you, everyone, for joining us today. I will turn it over to Alex and the workshop organizers for the next session.
Hey, thanks. Yes, the next section is actually our poster session. But to give our authors a bit possibility to draw people into the poster session, we organized some spotlight talks. And first, let me introduce Fredrik Gustafsson, which will present his work on accurate 3D object detection using energy-based models.
Yes, thank you for presenting. Yes, the title is given there. So we use energy-based models to get accurate 3D object detection. And we then integrate this conditional energy-based model into a state-of-the-art 3D object detector. And then we use this energy-based model to learn the distribution of y given x on this form. And then y is the target 3D bounding box, and x is the input point cloud. And then at test time, we can take this trained energy-based model and actually use this to refine the predictions or the bounding boxes produced by the detector. And then we show on Kitty that this then consistently improves the accuracy of these bounding boxes. So yes, so if you're interested in energy-based models and how they can be used to improve bounding box accuracy on 3D object detection, then feel free to come and check out the poster. Right, thank you.
Okay, and our next talk is by Bochun Ouyang about occlusion-guided scene flow estimation on 3D point clouds. You need to share your sound.
This one? Can you hear me? No?
There is a box in Zoom where you can turn on to share sound of videos.
Okay. Okay. We can hear. Okay, we can. Sorry about this. That's true. No?
Okay, maybe it's really hard to understand. You can share the video with us and we can play it in the second poster session.
Okay, that would be great.
Okay, good. For the remaining talks will be based on recordings actually played by us. So yeah, the first one is actually by even one of our speakers. on video class agnostic segmentation benchmark in autonomous driving.
Hello, my name is Minnatul Nasiam. I'll be presenting our work on video class agnostic segmentation for autonomous driving in collaboration with Wave. Towards the goal of scalability, most autonomous driving researchers have focused on active learning to reduce the annotation effort while relabeling images from challenging situations. Some have proposed few or zero-shot methods to help CNNs scale to a larger number of classes. These are important for the final scalability goal, but do not solve situations when autonomous vehicles have to deal with unknown objects outside the closed set of known classes used in the training. We formalize the task of video class agnostic segmentation to enable models to segment unknown objects, where we focus on two main tracks in which the problem can be solved relying on objects' motion or based on the known classes distribution. For the first track, we focus on motion instance segmentation and provide a dataset that extends Cityscape's VPS and KT mods with motion annotations, where we provide more sequences, larger number of categories, and manually annotated masks. We evaluate baselines based on multitask two-stream methods that learn, join panoptic and class-agnostic segmentation, then experiment with and without ego flow suppression on our proposed dataset. The dataset and models are made publicly available. For the second track, we focus on open set segmentation and provide a synthetic dataset with unknown objects that are outside the known classes in most of the current large-scale datasets. We built multiple scenarios within Carla integrated in their scenario runner, where we use separate towns and props for training and test data. We build upon a recent overwork that uses a Mahalanobis-based approach to segment unknown objects, then we extend it with auxiliary contrast of loss on the region level using semantic and temporal guidance, which is more suitable to our dense prediction task in video sequences, unlike image level 1. We have found that our proposed losses lead to improvement in situations with relatively smaller scale datasets and severe class imbalance. Finally, we demonstrate qualitative results on both Cityscape's VPS and ours, where we show unknown objects and semantic segmentation pairs.
Okay, and our last talk is by Keishi Ishihara on multitask learning with attention for end-to-end autonomous driving.
Hello everyone, thank you for watching this video. My name is Keishi Ishihara, and today I'm talking about our work titled Multitask Learning with Attention for End-to-End Autonomous Driving. End-to-end behavioral cloning allows an autonomous vehicle to be trained end-to-end, and it has shown reasonable performance in goal-directed navigational scenarios. However, the learning of reacting to traffic lights has not yet been extensively studied. Therefore, we focus on a driving policy that can also handle traffic lights. In this work, we propose a novel network architecture named Multitask Attention Aware Network. It has two key concepts to tackle the problem. First, multitask learning of scene recognitions, such as depth estimation, semantic segmentation, and traffic light classification. Second, the attention mechanism to adaptively focus on salient parts in the input image to make driving decisions effectively. Our attention mechanism is realized in the encoder module that encodes an input image into two types of latent representations depending on the task to perform. We evaluate our approach with standard benchmarks available in Carla Simulator, and here we show some driving scenes. The agent only observes a single frame of RGB camera image shown on the top left. As a result, our approach records the best success rate in completing test episodes among previous similar approaches. Also, in terms of handling traffic lights, our approach is less likely to ignore a red traffic light at intersections during driving tests. Thank you for watching.
Okay. Yes, these were the first batch of talks. For our second poster session at 11:30, we will play the remaining ones. Now it's either break or social gathering in Gatherly. The link you can find on the CVPR homepage. So see you in Gatherly and enjoy a break from the talks.
Hello. Can you hear me okay?
Yes, everything is fine.
Great.
Yeah, we have another 10 minutes until it starts, but it's perfect that you're already here. Okay, and welcome back from the break. And I hope you enjoyed Gatherly and a bit of social interactions. And now it's a pleasure to introduce Carl Wellington. He is the Director of Autonomy at Aurora, where he is working on bringing Aurora's first product to the market. Carl, the stage is yours, and we are really looking forward to your talk. You're still muted. Let me. Okay, now, what happened?
Okay. All here? Sorry, I was trying to unmute, but it was not letting me. Got it. All right. Thank you. All right. Thanks for the intro. Yeah, I'm Carl Wellington. As you mentioned, I'm Director of Autonomy at Aurora. And today I'll be talking about bridging perception to motion planning. So at Aurora, we're building the Aurora driver, and our first product will be trucking. So trucking is a really great application for autonomy because we can split the problem into two parts by establishing hubs in major cities. And this allows human drivers to perform the complex city driving, as well as also stay close to home. And then allows us to focus on the long haul, the repetitive highway driving from hub to hub. And so today it takes almost 3 days for a truck to deliver goods from Dallas to Los Angeles, given the breaks that human drivers need. And we can bring this down to 24 hours. So there's a real benefit here. We're also pursuing ride hailing to bring the benefits of self-driving to cities and to people who want to get where they want to get. And there's strong overlap between these two use cases because a lot of the most important ride hailing trips are actually also involve a lot of highway driving. So we're really just building one Aurora driver to kind of support both of these two use cases. All right, so how does the system look? Well, it's like other self-driving systems. We have a perception system that takes sensor data and builds a representation. We have a motion planner that uses that representation to make decisions. And there's a lot of interesting work, including things we've already seen today. It's been already a great workshop, and I'm excited to see the things coming this afternoon on how to bring these things together. So given the speeds involved in driving, knowing just the locations of the actors is not enough. We need to know where they're going. So with that in mind, a common approach is to use actor forecasting. And so in this talk, I'm going to be talking about forecasting and some different ways to think about it within the system, and kind of both from sort of a left to right perspective, as well as then a right to left. So let's start left to right. One really interesting area is to view the kind of perception forecasting problem jointly as a single problem. And this is based on the pioneering work of Raquel Erderson in her lab. And they showed that by learning a joint perception forecasting model, we can both simplify the system and then also get more accurate forecasts. So I'd like to talk a little bit about some of the work that we've done in this area. Okay, so what does this look like? Here's kind of a typical setup. You've got a sequence of LiDAR sweeps coming in. You've got a map. You extract features from both of these. You bring them together and combine them to produce both detections and forecasts. And so you train this end to end. For the detection, you may use a standard focal loss. For forecasts, we could use a L1 regression loss on both the box size as well as its centers and orientations going forward to kind of get the forecasts, and then train this jointly end to end to get both detections and forecasts. So one of the areas that we've been looking at in this space is really thinking about how do we think about these forecasts in terms of multimodality and also thinking about uncertainty. So here's an actor highlighted. And if you look at this actor, we don't yet know where this actor is going to go, right? It may go straight, may make a turn. If we have a single mode forecasting system, kind of as shown on the left, then it's probably reasonable to produce just a go straight trajectory. But of course, we don't actually know. So we'd like to think about having multiple modes and then put probabilities on those in kind of a discrete probability sense. More than having the discrete probability, we also want to think about having a distribution over the actual motions that the vehicle might take for each of those. And so this is shown on the right. We kind of have these multimodal forecasts with both the sort of discrete probabilities on the modes as well as the continuous uncertainty distributions for the actual trajectories. And this is really important because if you're giving these forecasts to a motion planning system, being able to understand how certain you are with them about what the other actor is going to do, as well as about how they're going to actually move through space, is really important to be able to make good decisions. So how do we do this? Well, we can assume a Laplacian distribution over basically the long track and cross track errors of these forecasts. And so then instead of optimizing kind of an L1 loss, as we talked about before on the box centers, we can minimize the KL divergence between these along track and cross track errors with the distributions. And if we look at this and actually kind of look at the actual error distributions that these models produce, you can see that they're well calibrated. This means that we can actually trust these distributions. This is a good result because then the uncertainties that are being produced can be used by the motion planner to make good decisions. Okay. Another thing that is important is this. If we're thinking about trying to predict the future, we really want to make good velocity estimates. And of course, using a sequence of LiDAR data over time is part of this. But we want to bring in other sensor data as well. And so here we show bringing in basically radar information. And we can do the same thing, bring in radar information, do another feature extraction, bring it in, and do the same kind of end-to-end learning to make sure that the features that we're learning from each of these sensor modalities are actually supporting the core outputs of detection and forecasting. So here's some work we've presented last year, and just a couple examples of kind of some of the benefits that you get from bringing radar in. Here you see on the top, there's the highlighted actor, and based on just the bit of motion we've seen from the LiDAR data, there's still kind of these multiple modes of what the vehicle might be doing going forward. With the addition of the better velocity, direct velocity measurements from the radar, this actually induces an interesting mode collapse here, where it actually becomes much more certain that the vehicle is just pulling out and going forward, and then we can make the right decision based on that. Here's another example. It's a little hard to see here, but basically this actor highlighted on the left has just come out of occlusion. So this is sort of the first time you get LiDAR data on this actor. And so we get a detection right away, but on the left, we've only seen it once, so we really don't know what the forward motion is or velocities. Whereas, again, the nice thing about getting instantaneous radar velocities on this is that we can get accurate forecast of its future motion right away as soon as that actor comes out of occlusion. And of course, this is really important for actors that maybe kind of quick reveal cases to be able to get a motion as quickly as possible. All right. Another area that is related to this is to think about input representation. And this is something that our team spent a lot of time thinking about, because a lot of the approaches out there really start with kind of 3D LiDAR points as the first thing you start with. But of course, this is not what's actually happening, right? We don't have a drone that's flying up above us getting bird's eye LiDAR points that then we can start processing. The actual LiDAR data we get comes from basically a range sensor. We're getting range measurements, and we can choose to project those in the 3D world if we want. But it's the actual data we're receiving is this range information. Then, of course, you get this over time. So you have basically a sequence of range views. And you can kind of see how things move and change in terms of shape and size as things move through the world. Just as before, right, we want the same output. We want basically to have essentially a bird's eye output of detections as well as forecasts with uncertainties, just like before. But now we'd like to think about, well, could we use this raw input data and take this directly? And this is interesting because, of course, we've seen with a lot of end-to-end deep learning approaches in general that they can often perform better if you actually give it the raw data directly instead of kind of pre-processing certain things. So the range view has a number of benefits, right? One thing is it does avoid approximations that we often use, like voxelization or other ways of kind of putting the 3D data and getting it a little bit easier to process, because it actually processes every single LiDAR point. This is especially beneficial for pedestrians or other kind of small objects. There's also a lot of structure because the range view encapsulates how the data was actually captured. And so you get the relationships between, for example, which objects are occluding which other objects, or other scene structure that can be lost when you take this data and project it in a 3D view, especially if there's something occluding something much further away from it. And of course, as you see on the left, this is a really nice, dense input representation that is well suited to efficient convolutions and being kind of computationally efficient compared to kind of the sparse representation that we see on the right. Of course, there's also challenges, right? There's no consistent world frame in the range view. Everything is changing. It's like using images, right? Where objects not only are just moving around, but they're actually changing size, they're changing shape. And so a lot of our work, in references below, has focused on basically building network structures that encode the structure of the problem into the network and basically extracting features in each of these, the range view directly, but then warping views together to be able to combine these things temporally. And this gets really important when we think about long ranges, right? And so here we see that, on the right is a typical LiDAR sensor you get today, where you might have a 200-meter range. And so this is kind of looking at over a 400-meter by 400-meter square. And so the nice thing about operating the range view is that because you're doing a lot of the processing on the input space, which doesn't change based on range, you're almost, your computer is almost independent of the kind of range you want to do. And so this is really great when you want to do really big ranges like on the right, or of course, Aurora has its an internal LiDAR, which we call First Light, which has much longer ranges still, which is important for high-speed driving. And kind of operating in the range view supports these really high long distance ranges because it stays dense instead of the sparse representation as you see on the right. All right. One more advantage of thinking about things in the range view is it is very natural to combine with other range view sensors, such as cameras. And so here you see, again, an example where you have the range view, which we can extract the LiDAR features. We have a camera image, which we can also extract and do feature extraction directly in the camera view. Take those camera features, basically project them into the LiDAR points, and then send these along in just the same way. And so it's a very natural and easy way to kind of combine these two different types of sensor data. We can also put these together with the whole system, right? We have the existing approach that I've talked about up above, and now we can bring in these new range view, both in the LiDAR as well as the camera, do feature extraction in the native view of those sensors, do a projection into the bird's eye, and then combine these things again into one kind of unified model that brings all of these things together. And if you look at, again, there's some work reference there, but if you look at a few examples, you can see some highlighted actors here, and it really helps in areas that are kind of small or occluded regions. These are these areas that I think having the sort of direct range view or camera information helps, like this occluded vehicle gets a better detection, or in this middle case where the kind of our baseline only detects one of these two pedestrians, but there's actually two, or this small actor over on the right. And as we take this forward even more, we start thinking about sequences of both sequences in the range view as well as sequences in the bird's eye view, and how to put all of these together. And if you're interested in this, please attend the afternoon poster session where we have work being presented on this directly. And it's just a nice piece of work, so please check that out in this afternoon's poster session. Okay, so what does this look like overall? Here's a kind of typical urban setting. You kind of see how it all comes together. You get a bunch of different actors, you get these predictions for pedestrians, vehicles, bicycles, and these are then able to be brought into Motion Planner to be able to make good decisions. Okay, so now if we step back, what have we learned? First of all, learning forecasts end-to-end with these kind of multimodal output distributions and calibrated uncertainties. I think this we've shown some really strong results in some various papers referenced earlier in this. And also we've talked about the benefits of multiple views and multiple different sensing modalities. I think one really key point to take out of this part is that the features that you want on the sensors, on the sensor data, for understanding the motion of actors in velocities and these things are often quite different than the features that you want for detection. And so by training end-to-end, we improve our performance not just on the forecasts, but also on actor state information like velocity. And this is, I think, one of the really key points that I'll kind of come back to later. Okay, so this is great. We have this joint model, and we can pass in the decision maker. Of course, there's some problems with this. Here's a typical scene that we see all the time on the highway. And we're driving down the highway. We've got people merging in from the right, and we need to make a decision. We need to either hold our lane and kind of let the next actor kind of slide in behind us, or maybe we slow down and let that actor go in front of us. So we have this joint interaction, right? Where we need to make a decision. And of course, this other actor is observing what we're doing and then is making decisions based on that. And we have this kind of interesting joint interaction. Of course, all of us who've done highway merges know this can be quite complex sometimes. So let's think about applying the forecasting approach that we just discussed to this problem, right? We go out, we collect a bunch of data of good interactions by expert human drivers, and then we start letting the model learn, right? And the model is going to see that sometimes this actor to our right goes in front of us, kind of accelerates. Sometimes the actor to our right slows down. And so we have kind of this multimodal distribution there. Well, this is fine, right? We just talked about how these models actually handle multimodal distributions, handle uncertainty. They handle these quite well. So we can generate this and actually generate this multimodal forecast. But then what happens when this gets presented to the motion planner, right? And so if we kind of click this, we can play this forward and think about, well, we're going to generate these two kind of possible actions, right, that we've seen based on our data, these two forecasts, right? One that the actor slows down, one that it speeds up. So the challenge with this, of course, is that then when the motion planner looks at this, we kind of put the motion planner in a tough spot because when holding our lane doesn't look good because there's a good chance that this other actor is going to be there at the same time. Slowing down doesn't look good either because there's also a good chance from the forecast that the actor will be there. And so then one option it might take is actually to just hit the brakes hard and kind of protect against either of these things happening. And this is really unfortunate because actually either of those first options would have worked out well. And now it actually does something quite different because it doesn't have the right information to be able to make this decision. So of course, this is the well-known problem of just providing a marginal. And there's great work out looking at kind of actor interactions or graph structures, and even some work earlier today on this about how to kind of produce self-consistent forecasts. But the thing to remember here is that the AV is not a passive actor. It's not a passive observer here of the situation, trying to figure out what's going to happen, right? The real issue is that the data that was collected for these forecasts is all conditioned on what the other actor is doing when that data was collected, right? That's how that person made the decision about whether to accelerate or slow down, is conditioned on this. So why don't we embrace this, right? Why don't we just embrace this and shift things around and take this forecasting and say, okay, we're going to make these forecasts conditioned on the decisions of the AV. And so we can now split this apart into two cases. So in the top, right, the AV basically says, okay, we're going to slow down, let this actor in. In the bottom, we're going to hold our lane and let them slot in behind. And then based on those actions, we can again go and do our forecasting and see that actually both of these options result in good outcomes. And so by basically shifting the forecasting around from being kind of this forward pass to a conditional forecast based on our decisions, we can get the good outcome. And of course, you see this in practice, where here there's kind of a slot that looks a little too small for us initially, but then because we can condition and say, okay, if we establish our place here, we can forecast conditionally this other actor is going to move back, give us space, and slot in well. This isn't just for merging, of course, other things too. Here's a lane change. We have to move over due to construction. Again, and not enough space initially, but we can signal our intent with our turn signal and then know that reason about the fact that by doing that, we expect this other actor to move back, give us space, which allows us to successfully move over. Okay, so we've talked about forecasting a bit, but there is this broader thing about decisions. And although I won't talk deeply in here, I think we have to acknowledge that making these decisions is complex. And Aurora's approach here has been to learn these decisions from human driving data, right? And that one of the things that's really important about how to think about this is that driving in a predictable human-like way is very important for safe driving. So here we show some cut-ins, finding an interesting slot. And on the bottom right, a case where we actually take these learned models and then wrap them in a kind of verified safety guardrail so that in this case, when the light turns green, we start to go, there's a red light runner, we can still react appropriately. Okay, so now we've shown that the benefits and how important it is to kind of do the conditional forecasting within the motion planner. Okay, well now what do we do, right? We've talked about the benefits of forecasting as part of perception. We've also talked about how important it is to do this part of decision making. And this is, of course, the great interesting thing about this problem, right? And we've already seen some really interesting approaches earlier today. I expect we'll see more this afternoon. And there's sort of a ton of interesting work in this area of how to think about bringing all these things together. So one way we've been looking at is to focus on actor goals. And just to set up this problem, we have a case here where, again, typical case driving down the highway. We're just driving right along, following behind this pickup truck. And if I just move it forward one step, we see that basically the actor motions haven't really changed. Everyone's continuing to do just what they did before. But now there's a few extra pixels in this image lit up, which is showing that this white car now has their turn signal on. And this, of course, changes everything, right? Because now we know that this actor wants to get over. We don't know when, we don't even know exactly how. Maybe they're just moving over when it's convenient. Maybe this is their exit and they're going to move over right away. But we can, again, start making these decisions and start doing this conditional forecasting interactions based on this actor because we know where it's trying to go. And as we try to formulate this kind of goal problem, here's another work we presented last year, thinking about goals relative to map geometry. And so here you think about that we have maps, and so the vehicles tend to follow the lanes in the map. Even pedestrians, right, are either generally following pedestrian areas or perhaps trying to get from one pedestrian area, like one sidewalk, to another sidewalk. And so there's a way to kind of reason pretty directly from the map geometry and kind of propose this problem in the context of the map geometry and get a natural generalization to new scenes, even if it's a complicated geometry that we've never seen before. If we look at what this looks like in practice, here's a couple examples of kind of ground truth of what actually happens, and then this goals being generated. And you see on the left case, lots of different options, and lots of different options are open, right? And so we kind of really generate this multimodal distribution over these different possibilities. The second option here is a little different because given the velocity of the vehicle, it's extremely unlikely this vehicle is now making a right. So we can actually use the motion of the actor to know that the goal is to go forward and reason about that. And of course, whenever using a map-based approach, you always want to have a fallback that says, like, if this actor doesn't match any of these goals, there's probably a different goal this has that isn't represented by the map, and being able to highlight that one if it doesn't match what the map says. Okay, so that's kind of in the vehicle side. Then there's this really interesting case that's, of course, so important in self-driving when you're looking at a pedestrian and trying to figure out whether they're going to cross or not. So at the top bar here, this t equals 0 space, here's an actor that's on the side of the road with no velocity. So if you give this and need to make a decision from motion planning side, just based on the state, here's an actor on the sidewalk with no velocity. It's pretty hard to know that this actor is someone that's going to interact with us and that we need to start reasoning in that way about. So here we show some results of a model that's basically trained directly on sensor data to predict these crossing goals, and it's combined with the geometrical reasoning we just from the map that we talked about just earlier. And so using these visual features, as you can see here, there are these indications that this actor is about to move even though they haven't really started moving yet. And so you can see in the top row that there's this red part about that there is a starting to get a crossing goal, even though the person hasn't moved yet. Of course, we don't know exactly how they're going to cross or when they're going to cross, but we know that they can start reasoning about this, start having these interactions, start doing this conditional reasoning. And then, of course, as the actor continues to move, the probabilities move around and show even a more certainty around the fact that this is their goal to cross. So one thing that's important here too is that there's lots of different ways to possibly recognize about gaze or other aspects of this. But the really important thing is whether they're going to try to cross or not. So you can think about this goal almost like the turn signal state up ahead, where it's like signaling a goal, signaling intent, and having to learn this directly from sensor data in kind of an end-to-end way. Okay, so where did we end up? As I mentioned earlier, there's lots of different ways to think about this problem, and that's what makes this so interesting. One way that we can kind of put together a couple of the different themes that I've been talking about today is to think about there being a forward reasoning pass. And this can really benefit from a lot of the advantages that we talked about in the first part, right? So this is generating actors and actor goals and trying to really use this end-to-end training from temporal sensor sequences all the way into the future, gaining the benefits of better state estimates from doing that, as well as learned uncertainties, but then bringing in this idea of these goals and understanding where are these actors trying to get. The key thing here then, the difference, is to not, at this point, try to forecast the exact spatiotemporal path, right? We know that this actor is trying to cross, we know this actor is trying to get over, we don't know exactly how or when they're going to do that. That part's going to be done over on the conditional, on this part on the right, where we can do conditional forecasting based on our decisions, potential decisions, and look at that jointly, because that really depends, the actual end-up motion of this actor really depends on our own actions. So we have this kind of forward reasoning pass that have stuff that's independent of the AV, and then we have this interleaved reasoning part that reasons about other actors in the context of the AV's decisions. So, of course, one thing you might ask is, well, wait, why split here at all, right? Why have any split? Why don't we just do these end-to-end? And I do think that there are really compelling reasons to think about doing end-to-end training, right? All the same reasons about reasoning about the future has better kind of sensor feature extraction. Thinking about what's actually needed all the way to the end is really important here too. And there was some great work on this earlier today. One reason you may want to be thinking this way is at Aurora, we think a lot about verification. And when we're doing verification, we want to test against cases that we've seen, and of course, many cases that we've never seen. And so you could build a full sensor simulator and simulate everything kind of from the raw data. And we do this, but the parts on the left here in that forward reasoning stage are often the really computationally expensive part. So if you think about kind of having a fixed budget for your cloud spend, it can be more effective to think about, yep, doing some simulations directly from log or sensor simulations, but then doing a huge number on this interleaved reasoning part, on the motion planning, on the conditional forecasting part, where you're able to put in the parts of the problem that are not dependent on the AV and really focus on these complicated interactions. And so this is one way that we've been kind of going about thinking about this problem, both for terms of how you set it up, as well as how you verify it. With that, I'll stop and just mention again, it's so interesting to be in this space and see all the different stuff. I've been already learning a lot of things from this morning, and can't wait till the sessions this afternoon. Thank you.
Thanks a lot. I actually have one question from my side. You said you kind of link the forecasting and the decision making. Did you ever look into game theory for this kind of the linked decision making? Yeah, absolutely. And I didn't use those words, but I think the whole way of thinking about kind of the setup that we had at the beginning, where we're doing the merges, it really is exactly that, right? It's basically a two-player game, and you think about that there's two good outcomes where AV goes in front and the other actor slots in behind, or vice versa, and those are both good outcomes. And then there's two bad outcomes that have the negative cost. And so you kind of exactly formulate these things as a game. And I think one of the things that trying to get across here is, as we're going through and reasoning about the whole environment, we're processing in a very feed-forward way all the sensor data on basically all the actors. We need to know where all the actors are, where they are, what their state is. And we can actually do reasoning in that stage of trying to understand, in terms of kind of the intent or the goals of these actors, to better be able to understand which of those actors do we need to be basically playing a game with. Is this a game that I'm playing is this an actor that I'm playing a game with?
Or is this an actor that's moving independently and I don't need to reason about the kind of interactions? And this is sort of an important way of thinking about it in terms of being able to figure out which ones to do the full kind of game theory approach on.
Yeah, completely agree. It's a game theory just doesn't scale often. So very important question, kind of thing to answer. So yeah, I think the time is up, and really enjoyed your talk. Is the next speaker already here? Yeah, perfect. I see Sarah already. Okay.
Hi.
Good. Then, yeah, with Sarah already in the spotlight, it's a pleasure to introduce her. So Sarah Taraki is the VP of Autonomous Driving Software at NVIDIA, where she leads, basically the whole AV, the development of the whole AV platform in looking into a wide range of topics from perception, localization, mapping, down to planning. I'm really looking forward to your talk. The stage is yours.
Thank you so much, Yuning. You can see my slides?
Yes.
Awesome. Well, thank you for the introduction. Super excited to be here. It was already a very exciting morning. Thanks, Carl, for your talk. And let me get started. So today I'm going to be talking about some of the challenges and solutions for deploying AV as a platform at an enormous scale. There's many interesting challenges when you encounter as you start thinking about how to deploy a hardware or software solution that has to scale across many different use cases, from active safety all the way to L4. It has to scale across different types of vehicles, from consumer vehicles to trucks, buses, robotaxis, and even specialized vehicles like tractors. You have to scale across different manufacturers, and you have to scale all over the world. So that really is the focus of my talk. How do you think about, reason about scaling like this, and how do you deal with the complexity there? So in the next half hour, I'll talk about some of these interesting challenges, some of the solutions that we see, and I'll wrap up a little bit by talking about the central role of simulation in training, testing, and validation. So developing a robust AV solution requires dealing with several different pieces, from data acquisition, model training, to deployment and testing. And all of these are areas that we're heavily invested in and providing solutions for. The thing that I find most exciting and challenging here is all of this needs to operate at this massive scale. So as an example, NVIDIA announced a partnership with Mercedes last year to build the world's leading platform for AV functionality in consumer cars. So starting in 2024, every next generation Mercedes vehicle will include this architecture, the NVIDIA hardware, software, and AI to be able to autonomously drive. And this functionality includes very basic active safety functionality, but then it also sort of includes driving autonomously from address to address on regular routes. It includes level 4 parking, many other things. And all of this capability has to keep improving over the life of the vehicle. We're developing this technology with Mercedes, but really this is an open platform that's available to other partners as well. So now when you start thinking about the scale of this, right, we're enabling large amounts of AV functionality from active safety all the way up to level 4 on millions of consumer cars, on multiple vendors all over the world. What are the sorts of challenges that you would face? Let's talk about those. So I'll start off by talking about all the functionality you need to develop here. So the very basic stuff, which is available in most cars, is active safety. So this is functionality like automatic braking and steering assist, it's lane keeping, blind spot monitoring, and so on. Next, you have level 2+ driving. So for example, address to address urban driving, where you have features that are either fully automated or they require human confirmation. These features include things like intersection handling. You have level 3 driving on highways, where the vehicle is responsible for detecting the ODD, detecting and reacting safely to all issues without requiring immediate handover to the driver. And then you have complex level 4 driving, where the vehicle not only parks or unparks, but can be summoned from a parking spot. It can have a trailer attached. You need to deal with that as well. And all of this functionality needs to be supported with a single stack, a single perception, planning, prediction stack. And that's what makes it challenging. Car manufacturers have been doing lane keeping, automatic emergency braking, for example, forever. But yet those have been done with very simple perception and planning. But when you want to run this functionality along with more complex urban driving, you want to leverage the same stack for all of this. Next, we have geography. Our partner vehicles will be sold in over 100 countries all over the world. how do you figure out what is the mix of real world data that you should gather in each of these areas for both training and validation? Which areas are similar enough so that you can leverage data collected between them, and which are more diverse and require targeted data collection? The diversity in the world comes from all sorts of different factors, from layouts of cities to the appearance of cars and other objects like traffic signs, to the rules of the road and even the behavior of the people inside them. Tackling this problem requires thinking smartly about how best to utilize your limited resources for data collection and labeling, and then how to leverage simulation. I'll talk a little bit about both these topics in this talk. Another thing we need to consider is this software and this hardware architecture have to scale to drastically different compute requirements. So you need to support everything from small ADAS computers that are only 10 TOPS and 6 watts, all the way to full self-driving that requires more than 2000 TOPS. You want to be able to leverage your hardware and software architecture as much as possible between all of these vehicles, because otherwise you end up having to maintain several different architectures and stacks, and that becomes very expensive. Similar to the compute and software stack, we also want to define a common sensor stack for all vehicles, and that has to be capable of scaling to different ODDs and different capabilities. So for example, here we have the level 2 and level 3 sensor configurations that we're using, and both of them have cameras, radar, ultrasonics mounted all over the car, and they're very, very similar. But then the L3 version of the sensor stack has to have some extra capability. So for example, it has more forward sensing capability using stereo vision and LiDAR in order to deal with things like debris at high speeds. Having a common sensor stack means having the same sensors in roughly the same locations for all partners that are using this platform. On the development side, that helps us validate our algorithms once, build and validate them once, and deploy across everyone. It also helps leverage common work like sensor tuning, ISP tuning, drivers, and so forth. So we're building this platform to enable all the different partners that we have, but we want to minimize the amount of work that it takes to enable every partner. I already talked about having a common compute stack and sensor stack, but there's much more. You also need to have a common vehicle abstraction layer. So basically an abstraction between our software and the manufacturer low-level software that does controls. We develop our common stack on a reference of fleet vehicles that encompass different types of vehicles like a coupe, a sedan, an SUV, and so forth. We test our software on these reference vehicles in both simulation and the real world. And then every additional manufacturer vehicle that comes up, we first test it in simulation using a vehicle dynamics model that the manufacturer provides, and then we test it on road. And that really minimizes the amount of vendor-specific testing that needs to go in. So I've been talking about how to create a common set of advanced AV functionality for all car manufacturers, but you still want different car manufacturers to have the ability to customize their cars and make them unique. There's several ways that you can make this happen, from visualization changes to changes in how the HMI works, all the way to how the car feels when driving. The feeling of driving a Mercedes, for example, is very different from driving a Mustang. The interesting challenge here is that you want to write a common control stack for deploying on many different types of vehicles and manufacturers, and to enable this change of the feel of the vehicle from something smooth to something sporty with just changing some knobs or parameters. And of course, all this functionality has to be enabled inside constraints. Consumer cars, for example, have very tight constraints on the amount of space, the power, the thermal budget, and the cost. And all of this functionality running on all of this constrained architecture needs a lot of compute, right? So there's a lot of things that we need to be doing in order to enable everything from active safety to something like level 4 parking. Here's just some examples of the types of networks that we're running. So for example, we have to do very simple, just basic object detection in cameras and LiDAR and radar using DNNs. But then there's more complex stuff. You need to estimate distance to things. You need to estimate what are your paths, especially when there's no maps. Figure out what are intersections. You need to understand what the human inside the car is doing so that you can monitor whether they're distracted or not. You need to find parking spots and many other things. And that's just on perception. You still have the planning and control stack that needs to do, again, very simple stuff like ACC and lane keep, lane assist, but it also needs to do much more complex stuff like intersection handling, dealing with very congested traffic, and so forth. So a lot of advanced planning maneuvers, some of what I talked about, require HD maps, and that's a vital component for self-driving technology. You can do some things without a map, but much more functionality is enabled once you have a map. So for example, you know precisely where you are on the road, which lane you're in, how to navigate an intersection, and so forth. And HD maps are something that the level 4 robotaxi community, for example, just takes for granted. However, when you're launching a product on consumer vehicles all over the world, you can't guarantee HD maps everywhere. And in addition, there are several areas where survey cars can't even go, like private driveways and parking lots. So how do you get around this problem? At NVIDIA, we have a concept of my route maps. So basically, as a commuter, there are some routes that you travel frequently, like your daily commute, or your school carpool route, or your drive to Whole Foods. And we generate personalized maps for you on these routes. By running perception landmark detection in real time on your drives, we can generate a map automatically, fuse it with previous drives on the same roads, and automatically generate a high quality HD map that then we can use to enable extra functionality. With user consent, we can also transmit this map to the server, aggregate user data, and share that map with the entire fleet. So that shortly after the launch of a new vehicle in an area, you can start to generate automatic crowdsourced maps for these locations. And this same process can then also be used to keep the map fresh. We can dynamically update a map when any vehicle in an OEM fleet drives the same route and it has changed. So let me show you a little bit of how this works. On any given drive, we use perception semantic output and ego motion to create a version of the map. It's called the map stream here. Map streams contain information like the lane and road boundaries, signs, traffic lights, road markings, radar data, so forth. Streams from multiple map streams can be registered, fused together, and then we create a final map that you drive on. So here's just a very basic drive. We're driving this route for the first time. We're generating all of this data that can be useful in a map and for localization. So for example, we've got ladder lane lines, road boundaries, we've got traffic signs up ahead, we've got poles, vertical geometry. And then if you fuse together multiple of these, you get an automatically generated map. And so you can see here all of the semantics. You know, it's a very consistent lane boundaries, road geometry. There are lanes that are not complete because we never drove there, but for the most part, you can see there's a lot of useful data. And then there's also this radar data that you can use for localization. So here's a video of showing the quality of that map that is generated and the quality of the localization. We're driving a route that we created automatically, and then we're reprojecting these map elements that I talked about, like signs and lane boundaries, back into the image here. And then here we have we have a route that we generated a map for automatically, and we can enable autonomous driving functionality on that map. Okay, so let's switch topics a bit and talk about data. When we're driving at a massive scale all over the world, we're regularly dealing with petabytes of data. How do we utilize this data to best train our networks? Ideally, we want to pick images that would best help train our networks. And what we want to do is pick images where the networks are the most uncertain. And this uncertainty can occur because of many reasons like noise in observations, incomplete coverage of the domain, or imperfect models. The accuracy of a network is not the same as uncertainty. You have to have an accurate output. You can have an accurate output, but with a large amount of uncertainty. So how do you predict the uncertainty of a sample? I'll cover one technique, and there's so many ways of doing this. But basically, you need to have some way. Otherwise, you're going to be left with massive amounts of data and no good way of curating it. So if you're looking for the uncertainty of a sample, Bayesian networks are a very principled way of modeling it, but they're expensive. The cheaper way to model uncertainty is to use an ensemble of networks. So the basic idea is really simple. You can train an ensemble of networks, for example, using different seeds, and we can sample from their output and quantify the uncertainty of the model on new unlabeled samples. And we basically label the samples where the model has the most uncertainty. This framework is pretty straightforward for a classification task, but how do we generalize it to detection? So basically, to extend this approach to detection, you can partition the image into cells and then use the disagreement of the output of the ensemble at each cell in order to measure the uncertainty. You can visualize this as a heat map. So here, for example, we've got this image. Here's a trailer that we haven't seen a lot of before, pretty uncertain about it. And when you plot the uncertainty here, there's pretty high high uncertainty. And the idea would be you sample images where you have such examples of uncertainty. Okay, so I want to switch gears a little bit again and talk about simulation. Simulation helps us support the entire development and validation process from start to finish. This includes perception development, planning and control development and testing, full AV stack validation, integration testing, and full virtual vehicle testing. So for example, for testing human-machine interface. The benefit of simulation is that we can test all sorts of scenarios from all sorts of lighting and weather to scene setup, traffic patterns, to the long tail of appearance and events. And just as importantly, the ground truth is free. We know all the attributes of the world around us, from the exact 3D envelopes of each object to their velocities, their trajectories, and the semantics of everything in the world. We use simulation across several different use cases, but in the rest of my talk, I'll focus on the use case of end-to-end simulation and synthetic data generation for perception. Training and testing in simulation is hard for several reasons. You need simulation to accurately reflect the world we're trying to replicate, from sensors to the content to the behavior of other actors. We need simulation to be reproducible, and we need it to be able to run reasonably fast, ideally interactively. I'm not going to talk about all of these challenges, but let's talk about a couple. So let me show you what this looks like on our side. In order to close the content and appearance gap, the first thing we do is look at the quality of a renderer. So here I'm showing the results of rendering with our renderer. And this is the easiest way of closing this gap. We basically model the appearance of the world as realistically as possible. Instead of relying on a game engine with a renderer that has approximations, we model light transport with ray tracing and material properties in a physically accurate way. As a result, the image quality is absolutely unsurpassed compared to any other synthetic data approaches. And this sort of approach is applicable not just to cameras, but to all the sensors that we're rendering. Basically, LiDAR, radar, camera, for all of them, we need to be able to match the physics of the world, the light transport or the transport of radar frequency, and we need to be able to match the surfaces and the materials in a physically realistic way. Omniverse, the renderer that we're using here, supports fast real-time rendering as well as a physically accurate path trace mode. During runtime, we will typically use the faster real-time mode, but synthetic data generation can make use of either the RTX renderer or a full path trace mode. So that's one way of closing the gap on appearance, but there's other ways as well. So you can use domain randomization and many other techniques. So here's an example of just sort of creating a simulated scene and then randomizing it with much more synthetic data. So for example, we can augment it with scene lighting, fog, image saturation, bloom effects, and so forth. I mentioned at the beginning of the talk that AVs need to be deployed all over the world. An important component of the testing we need to do then is to validate our stack and run in all these unique environments. It starts with needing to have a really good map. Maps are an important component for realistic generation of scenarios for testing. For example, complex many-way intersections that we might see in the real world. They're also important for creating the proper context for perception. So for example, when you have occlusions due to road curvature. Map data and simulation can come from maps that we are creating from the real world on our vehicles. So for example, I talked about how we're creating these MyRoute maps. You can then import any such map directly into simulation, or you can build it from aerial or scanned map data, and this data can be imported. Or you can even generate this map data completely procedurally. So for example, we can have generative models that create realistic road layouts, and even more, we can make them conditional. So you can create a synthetic hybrid testing environment where part of the scene looks like Cambridge, another part looks like New York. This can be framed as a graph generation problem. So I'll say there's much more work on this. I'm talking about one specific area that colleagues are looking at NVIDIA. So when you're framing it as a graph generation problem, you're basically saying the nodes are the control points on the roads, and straight road segments connect nodes. And then you're generating this graph using a RNN but with attributes. So control points need to have things like the XY location of where they are in the city. So let's show a quick example of how this works. So here we're conditioning on different cities, and you can learn the style of how cities are laid out. And that's pretty authentic when you compare it to real OpenStreetMap data. You can also create a map where you have certain road elements that you anchor basically, and then you generate the rest of the map around it. And you can use this sort of technique for parsing aerial imaging so that you can use this as a prior for estimating world geometry. And then once you've got these maps that you've generated either from aerial images or completely procedurally, you can start procedurally generating many more things like vegetation and buildings and other elements and so forth, in order to have maps now that are reflecting the sorts of conditions that we want to be testing, like testing in India or testing in Japan, even without having gone there. So I just talked about testing in different parts of the world. And in order to enable something like that, right? Like how do I test that my algorithm is going to work equally well in India or Japan if I'm only driving my vehicles today in like some part of the US? And some part of the story is the maps, but an equally other important part is having the right objects to place in our scenes. So 3D objects, 3D assets are expensive and time consuming, and we're going to hinder our ability to train and test our software stack all over the world, for example, or in very different conditions, if we are overfitting to these very few assets that we have access to. There's been a lot of work on creating assets directly from images, and I think this is a really exciting area of research. So basically, if we can go from an image to a 3D model, we can replicate all the diversity we would see in the real world, which can be captured with just a specific sensor from just any sensor. For example, you can capture all of this diversity from a dash cam, or you can capture it from somebody's iPhone. You don't need to have your specific sensor set on your vehicles driving in the world. So you can now test, for example, the diversity of cars, trucks, and rickshaws in India just by getting consumer photos and creating assets that you then populate into your simulation. So how would you go about doing something like this? In graphics, we know that images are formed by the interaction of geometry and light. So you have a mesh and lights and materials input to a renderer that then generates an output image. There's been a lot of work on making these renderers differentiable. And with that, suddenly this whole rendering pipeline becomes amenable to deep learning. So you can have an input image or a set of images that goes through some neural network that's going to predict these graphics parameters. And now through the renderer, you can produce a rendered image. And you can create a loss between that rendered image and your actual input image. With a differentiable renderer, you can then backprop gradients directly and train this whole stack. Idea being, right, like I have my image from a dash cam of a car in India, and I want to be able to create 3D assets that accurately model this. So this almost works, but I'm going to gloss over some much more, more involved details here. Basically, if you train something like this, you need additional complexity in order to get good results, because you need to be able to have multi-view geometry, right? You need to be able to have images of the same object from multiple angles. And this sort of defeats our initial premise, because I wanted to create 3D reconstructions from uncontrolled input data, for example, a dash cam or someone's iPhone. In order to solve this problem, you can exploit GANs as a multi-view generator. I'm not going to talk about the details, but they are in the paper that is linked here. But basically, the result of this is pretty impressive, right? Like you can go from input images on the left to synthesize data on the right. The 3D geometry we're rendering here from both the same view as the input image, but from many other views. The implications are basically that you can create 3D data to easily replicate scenes that you've captured with your own sensor stack, and then recreate, for example, scenes that your AV stack had trouble with in the past, and recreate them entirely in simulation so that you can test in closed loop improvements that you're making, either in your perception or planning and so forth. Even more excitingly, you can create representative 3D content for regions where you don't have any data, just by using cheap consumer content from any off-the-shelf device like a dash cam or a phone. Like I mentioned, simulation is useful not just for testing and validation, but we also use it for quickly bringing up a new sensor or algorithm before we have any on-vehicle time. A network trained on just simulated data is not going to do that well in the real world. but it is a huge advantage to be able to train and create a whole pipeline in simulation in advance of when real data becomes available. As real data starts to come in, you can then balance the amount of data that you're using from simulation versus the real world. So as an example, we recently brought up new fisheye cameras from our sensor set, and we wanted to test out using these cameras for parking. Before we had any vehicles with fisheye cameras mounted, we were able to train and test our parking end-to-end with object detection running on our simulator, and with the object detector trained entirely on synthetic fisheye lens camera data. As soon as we had a vehicle with sensors integrated, we were then able to immediately start testing our end-to-end parking system, while in parallel, we start gathering data to train better networks. This ability to train and test entirely in simulation means you significantly cut down on the time it takes to bring up new end-to-end functionality. And then, even when you have enough real-world data, you can still use simulation to generate data for specific failure cases. So for example, here's an example of a network that was having trouble detecting truncated large trucks that were very close to us. So one way of solving for this easily is you find this failure event, you generate massive amounts of similar data in simulation, you retrain with some of this data added in, and you solve your problem. Let me wrap up by showing you a pretty cool video that we recently showed. This video is the result of our collaboration with Mercedes. It's pretty early results, just took us a couple of months. And it shows the development flow that lets you first develop AV software in a physically accurate simulator that is essentially identical to a real car. In this video, you'll see that we've modeled a Mercedes-Benz EQS to be true to life. It has accurate vehicle shape and dimensions, true to life vehicle dynamics, and includes even life vehicle tires. And we've modeled the sensors accurately, and we're running the entire AV stack on an entire compute architecture that is identical to what we have in the car, but running on the cloud. After building this digital twin, we're able to simulate the AV software running on this vehicle, and we can run different types of traffic simulation and weather conditions and so forth. We really see the simulation-based testing as a key to validating the safety and functionality and performance of fleets of different vehicles at scale all over the world. So what you're seeing here is rendered in real time, and it's showing not just the rendering of all of our sensor stack, but it's showing all of the AV stack that is running on the sensor stack together in lockstep in real time. This is just some of the sensors that we're rendering in real time just for the cameras. Okay, and that ends my talk. I'm super excited about the revolution in autonomous driving and its positive implications on safety and quality of life for people all over the world. The scale of this revolution is massive, and I hope I got you excited about some of the challenges and thinking about some of the solutions for developing and deploying at this sort of scale. Thank you.
Thanks a lot, Sarah. I think we have time for one question. We have a question. This is a question from our Zoom channel and the map part. So how do you measure the performance improvement on your model when using synthetic and then kind of, synthetic meaning potentially fake generated maps?
Yeah, that's a good question. So with all synthetic data, what we're trying to figure out is it giving us useful information about what are the sorts of issues we will encounter in the real world? And is it helping us find maybe long tail events and so forth? So the sort of idea that I'm giving about synthetic generated maps is it helps you figure out what sorts of problems you might encounter that you haven't seen even driving in the real world. So performance of the model is sort of measured on this, might not reflect in real world driving because I'm not even driving at that sort of scale. It takes me to this important point, right? Like you need to be able to have these KPIs that you can compare in real world and in simulation, where simulation is sort of like encompassing some parts that you might not even see. When KPIs are improving in both of them, you're doing the right thing.
Yeah, thanks. That was a very clear answer. Yeah, unfortunately, time is very tight. So it was great to have you here. And I hope you also enjoyed the rest of the workshop. So now it's time to switch over to our second spotlight session. Tuning, can you maybe show your screen again that we can now watch the remaining spotlight videos of our paper track?
Hello, everyone. I'm Yizhou from the University of Washington. I'm glad to present our work, Rethinking of Radars Role, a camera radar dataset and systematic annotator via cognitive alignment in workshop on autonomous driving at CVPR 2021. The co-authors also include Dr. Wang, Dr. Xu, Dr. Liu, and Dr. Huang. To talk about the radar's role for autonomous driving, traditionally, radar is usually used for obstacle ranging and speed estimation, often the robust sensoring and supplementary sensor for camera, LiDAR, etc. However, in this work, we are trying to use radar as a primary sensor to achieve more complicated tasks independently, like object detection and object tracking. It is very important to make it work when other sensors are not reliable in adverse driving scenarios. So in this paper, we used radar object detection, ROD, as an example to show our pipeline. The detector used radar data as the only input to do the object detection, and the proposed annotator takes both camera and radar data as the input to generate annotations by detection alignment between the camera and radar. Finally, a score with the series of evaluation metrics is appended to compare the detection results with the ground truth. We collect a dataset named CREW containing a synchronized and well-calibrated camera and radar sensor system. It includes about 3 hours of 30 FPS data. Most importantly, the format of our radar data is radio frequency image. Unlike the radar points, this kind of data format contains richer information like object location, shape, surface texture, speed, etc. This information is very useful to achieve radar object detection. We also host a challenge called ROD 2021 based on our CREW dataset at ACM ICMR 2021. It shows that our problem is very attractive to the community. Thanks for listening, and if you have any questions, please drop by our poster session. Thank you.
Hello everyone, I'm Shivam Gautam and I work within the perception team at Aurora. I'm going to present an end-to-end method for joint perception and motion forecasting, MVFuseNet. This work has been done in collaboration with Ankit, Stefan, Shreyas, and Carlos. Our model does end-to-end detection and forecasting by taking in a time series of LiDAR sweeps. This is followed by multi-view processing in the range view and the bird's eye view. The final output is a bounding box for each actor along with its predicted future trajectory. The natural question that arises is, why do we need this multi-view fusion? The reason is that each viewpoint has its own advantages. Range view methods are computationally efficient and scale well to longer ranges, which makes them suitable for real-time autonomous driving applications. Bird's eye view methods, on the other hand, generally perform better than range view methods on detection and forecasting performance, at the cost of increased runtime. So this is where MVFuseNet steps in. We leverage both viewpoints and combine their advantages in a single network. First, we perform temporal fusion in both the range view and the bird's eye view. This is followed by fusing these multi-view spatiotemporal features in a backbone network that extracts multi-view, multi-scale features and predicts bounding boxes along with future trajectories. We show that using multi-view in both parts of the network is key for best performance. As a result, we improve on the current state of the art for joint detection and forecasting. Our method improves over the next best method by 15% on motion forecasting and about 10% on detection performance. The method is also computationally efficient and scalable to long ranges. We are 38% faster than the next best bird's eye view method and 8% faster than the best range view only method. That's all from our side. Please come check out our poster for further questions and discussions. Thank you.
Hello to you all, I'm Francesco Barpato from University of Padova, and I will present our work, latent space regularization for unsupervised domain adaptation in semantic segmentation. We focus on this task because deep convolutional neural networks don't generalize well and require huge amounts of data for training. This is a very big problem for semantic segmentation, given the expensive labeling procedure, which can take up to 2.5 hours per sample. Unsupervised domain adaptation allows to tackle both problems simultaneously. It enables a network trained on a source dataset to be adapted to a target domain using exclusively unlabeled samples, whose acquisition is as trivial as setting up a dashcam on a car. In our experiments, the source dataset was synthetic, while the target one was real. Our approach is based on encoder-decoder latent space shaping. Particularly, we introduce three mutually beneficial objectives. The first is class discriminative clustering, which aids both in the estimation of the prototypes and also in the domain alignment between source and target feature vectors. The second is prototype perpendicularity, which forces the prototype to have disjoint activations and, given our estimation strategy, its effects are automatically transferred to the cluster that generated each of the prototypes. The third objective is feature norm alignment. We argue that more common classes have higher norms in the feature space, and therefore can overshadow the activation of rarer classes. To avoid this issue, we force all vector norms to have the same value regardless of the final classification. A final note about our strategy is that it is end-to-end and can be seamlessly employed together with other strategies. To prove this, we included in our testing an additional entropy minimization loss. To conclude, in our work we focused on unsupervised domain adaptation at feature level, introducing three novel objectives that were able to surpass previous state-of-the-art approaches in common synthetic real autonomous driving benchmarks. Additional information can be found in the paper website, and we hope to see you during our poster session. Thank you for your attention.
Welcome to our talk, Soft Cross-Entropy Loss and Bottleneck Tri-Cost Volume for Efficient Stereo Depth Prediction. We offer two main contributions. First, we introduce our bottleneck tri-cost volume, which has performance comparable to a 64-channel concatenation cost volume, while reducing runtime on PSMNet by over 20%. Second, we demonstrate soft encoding for cross-entropy loss outperforms super-regression loss by 10% on PSMNet. We use a standard stereo network architecture for disparity prediction, with a Siamese feature extractor, a cost volume, and a cost aggregation stage. These networks typically output 3D tensors of dimensionality, disparity, height, and width. A softmax taken over the disparity dimension produces a probability distribution, and the expected value over this distribution yields the predicted disparity. Cost volumes are almost ubiquitous in state-of-the-art solutions. Many papers use concatenation, grouping, or single costs, Our investigation demonstrates that the sum of absolute differences with two reference features has performance similar to concatenation cost volumes and speed similar to single-channel cost volumes. Our second contribution focuses on improving the loss function. All distributions shown have an expected value of 0.4 pixels. However, only one encoding is the minimum variance unbiased distribution, which we term the soft encoding. Instead of training to learn the correct expected value via regression loss, we propose training to learn the probability distribution directly via cross-entropy loss. We perform an ablation study on PSMNet to evaluate the bottleneck tri-cost volume and the soft cross-entropy loss. The bottleneck tri-cost volume is more efficient and maintains performance, while the soft cross-entropy loss results in lower error rates in our experiments. Here's a visual comparison between PSMNet trained with a 64-channel concatenation cost volume and Huber regression loss against the bottleneck tri-cost volume and soft cross-entropy loss, which results in a lower error rate. Thank you for coming to our talk.
In this work, we present a deep neural network which can estimate the scene flow on 3D point cloud and their occlusions. Scene flow estimation is one of the core challenges in computer vision, which aims to find the 3D motion field between two consecutive time frames. Traditionally, it was usually performed on the stereo image, but in recent years, many work suggest to directly estimate the scene flow on 3D point clouds. We always encounter the issues of occlusion, where some regions in one of the frames does not exist in the other. They provide misleading information which can reduce the accuracy of the scene flow estimation. In this work, we present a deep neural network which directly consumes the source and target point cloud and estimate both of the scene flow and occlusion map. In addition, we utilize an occlusion guidance mechanism inside our cost volume layers, where the predicted occluded regions are being excluded during the correlation construction. This design can give us a better connection between the two estimation tasks and improve the performance significantly. By purely trained on synthetic data, our model can easily generalize on real scans from Kitty. We can obtain an accurate prediction of both of the scene flow and occlusion. Tested on both Flying Sim 3D and Kitty dataset, our model achieves the best performance on all kinds of evaluation metrics. To summarize, we present a deep neural network which can estimate both of the scene flow and occlusions from the point cloud. We utilize an occlusion handling mechanism inside our cost volume layer, which can improve the performance under the occluded scene. Our model achieved the state-of-the-art performance on Flying Sim 3D and Kitty dataset. We invite you to read our paper in order to have more details of our design. Thank you.
Okay, so thanks for listening to all our spotlight talks. And now you can go to Gatherly, to our autonomous driving poster floor, and have a chat with the, with all the authors or with other peers. And the workshop or the talks will continue at 12:15. With a talk by Vladlen Klotun. Okay, see you then. And in Gatherly. Hello and welcome back from the lunch break and Gatherly poster session. And let me introduce our next speaker. Our next speaker is Vladlen Colton. He is the Chief Scientist for Intelligent System at Intel, where he directs the Intelligent System Lab. Vladlen shared a video with us, but due to a miscommunication on our end, Vladlen shared a longer video than expected. And to stay on time, we will play it at the 1.2 speed. I hope the talk will still be okay. And Juning, can you please play the video?
Hello, this is a keynote for the workshop on autonomous driving at CVPR 2021. And even though the workshop is about autonomous driving, today I want to step back and talk about the basics. Let me begin by quoting from the Handbook of Child Psychology and Developmental Science, the chapter on development. The average toddler can run circles around the world's most sophisticated robots. By 18 months of age, toddlers can coordinate their limbs to navigate living room clutter, run into mother's arms, crawl under a chair, or climb up a flight of stairs. They can control their arms to pound a pig or pet a cat, and configure their hands to unscrew the lid of a water bottle or grasp a tiny bite of cracker between thumb and finger. They can synchronize torso, head, and eyes to examine a toy in hand, peer under the table, or gaze at a caregiver. They can coordinate tongue and jaw to eat a snack or speak their intentions. And whereas robots can still only perform particular tasks in particular environments, toddlers multitask in variable environments. They walk, talk, look around, and interact with objects and people all at the same time. How do we get there? That's what I want to talk about today. The basics, embodied intelligence, sensory motor learning. How do we do it? Let's think about the first principles. My conservative assumption that I want to advance today is that we're not going to outlearn the child. The child is the most impressive, the most effective learning system we know. If the child needs 18 months of experience, our artificial learners will need at least 18 months of experience. The child is an awesome learning system, and we are not going to outlearn the child. A more conservative assumption would be that we need an order of magnitude, more than an order of magnitude experience than the child, but let's start conservatively by saying we'll need at least as much experience as the child, since our learners are nowhere near as effective at learning as the child. But that's not it. That's not all. How about designing the learner? To design the learner, we need an outer loop of some sort that tries out different learning architectures and different learning settings and different hyperparameters and different learning schedules. This outer loop in reality was performed by evolution that tried out trillions of prototype learners to arrive at the learning architectures we have today. This child that achieves this incredible level of competence in 18 months is the result of trillions of experiments by evolution. Here, I am hopeful. I think we can be more efficient than that, because evolution is not teleological. Evolution is not a goal-directed process. Evolution was not deliberately from the get-go aiming to arrive as quickly as possible at the most effective embodied learning system. We know what we want, so we can drive there more deliberately than evolution did. However, there is no doubt that we will need an extensive outer loop that tries out different designs, different learning architectures, different learning schedules. Right now, we have no idea what the right architecture is that would give us the abilities that the child has. So we need extensive prototyping, extensive architecture search, extensive design exploration, and extensive hyperparameter tuning. That is the outer loop. How do we do this? If our inner loop is 18 months, how do we go through this process? We need to run experiments and observe the outcomes. And the only feasible solution is to accelerate the inner loop. Accelerate the inner loop by simulating reality at faster than real-time rates. How do we compare? How do we compress 18 months of experience into overnight? How do we compress 18 months of subjective learning and development into overnight? Overnight is a comfortable debug cycle. Overnight means that you launch an experiment at the end of the day, go home, come back in the morning, the experimental results are ready, you can tune some things during the day before you launch the next experiment. Well, compressing 18 months of subjective experience into 8 hours requires an acceleration of 1620. If we simulate reality at 30 frames per second, 30 time steps per second, if our temporal granularity is 30 time steps per second, we need to get to 50,000 frames per second. 50,000 frames per second, running the coupled simulation and learning system at 50,000 frames per second will allow us to compress the inner loop, the debug cycle, from 18 months to 8 hours. We can, of course, be more ambitious than that. Because 8 hours is still pretty long, it is a kind of time, a kind of debug cycle that is aimed at a human that is in the loop and is taking a day, a work day, to tune parameters or do some exploration before launching another experiment with a new architecture, with a new design. But a lot of this outer loop exploration will be automatic. It will be an automatic architecture search, hyperparameter tuning process, perhaps some kind of evolutionary process that is automatically exploring different designs, different variations, and is just launching every variant that it decides to try out and seeing how well it learns. For this kind of automatic outer loop, it would be much better to have, let's say, a 1 hour long inner loop, a 1 hour long debug cycle. So how do we compress 18 months of experience into 1 hour? We do that by simulating 18 months of experience in 1 hour, which requires an acceleration of roughly 13,000, 4 orders of magnitude. We need to accelerate reality by 4 orders of magnitude to get a very comfortable 1 hour long debug cycle. So if reality ticks at 30 frames per second, we are aiming at 400,000 frames per second in our coupled simulation and learning. Our simulation and learning system needs to yield a throughput, provide a throughput of 400,000 frames per second. That is what we are aiming at, and I will show you today that this is possible. We can achieve hundreds of thousands and even a million frames per second in coupled simulation and learning in immersive three-dimensional environments. This line of work was driven by 3 amazing PhD students that have all spent time or are now spending time in my lab: Alexei Petrenko, Eric Wymans, and Brennan Shacklet. These are amazing superhuman PhD students, and as you can see, they've achieved superhuman results. I'll begin with Sample Factory, our paper that was presented at ICML 2020, last year at ICML. Sample Factory is a clean, first principles, clean slate system design for high throughput reinforcement learning in immersive environments. There are a number of key ideas here. First, specialization. Every process specializes in a very particular, very narrow workload, and that's all that process does in parallel with massive parallelism, trying to get the highest level of utilization for the hardware by specialization. There are workers that all they do is simulate agents in the immersive environments. That's all they do. They don't do learning. They don't do the thinking of the agents. They just simulate agent actions and get environment responses. There are other processes that simulate the neural network in the agent's brain. They do the forward passes through the neural networks. That's all they do, just forward passes all the time, full throttle forward passes with whatever weights and whatever observations are given to them by other workers. And there is a third type of worker, and what it does is the backward passes. That's the learner. It gets experiences, already collected experiences by other processes, and it does the backpropagation, the backward passes. The second key idea is that all the processes communicate through shared memory buffers. There is no message passing because every message passing protocol is too slow. Once you ramp up to hundreds of thousands of frames per second, message passing becomes the bottleneck. So we don't do message passing. Everybody just writes and reads from shared memory buffers. And here there's a cute idea that we borrowed from computer graphics, which is double buffering. When two types of agents need to essentially access, read and write from the same buffer, the buffer is split into two. Agent A, agent type A, process type A, reads from buffer A. Process type B writes to buffer B, writes fresh information, for example, fresh neural network weights. And at certain points in time, they just swap pointers. They just swap pointers. When new information is ready in buffer B becomes buffer A. That's now the buffer from which processes A read the latest neural network weights, and the processes B start writing neural networks weights to the other buffer that used to be buffer A, but is now the buffer that is pointed to by processes B. It's a super simple idea, and it basically makes sure that nobody ever waits for anybody. There is never a reason to wait. There is no situation in which agents need to wait for new neural network weights, or the learning process needs to wait for new observations. There are always some reasonably up-to-date neural network weights in the buffer that the process points to, always some reasonably recent observations in the buffer that the neural network points to. Everybody always has data to work with. Nobody ever needs to wait for anything. With this clean slate design, we achieve more than 100,000 frames per second in an immersive environment such as Doom with a single GPU on a single node. One GPU, one machine, one workstation class machine. This is incredible. With the game Doom in particular, I like the game Doom, and we've used it in the past. I like it in part because I played it as a teenager, and in part because it is a classic game that popularized a whole genre, the genre of first-person shooters, and gave birth to a multi-billion-dollar industry. It is also open source. It is open source and easy to work with. We've worked with it before. The green horizontal line here, DFP, stands for Direct Future Prediction, which is an approach that we presented in an iClear paper several years ago. At the time, we won an international competition of AI agents playing Doom, and we achieved a certain level of performance in playing Doom from just raw pixel observations, and that's 30-something points here, the green horizontal line. The paper, by the way, is called Learning to Act by Predicting the Future. It's now a few years old, but I still like it very much. I think we said some things there that are quite good and are still worth reading. At any rate, a couple of years after that, we published another paper in which we showed that intermediate representations produced by computer vision provide a higher level of performance. They provide a boost of sorts by a few points. And that here is the orange horizontal line. The orange horizontal line is actually another very nice paper that was published at Science Robotics and talk about the utility of computer vision. Well, you can see the punchline. With Sample Factory, with just brute force, we can blow past those levels of performance by just an absolutely massive factor. And that is because Sample Factory allows us to learn so fast that we can run billions and billions of time step and just brute force through this learning process. When we pit our agents that are trained with Sample Factory against the in-game bots in Doom, there is just no competition. Our agents crush the in-game bots. Here, the bots, the non-player characters, are set to the highest possible level of difficulty. This is very difficult. As a human, if you try to play against the in-game bots at the very highest level of difficulty, for mere mortals like me, it's quite difficult. For professional players, it's easier, but the in-game bots at the highest level of difficulty are really quite scary. Well, our agents very quickly, within billions of time steps, which are made possible by sample factory, but very quickly in wall clock time, blow past that level of performance and just crush the in-game bots. There is just no competition anymore. DeepMind has a benchmark suite based on their DeepMind Lab platform. This is a suite of about 30 immersive environments, tasks in immersive environments, using sample factory on a single machine with a single 4 GPU node, a workstation class 4 GPU node. We achieved a higher level of performance than a DeepMind team that used a massive distributed cluster. Sample factory allowed us to train so fast and get to 10 billion time steps of experience so fast on a single machine that we outperformed what DeepMind did with their Impala project on a massive distributed system. The second work I want to present is an iClear paper that was just presented this year, iClear 2021, a few weeks ago, large batch simulation for deep reinforcement learning. And here we worked with more realistic environments. These are 3D scanned environments from the Matterport dataset. They have some issues. I wouldn't quite call them photorealistic, as you can see that there are some artifacts, but they're certainly much closer to reality than Doom or DeepMind Lab. These are real, scanned real-world environments. And the task here is navigation. You're given a coordinate in the environment, and the agent needs to get there as quickly as possible through potentially a very complex environment where the agent needs to traverse through rooms and corridors, maybe backtrack if needed, and get to a particular point in this extensive, complex, interconnected environment with a lot of occlusion. This batch processing simulator, BPS, batch processing simulator, is again a clean first principles system design for maximizing the throughput of this kind of coupled simulation and sensory motor learning in these immersive, reasonably high fidelity real-world environments. The key idea is batch simulation and rendering, where a large number of agents are simulated all at the same time. Their simulation is done in parallel by the same process, and they are rendered. Their observations in their different environments that they're instantiated in is rendered with a single rendering call. This is what it looks like. We, in effect, render an absolutely enormous image in GPU memory. This is one buffer in GPU memory. And with a single render call, into this image, we render a huge number of tiles, hundreds of tiles. Each tile corresponds to the first-person observation of one of the agents. Agents are deployed in instances of the same small number of environments. And the 3D assets, the geometry and textures from these environments are shared by these different agents. To get good sensory motor learning, we don't have every single agent to be in a completely different environment. Multiple agents can be instantiated in parallel in different copies, different instantiations of the same environment, just with somewhat different tasks, in somewhat different places, and somewhat different configurations. These instantiations reuse the same assets that are in GPU memory. And by rendering everything with a single render call into a single memory buffer, we drive the hardware, the rendering hardware, at peak utilization, at peak performance. These ideas allow us to render and simulate and learn with these complex high-fidelity scanned real-world environments at on the order of 70,000 frames per second. We achieve 70,000 frames per second for coupled simulation, rendering, and learning. The whole thing, simulation, rendering, and learning in the loop on an 8 GPU node with at 72,000 frames per second. This allows us to train navigation agents that roughly match the prior state of the art on this navigation benchmark. We train navigation agents that attain the same level as the state of the art in 1.5 days, in wall clock time, 1.5 days, on a single GPU. And we attain the level of performance on a single GPU in 1.5 days that was set just a year earlier on a massive industrial scale 64 GPU cluster in 3 days of wall clock time. So we collapse 3 days of training on a massive industrial scale 64 GPU cluster into 1.5 days on a single GPU. a workstation. This brings to mind a cheeky quote that was attributed by Paul Barnum. You can have a second computer once you've shown you know how to use the first one. The third paper I want to present today is Megaverse, and this is the first time this work is presented in public. Megaverse is a paper that was just accepted to ICML 2021. It will be presented next month at the ICML conference, and I'm telling you about this today for the first time. It has never been presented before. Megaverse is again a clean slate, first principles system design that aims to attain 1 million frames per second on a single 8 GPU node in interactive environments that are shaded and lit in real time. So you have lighting, you have shading, and they're dynamic, they're interactive, that allow us to prototype object manipulation, rearrangement. The agents can really engage with these environments and modify them, manipulate them, and interact with them. And we achieve it. We achieve our goal. We hit and exceed 1 million frames per second on a single 8 GPU node. An 8 GPU node is a standard hardware configuration that is present in many deep learning labs. Generally, a standard configuration is an 8 GPU node, and on one of these, we attain 1 million frames per second for coupled simulation and learning with these interactive environments. There are a number of ideas here. The key idea really is this batch simulation and learning. We build directly on the work that I presented to you earlier, and we just leverage and maximize this batch simulation and rendering such that a single process, a single instance of Megaverse can in parallel advance hundreds of environments, each containing multiple agents, and render them in parallel into a single GPU buffer with this kind of tiling that I showed you earlier. We leverage key ideas that I described earlier: specialization, batch simulation, and rendering to attain 1 million frames per second in real-time dynamic shaded environments. Before I proceed and show you some of these environments, let us step back and consider again what 1 million frames per second means. 1 million frames per second is a century of experience in one day. That allows us to simulate a century of subjective learning experience in one day and whole clock time, or 4 years of subjective experience in 1 hour. Here's one environment. This is the obstacles environment in our Megaverse 8 benchmark suite that we built using the Megaverse platform. The goal here is to get to a green patch of the environment by modifying the environment as needed to traverse it. Here is a high wall, and to traverse it, the agent needs to build a staircase. And you can see the agent building a staircase. And now the agent is going to build a bridge over the red patch. The red patch is lava. Bad. If you step into it, you die. So the agent builds a bridge and then traverses this bridge many times to build another staircase, to traverse another wall and get to the goal. This is actually quite hard. For a human, we can get the hang of it. We can do it, but it's hard. It's hard. The environments are procedurally generated. You never see the same environment twice. The agent never sees the same environment twice. This is very important for avoiding overfitting and understanding that we're really training agents that are learning generalizable skills for testing generalization. We can just generate environments again and again and again and again, and we're going to get a different environment at a calibrated level of difficulty every single time. And we can change the level of difficulty. We have easier obstacle environments, we have harder obstacle environments. This obstacle environment is only one kind of environment, one out of very many kinds of tasks and environments that you can build with the Megaverse platform. And the platform provides multi-agent support out of the box. Just natively, you can simulate multiple agents, dozens of agents in the same environment. They can be organized into teams. Some can collaborate, some can compete, depending on the task and really your level of imagination for what you want to try out, what kind of embodied intelligence dynamics you want to stress. We think of Megaverse and the Megaverse environments as a platform for building model systems for embodied AI. It's a platform for model systems for embodied AI. And the analogy here is neuroscience. In neuroscience, much of what we know about learning and memory comes from experiments on model systems such as Aplysia, a sea slug. At the top image, you see Aplysia, the sea slug, in its native habitat at the bottom of the sea floor. In the left image, you see Eric Kandel, Nobel laureate, holding an Aplysia in his hands. He has worked with Aplysia for decades, and using experiments on Aplysia, he established what we know, much of what we know about how learning and memory work in animals, including humans. But rather than running experiments on humans in the whole complexity of our natural environment and the complexity of our nervous system and the difficulty of doing experiments on humans, instead, he made the strategic call of studying a simpler model system, Aplysia. Aplysia has a simpler nervous system, and it has beautiful large neurons that you can see with the naked eye. But the basics, the foundations, the basic principles of learning and memory are actually the same. The principles that drive the organization of the learning system and the formation of memory are the same. So by working with the model system, Aplysia, he was able to learn much of what we now know about how learning and memory works in animals, including humans. When he gave his Nobel Prize lecture in the year 2000, he showed the picture of Aplysia with the Nobel Prize. The picture that you see on the right is taken from Eric Kandel's Nobel Prize lecture to acknowledge the role that Aplysia played in this work. Our argument is that fairly simple immersive environments of the kind that you can build and simulate at 1 million frames per second in Megaverse can lead to this kind of fundamental understanding of the basic principles of sensory motor learning and embodied intelligence. As long as these environments elicit the kind of advanced embodied cognition that we are interested in, navigation, exploration, long-term planning, long-term memory, the formation of internal representations, as long as we can elicit these with our model environments, we can usefully, productively, informatively study embodied cognition, embodied intelligence, sensory motor learning in these model environments built and simulated on top of Megaverse, which sure is convenient because we can do it at 1 million frames per second with a very, very manageable debug cycle. To give you just some indication that we're onto something here, that we can simulate pretty non-trivial challenges in Megaverse with 1 million frames per second. This is the learning curve, the learning success rate over 2 billion time steps for model-free reinforcement learning in these obstacle environments that I showed you. Remember that every environment is different every single time. They're all procedurally generated, so the environments are not identical to what I showed you, but they come from the same procedural generation mechanism. And you see a beautiful flat curve that stays at 0. Turns out model-free reinforcement learning, at least our fairly credible instantiation of it by fairly experienced researchers, just doesn't get off the ground. So model-free reinforcement learning with a fairly reasonable instantiation of it just doesn't get off the ground with tasks of this complexity, which provides some indication that there's something interesting here. There's certainly something worth looking at and understanding. And my hypothesis is that this can lead to deeper fundamental understanding of the basic principles of embodied AI. Here's another task. This is tower building. The goal here is to build a tower that is as high as possible on the black perimeter, within the black perimeter on the black patch. This is human performance. This is a human performing this task. You can see that the environment is dynamic, interactive. We're moving, building materials around. We have a suite of 8 different tasks. Now you're seeing the second out of 8. This is our Megaverse 8 benchmark suite that test aspects of embodied cognition that seem to us to be fundamental: navigation, exploration, tool use, manipulation, long-term planning, and memory. Here you will see the procedural generation aspect. You'll see a number of these environments, a number of tower building environments generated procedurally. Again, never see the same environment twice. You get to test generalization very well in this way. one very interesting aspect of these environments, that tower building environments, is that Model 3RL does attain a good level of performance. Here you will see a trained agent, trained with Model 3RL in Megaverse, building a tower. This is no longer human gameplay, this is an agent. And you will see that the agent got the hang of it. They understand what building a tower means. They need to build it progressively, maintaining a staircase structure that lets them go up and down, and carry building material to the top to make the tower even higher. And they also understand how to wrap it around within the black patch to stay within the area that they must operate in. Very, very neat. Here is a third environment. This is called Rearrange. This is inspired by the classic MIT copy demo. You're given a configuration of objects on the white platform, and you need to reproduce it with building materials that you're given on the blue platform. So whatever you see over there, you now need to create it over here on the blue platform. You're watching human gameplay. This is Alexei doing this task, and Alexei can of course do it, but turns out Model 3RL, not so much. Model 3RL does not get off the ground, and in our experiment so far, does not attain a good level of performance on this rearrangement task. Here you'll see the procedural generation aspect, the procedural generation of multiple of these rearrangement environments. And now I showed you three out of the 8 Megaverse environments in the Megaverse 8 benchmark suite. We think the benchmark suite is good, but what I'm even more excited about is Megaverse as a platform that allows you to create such benchmarks. Megaverse is a platform that allows you to create such classes of procedurally generated worlds that stress different aspects of embodied cognition, and you can try out training agents in these worlds with your favorite learning paradigm, your favorite approach to sensory motor learning, and benefit from 1,000,000 frames per second. So sample complexity is no longer a good excuse. We take away sample complexity as an excuse for poor performance. You can easily get billions of time steps during learning, tens of billions of time steps, no problem. If you want to try out something that requires tens of billions of time steps, no problem. The remaining problem is the fundamental understanding of sensory motor agent architectures, internal representations that they construct, and learning processes that they go through. To summarize, speed matters. Achieving hundreds of thousands or millions of frames per second reduces our debug cycle such that we can study advanced embodied intelligence with very, very comfortable, very short inner loops that allow us to then iterate rapidly over different learning designs, learning architectures, and hyperparameter configurations. And the good news is that we can attain hundreds of thousands and now 1,000,000 frames per second with clean slate, first principles system design. And we can do it with hardware that is present in pretty much every deep learning lab. A single 8 GPU machine. You don't need custom, massive, distributed infrastructure that is only found in industrial research labs. You can do it. You can do this kind of research and probe the foundations of embodied cognition and embodied AI in your lab with a single 8 GPU node. There are a number of design patterns that are proving very useful in this sequence of projects: extensive use of shared memory rather than message passing, double buffering, and notably batch simulation and rendering. The frontier here, I think, is maximizing throughput with photorealistic simulation of very high fidelity, dynamic, real-world environments. The Megaverse environments I showed you are like model systems. And I made an argument that these model systems can carry us a long way. And I believe this argument. I think this argument is good, and it is true that model systems of this sort can give us fundamental understanding and carry us a long way. However, in the meantime, we should also explore how far we can push high fidelity simulation of very complex real-world environments that capture as much of the real world as we can, because at some point we will need it. At some point it will come in handy when our fundamental understanding is further along. Higher fidelity simulation of more complex environments that are closer and closer to the real world will become more and more important. We are working on this now, and I encourage all of you to work on this as well. It is an absolutely fascinating problem. Thank you very much.
Hey, I can already see Raquel. So, and already in full screen, perfect. So let me introduce Raquel. She is a full professor at the University of Toronto, a co-founder of the Vector Institute for AI. And recently, I think everyone heard that she just founded Vabi, which wants to take, which develops the next generation of self-driving technology. And I'm definitely looking forward to hear something about this technology. Raquel, the stage is yours. No, we have again a microphone problem.
Thank you for giving the power. It's really a pleasure to be here today, and in particular, it's been an incredible couple of the last 2 weeks. Let's see, cool. So today I'm going to be talking about interpretable neural motion planner, and before I start this, I think it's worth to spend 1 minute thinking about where the industry is today. So since the DARPA challenge in 2004, there has been meaningful progress in terms of technology. However, when it comes to commercially deploy this technology, it's really in very small operation domains that are also very, very simple. So in particular, there is like 2 main key open questions that there is a lot still for research to actually be working on. On one side is the need for autonomous systems that are able to really solve the long tails of all the things that might happen in the world. The second piece of technology that is required is the ability to do real-time, high-fidelity closed-loop simulation in order to test at the scale and also to train your AI systems. WAP is providing breakthrough technology for these two open problems. And in particular, we are doing an AI-first approach and you will see a little bit of some of the I guess technology that we have built in the past in this direction today. But basically, we are building an AI-first approach that is interpretable, is end-to-end trainable, is explainable, and can through complex reasoning can solve the long tails. We also have a breakthrough closed-loop simulator with an unprecedented level of fidelity that works in real time. And it really allows us to test at the scale, regular scenarios, as well as scenarios that are, the long tails of the rare events. Now, in terms of the use case, the first use case that we're going to be pursuing for our technology, we're going to start with long-haul tracking, which makes a lot of sense because there is a chronic shortage of drivers, and there is also, pervasive safety issues. It's actually considered to be one of the most dangerous professions in North America if you're a truck driver. So there is a lot that this technology can really provide. On top of this, if you think about highway driving, it's actually more simple to solve than compared to driving in our cities, where the complexity of the world is much higher. Right? That doesn't mean that it's a super easy problem to solve, but it's definitely the first one that we're going to start with. Now, the other thing that we announced last week was that our Series A, after I guess on our 3-month anniversary of the company, we launched it publicly, and we announced a set of incredible investors that they're the best in class in terms of deep technology, logistics, as well as the thriving Canadian ecosystem. And we announced one of the largest Series A in Canadian history. So we have offices in Toronto as well as San Francisco. And if you're excited about solving self-driving and you want to do it with technology of 2021, this is the place for you. So please, apply. We have plenty of openings, more than 30 or so right now in our website. Okay, so I hope to see you all there. I think there is many incredible things that we can do together. All right, let's go back now to the, I guess, the topic of the workshop. And let me start by talking a little bit about how traditional approaches to self-driving work. Right, so typically, and this is what you will see typically in industry, right? So you have the vehicle that senses the environment. This is seen from the top here, and basically the first thing that typically every self-driving vehicle does is that you localize with precision of a few centimeters. And the idea of doing this is that you want to be able to import your high-definition maps that tell you a lot about the environment before you even see anything. Then basically the perception system is going to tell you, where are the objects and things. It's going to perceive things, around the vehicle. Then you're going to predict the motion of the actors into the next few seconds, and you're going to use all this information in order to, plan a safe maneuver that is comfortable to arrive towards your goal. Right, and this is something that you repeat every fraction of a second. Now, if you think about this traditional software stack, there is a couple of advantages, but also there is some issues. This system is actually interpretable, and it's very easy to incorporate prior knowledge, right? So that's great, right? Engineers can actually, for example, tune the cost of the motion planner in order to reflect their intuitions about the task of driving. However, if you look at how this is typically deployed or work on in industry, you're going to have teams of hundreds of people, in some of the companies even more than 1,000, working in this piece of software, right? So you end up with teams that work in silos in small pieces, and there is not really a holistic view into how to solve this task, as a single system, which is extremely important to do for such a complicated task as self-driving. Furthermore, typically the software stacks, don't look as pretty as just a few building blocks, a few modular functions, as I was showing you here. Instead, it's an extremely complicated system where every time that there is an issue on the road, basically there is yet one more module that tackles one specific thing, and it looks more like an if-else statement than anything else. Also, the fact that there is no ability to train this end-to-end, you end up basically with very little interfaces between the different models. And as a consequence, if you have a mistake, it's very hard to actually reason about it or be able to correct this mistake. Instead, you have this cascading issue as you go through the software stack, right? And engineers typically are pretty, unhappy because developer productivity is very low because there is no automation. Basically, you have to tune one thing at a time, and every time that you make a change in one of the models, you will have to change everything else. So the alternative that we've seen, quite a bit in academia, is to, instead of having this modular approach, to try to use a single AI system to basically for the task of driving, right? So sensors in and then driving commands out. The advantage of this is it's super simple, right? A few lines of code will do it. The problem is that, the other advantage is that you're going to train the system for the end task of driving. So that's important. Now, the difficulty of this, or the problem, is that there is really no interpretability, right? So, if the system does something wrong, you're going to have an issue into explaining why it is the case. Also, it's very difficult to incorporate prior knowledge, and the assumption is that you're going to observe, you're going to have data for all the things that might happen, and then basically you will learn from it. But as we know, it's potentially unethical to collect data where you have near life or accidents, right? So this is not a solution either. So the type of technology that we've been developing, and we continue to go into the next generation now at Wabi, is something that inherits the advantage of these two approaches without inheriting the disadvantage. In particular, it's going to be modular. You're going to be able to incorporate your prior knowledge, and it's going to be interpretable, so that at every point in time, we can explain why the system actually decided to do a particular maneuver. However, it's going to be end-to-end trainable, right? So you have all these advantages of being able to have more complex functions. Even, for example, when you're doing the motion planner module, you can actually get access to raw sensor data, which is, potentially very, very important to not have these cascading mistakes, right? So this is, a new family of models that actually is, very, very, very interesting from a modeling perspective, and at the same time, actually, they work remarkably well. All right, so today I'm going to talk a lot about two generations, the latest two generations. But before, I'm going to show you the first that we built in order to motivate what they need for a different one. Right, so I guess Motion Planner was the first generation that we showed CVPR a couple of years ago. where the idea is that you're going to use the raw sensor data. So whether it's LiDAR or, you can also fuse multiple sources like cameras, radar, etc. And we're also going to use the maps, and then you can use, rasterizations or graph representations, whatever your favorite is. We are going to process this information to obtain some intermediate features. And then basically our first generation was treating this problem as a multitask problem, where we're going to detect the objects of interest. We're going to predict, sorry about that. We're going to predict their motion into the future. And at the same time, if my computer wants to work, which doesn't look like, and at the same time, we are also going to predict a non-parametric volume, where it basically represents what is the cost for the self-driving vehicle to be at every point in time in space and time, okay? Such that planning can be done very, very simple by doing a forward pass to obtain all this different information. And then basically we sample a very large collection of physically realizable trajectories. And then we can simply evaluate these trajectories or cost these trajectories by indexing in the cost volume at the appropriate location in terms of space and time, right? We can sum this up, do a minimum operation, and basically the solution for every frame will be just the argmin of this, right? So this is something that you can do on GPU super, super efficiently. So showing you just a video of this, it also worked remarkably well. And so here you're gonna see how we are gonna detect the objects of interest, predict into the future, right? And this, I'm gonna showcase the volume here with basically colors indicated time. And the volume is 3-dimensional, so I'm gonna project it into 2 dimensions so that you can actually see something. And I'm only gonna show you the areas of low cost, okay? So that you get a sense of what the self-driving vehicle is actually thinking. Okay, so you see that it produces multimodal possibilities, understands the notion of changing lanes and staying on the lane. It understands, that you can turn, that you should slow down. If somebody cuts in front of you, that potentially you can change lanes as well, right? So it does all these complex behaviors directly from data without any hard coding of any of these behaviors, which you will typically see in planners. Now, I say that I wanted to talk to this to motivate the next approach. And in particular, we've seen a lot of work in the self-driving literature that the perception model does object detection. And there is actually, an issue potentially if all your perception system is based on detection, right? So let's look at this with a situation, right? We have an intersection. This is the self-driving vehicle. If we actually detect all the objects of interest, right, so we can actually plan a safe maneuver. For example, here we're going to slow down. However, if for whatever reason, in particular, this object is below the threshold of the object detector, then suddenly you're going to go blind, right? So this is not a very safe idea, right? Because you're going to basically accelerate and then, continue driving in the intersection, and potentially you will arrive to a collision, right? So what I'm going to be talking today is working with a different type of intermediate representation, which we like quite a lot, which is basically instead of doing object detection as part of the pipeline, we are going to directly work in semantic occupancies. Okay, so if you look at typically how detection is used in motion planning, is that the detected boxes and their trajectories are rasterized into an occupancy. And the question is, why to go through this thresholding, iteration in between? Instead, can we just predict directly the semantic occupancies? Okay, and in a way that is end-to-end all the way to the motion planner. All right, so let's look at the first approach. So the idea is that we're going to have the semantic information, and with the semantics, you can actually think of them as a probability distribution of where the different objects or actors might be at different point in time, right? So there are spatial and temporal. And temporal here is the prediction horizon, which is, how much in advance are you predicting how everybody's going to move in the future. And what is interesting is that we have, different layers of this prediction for every type of class of interest, right? Whether it's pedestrians, whether it's bikes, whether it's vehicles, you can also have an additional class, which is everything else, so that you handle all the open set things as well. And in this case, they're not mutually exclusive. And the reason why is that, potentially a pedestrian might actually be riding a bike or might enter a vehicle, etc., right? Or a bike can be on top of the vehicle. Also, what is also interesting of this representation is that we have very fine-grained sort of semantics within the classes. We reason about occlusion a lot because it's important to slow down if you don't see well. So we want to handle that kind of behavior. And also, things like whether they are in conflicting lane on our route, etc., will also, depending on whether we see things in these different semantics, right, we will actually act differently. So the way that we are going to estimate the semantic occupancies is going to be, again, very simple. We're going to have, our sensor configuration, sensor data. Again, you can use your cameras, you can use your radar, whatever, all set of sensors here. You have your map. We are going to basically, process this through a neural network. And then we're going to basically produce some intermediate features from which a recurrent neural net is going to estimate the predictions into the future one timestamp at a time. Okay, and this is important in order to try to get some level of consistency in your occupancies versus just predicting all the different timestamps into the future at once. Okay, so then basically this semantic occupancy is going to be used by the motion planner as well as the map itself. And we're going to use a sampling-based motion planner. It's something that we actually like a lot in the lab. It's a great type of planner that is actually really, really easy to work with, and it's very amenable to learning as well. And in particular, so the way it works is that for the self-driving vehicle, we're going to sample a set of trajectories. We're going to evaluate those trajectories. We're going to cost them all those trajectories, right? And we're going to select the one with the minimum cost. Okay, so in terms of the trajectories, you can be quite clever into how you actually generate the potential set of trajectories for the self-driving car. So you can do it, behavior-based, so that you reason about all the possible behaviors that you might want to do, and also to be super map-aware, so that with a relatively small number of samples of these trajectories, say from 1,000 to 10,000, something like this, you can actually have a super dense, set of trajectories from which to choose. And this is, key if you don't want to use a continuous planner after the discrete planner. All right, and then we're going to evaluate these trajectories with, some cost function, which is a sum of costs that basically represent things like, based on our semantic occupancies, we want to avoid occupied regions. We want to drive comfortably, right? You don't want to zigzag around, so minimize jerk, things like this. You want to follow the route because you're going from A to B. You're not just driving around the world randomly. You want to also drive, close to the center line because that's safer than if you are, on the edge of the road, etc. Right? So you have this set of costs, and then basically you have the sum of these costs, which are a function of, all the intermediate representations. And then basically, once you sample, you cost, and then you select the one with the minimum cost. Okay. So I was mentioning these are functions of all the intermediate representations, so that you basically can train the entire thing end to end, right? So you have some kind of deep neural network followed by some optimization stuff, right? So this is the complex optimization model. And the way that we learn this system is basically with a set of loss functions. For interpretability, we have a loss function at the level of the semantic occupancy that basically, we use a form of cross entropy here, right? Saying that for our training set, right, we should be able to create occupancies that are as similar as possible to the ground truth of what is the representation of the scene. And then for motion planning, since basically what we do is that we do max margin. So we just backpropagate through the max margin loss. Okay, and then you can simply do this, by just running inference and basically utilizing the gradients from the first part of the network. Cool. So this is the way that you train end-to-end the entire system, and actually it works remarkably well. So this is comparing to things like behavioral cloning, adaptive cruise control, the first neural motion planner I show you. This is the Waymo multipath followed by the same type of cost functions planner that we use here. And this is the end-to-end system with the semantic occupancies instead of having object detection followed by prediction. Okay, and you see that it's much, much safer. It also, in general, is as good as anybody else in terms of how well it imitates what humans did, as well as equal in terms of progress, and it's actually very smooth. Okay, so this is a very good planner. And you might ask, how important is to train end-to-end? Well, it is quite important. But what is so this is end-to-end training versus the same thing, the same planner into just stage-wise. First the semantic occupancies, and then the motion planner, right? So there is quite a bit of boost, right, particularly in safety. And this is showing here the importance of the actual representation. So if you have trajectories, so this is detection followed by prediction into the future, followed by rasterization, and then the same planner. And you see that using the occupancies is much, much better, particularly again in terms of safety, in terms of jerk, as well as immediating humans. Okay, so this is, it's a great representation that is much safer, typically, the detection. So I'm going to show you some qualitative results. So what you're going to see is now open loop setting, meaning that we're going to unroll the plan based on 1 second history. We're going to unroll it for 5 seconds, and we're not going to reuse the observations to recorrect that plan. Okay, and yes, want to show you how good the full horizon of the planner is. Okay, and I'm going to show you the ground truth of what happened in practice as well. Okay, but remember that we don't use those observations. Okay, and this is from raw sensor data. So what you can observe here is that there is like multimodal distribution, like for this bus, right? It captures it very, very nicely. Different colors are just different semantics, right? And as I said, this actually overlaps quite well with what happened in practice, but note that, again, we are not using the observations to replan. Okay, this is just what will happen into the future. Okay. This is showing that we can very nicely reason about, pedestrian crossings or, very small objects, as well as, slowing down and never overlapping what we predict for a vehicle just yielding to pedestrians and the pedestrians, right? So you can actually handle, very complex behaviors, etc. Cool. So these are open loop metrics, and one of the things that we've seen, particularly in the computer vision literature, is people only looking at perception or prediction or metrics there. So going to the end to motion planning is a big step forward, but open loop is not sufficient. Right, just predicting what I will be doing, and then just the next frame will be my ground truth of my trajectory is not sufficient to understand whether I'm gonna do well if I actually put this system to be on a real self-driving car and I say yes, drive around. Okay, and the reason why is that you don't see things out of distribution. You don't see the compound errors that would happen if you deviate, etc. Okay, so this is the need for the closed loop simulator that I was mentioning, and what we're going to do here is utilize, our, super duper whatever simulator. And I'm going to do a 3 minutes introduction into how the simulator is and what you need to build, and then we will go back to the task. All right, so in order to do this closed loop simulation, we need to, and remember, we need to do sensor simulation. So we need to recreate the virtual world. We need to be able to generate automatically scenarios that are super realistic, and we need to simulate how the sensors will have observed this scene. So in a nutshell, the way that we do this is very different to what you will see in the industry. So for recreating the virtual worlds, we do it from just raw sensor data. You can see at this CVPR with GeoSim. So one of our best paper award candidates shows how to reconstruct super accurately assets by just driving. We also have another paper at CVPR on how to reconstruct just with a single letter sweep as well as a single image animatable pedestrians. So you see them once in a single frame, and then you can from there automatically animate them, reconstruct the shape, their skeleton, and the skinning wedges to animate them to do whatever you want and simulate them. We can also generate these arbitrary scenarios automatically. We use some form of convolutional STMs for the scenario initialization, followed by pretty sophisticated conditional models, conditional VAE models. So this is a version of ILBM that you will also see a paper at this conference. Okay, and this actually works remarkably well. As you can see here, we can simulate behaviors that are super, super realistic. This is just showing, give us a map, and then we can generate in this map arbitrary scenarios. Okay, and you can do this at the scale, super fast. And the good thing about this way of simulation is that you can actually generate super realistic behavior. So this is an AI system orchestrating everybody. And you see for here, I'm going to show you 4 different maneuvers and how accurate you can actually do this. So things like U-turns, things like lane changes, and you're going to see a unprotected left after, which is one of the most difficult things to simulate. All right, so here comes the unprotected left. All right, so then we can use our sensor simulation. It also runs in real time. Actually, it's only a few milliseconds. It's less than 10 milliseconds, if I remember correctly, to do the simulation of a single LiDAR sensor. And basically, you can see the real LiDAR, the simulated LiDAR here, and the output of perception is in green, and you see that it correlates perfectly. So this is the reason. This is why we have this high fidelity. The reason why you can actually really understand how your system performs in simulation. All right, so you can create your safety critical case, and here the entire software stack is tested, right? And then we are seeing that we can actually behave and react to somebody just entering the lane just in front of us, coming out of occlusion, which is one of the most something that happens a lot, but it's actually quite safety critical. And we can do this at scale, right? And this is the way that you can really generate all these scenarios to test your software stack. Okay? And we can also simulate things like cameras. So this is GeoSim, which is which I was talking about before, where basically a few of the objects that you see here are actually fake. Okay, and my question to you is, can you identify which ones are fake? So for example, this one is actually fake. It's in front of us, but it's super hard to say. So this is in 3D, so we can do simulation of LiDAR as well as images. It's a video simulation. Here we are inserted objects that were captured in some other location, some other place with very different lighting conditions into an existing log. Okay, so and we can simulate again very realistic behaviors and multiple cameras at once in a way that is consistent. Okay, so this gives us an incredibly powerful simulator in order to really test and train our software stack. All right, so the way that this will work for testing now is that we have some observations from the simulator, right? Which is in this case we're gonna do the experiments here with LiDAR. The autonomy stack reacts. They're gonna upload, and the actors react to us and to themselves. We're gonna update the world state, and then we're gonna resimulate for the next frame. Okay. And oops, sorry about that. And this is showing results for now. We're going back to the neural motion planner that I explained before. And then one of the things that we can see is that in open loop, the differences are even bigger. Right, so this is again sort of the Waymo style multipath followed by a planner, which is the same kind of planner as we use here, versus this representation as an end-to-end trained system. And you see that it's a gigantic difference in terms of the safety. Okay, so it's super, super important that you test in closed loop simulation, because this kind of thing, you will not see the difference if the only thing that you pass is the trajectories that the car had driven before. All right, so the last bit that I'm going to show you is MP3, which is also another candidate for Best Paper Award at the CVPR. And the idea of MP3 is actually quite simple, and is that if you think about these neural motion planners that I was showing you before, we use maps, right? So we assume we can localize super precisely, and then we can use this to estimate where we are. Sometimes the localization might fail or the maps might not be up to date. So now what we're going to do is have a neural motion planner that really works much more like how humans drive. If you think of us, typically we will have maybe our Google Apps map and it's going to tell us things like, oh, in 50 meters, take a right turn. Right? So let's see how we can do neural motion planner in a system that only takes that as input, as well as the raw sensor data. So there is no maps given to us a priori. Okay, so this is much more scalable. We can use this if localization fails, etc., etc. All right, so the way that we're going to do this is the following. Again, we have the raw sensor data. Now there is no maps, right? We're going to process this information and through a neural network, we're going to estimate not only the dynamic part of the environment as we were doing before, but we are also going to estimate online the maps, okay? And we're going to use this information together with the high-level commands, like keep straight, turn right in 50 meters, to basically route and perform the entire motion planner, okay? And basically decide of what the self-driving car should be doing, right? So very, very, similar sort of in terms of the inputs of how a human will actually do. All right, so let's look at the scene representations, and then we will look at the plan. If my computer wants to work. Thank you. So in terms of the semantic representations, now they're going to be enhanced. So we have drivable area, we have intersections that we predict, reachable lanes. We need to understand where we can drive that is not the opposite direction or things like this online, right? This is actually quite difficult. And also we have some sort of notion of orientation that is going to help us. Then dynamic objects like occupancy, as well as a motion field. And the interesting here is, instead of having a recurrent net that predicts always occupancy, we are going to incorporate more consistency by predicting an occupancy in the first frame, and then a motion field that is multimodal, that basically can be combined to decide into, by moving the occupancy into where the occupancy will be in the next time step, and next time into the future, etc. Okay? Yeah.
Raquel, can you please wrap up? The half hour is unfortunately.
No worries, no worries.
Thanks a
cool.
lot.
So I have, I guess 2 more minutes. That's okay. Come on, you gave a Blandon 42, man. All right, so so we do motion planning, right? And we need to decide on what is the routable route. So we do this through a neural network that is basically a switching component. We basically have a way to retrieve trajectories now, so it's non-parametric, and then we're going to cost based on our online maps as well as the dynamic objects, okay? And we can train this end-to-end in a similar fashion from before, and it actually works remarkably well. And I'm going to show you just results.
We initialize the self-driving vehicle in interesting state from logs. As it executes the planned actions, we can see how the plan, shown in blue, diverges from the trajectory the expert performed when the log was recorded, shown in black. Here, we showcase an interesting scenario where the self-driving vehicle exhibits cautious behavior around fast-moving traffic, similarly to what the expert driver did. In this other scenario, we first highlight the accurate route prediction for a left turn in an atypical map topology. As the other cars pass by, our model shows more cautiousness of the expert driver when yielding to them.
So this is a good thing, right? To be cautious.
At the core of safety in a self-driving vehicle is the behavior around heavily occluded pedestrians. In this example, we can see our model safely predicts a pedestrian in between cars might jaywalk, and we reduce speed accordingly. MP3 can also navigate a heavily crowded 5-way intersection with an atypical topology by driving cautiously. Finally, we can see how it yields to pedestrians at the crosswalk.
Cool. So just to summarize, so we show how with new motion planner we can go from raw sensor data all the way to the decision making of the self-driving vehicle. How these dense representations instead of detection is actually a much better representation that is much safer. And finally, I show you how to basically drive without a map. So this is all for me today. Come join us if you're excited about solving self-driving and how to change the world with it. Thank you.
Thanks a lot, Raquel. And I think there is no time to spare. And it's a pleasure to hand over to James. Bye, Raquel. And the Argoverse challenge. Can you, microphone unmuting works much better now. Okay, thanks a lot. And James, the stage is yours.
Okay, great. Thank you guys for inviting me. It's a pleasure to be here. It's a pleasure to get to share our competition with this such an awesome selection of speakers and other competitions, Waymo as well. I'll try to get back on time a little bit. First, a recap of what is Argoverse in case you've never heard of our data sets. And then we're going to have 3 different presenters for 3 different challenges, taking about 15 minutes each. Stereo will be presented by Joni right after this, and then motion forecasting by Jagjit, and streaming perception by Martin. And then I'll wrap up with some other brief announcements. So Argoverse is one of the first modern self-driving data sets. Let's say a bunch of them got released in the last few years. We were the first data set to have HD maps, actually, although Lyft and NewScenes and Waymo have now released HD maps. And Argoverse is really two data sets: a sensor data set, which has things like object cuboids, LiDAR, camera images, and a motion forecasting data set, which is these abstract bird's eye view scenarios of trajectories. And the sensor data set has several leaderboards for different competitions we can do with it. For example, 3D tracking, 3D detection. But most relevant for today, a new stereo competition. This is the stereo data has always been there. It's the first time we're doing a competition because we've defined some notion of ground truth now based on LiDAR accumulation, which is always tricky and always imperfect. So anyway, and the other competition is the motion forecasting competition that we'll talk about today, which we have run 3 times, and Jagjit will be presenting that. And then again, there's a streaming perception challenge, which also uses our sensor data set, but it uses additional annotations that Martin added himself, and he'll explain what's going on there. Okay, and I don't want to take any more time, so I'll pass things now to Joni to present the results of our first stereo challenge.
All right, so let me share my screen here. Great, so I think everybody can see the proper slide.
Yeah.
Cool. So hi everyone, I'm Johnny and I'm a research scientist at Argo AI, and I'm gonna present the results of our first ever Argoverse stereo challenge. So some cool results to show you guys. Oops. So the first thing I want to do is to talk about the Argoverse stereo dataset. So our stereo dataset is based on the Argoverse 3D tracking dataset, which has high resolution stereo images that was sampled at 5 Hertz and that can be synchronized with the LiDAR point clouds. And inspired by the Kitty stereo dataset, actually, we also accumulated the consecutive point clouds to densify the ground truth depth maps. Otherwise, would have pretty much like sparse depth by projecting a single LiDAR onto the frame. However, we did not rely on vehicle CAD model fitting as Kitty did to handle the dynamic objects in the scene. We instead used our recent scene flow method to non-rigidly register the point clouds without any priors. And with that, we could create ground truth depth maps to for the high resolution rectified images that we have available in the Argoverse dataset. So if you look at the distribution plot here, where the x-axis is the depth in meters and the y-axis is the number of rays, or the number of ground truth depth available in our dataset or in the Kitty stereo we're comparing against to, we can see that the Argoverse stereo in blue has significantly more ground truth information than Kitty stereo. In fact, the Argoverse stereo is about 16 times bigger than Kitty, and it covered longer distances. The dataset is publicly available, and if you guys are working on stereo, please consider using it. Now, the idea of the stereo challenge is to motivate research on stereo models that are accurate, lightweight, and fast, given the high resolution stereo image that we made available. The participants submitted their results on our test set, in which the ground truth is not available. We've withheld the ground truth for the test set. And for the evaluation, we use the open source Eval AI platform, which is a great platform for this kind of competitions. And we had about 260 submissions from 49 teams, and the leaderboard has about 30 entries. So it had a good motion in this challenge, considering the stereo community to be such a small community. Also, the leaderboard will remain open, so feel free to submit your results for evaluation at any time. So here's the public leaderboard, and the top 5 teams we'll be discussing next a little bit. For evaluation, we use the standard stereo metrics that we define as all, which is the percentage of disparate errors averaged over all the ground truth pixels. FG, which is the percentage of disparate errors averaged over only the foreground regions. We released these masks as well, so you can easily identify the foreground objects. And the background, BG, is the percentage of disparate errors averaged only over background regions. And we count a disparate error if the absolute error between the ground truth and the prediction is greater than a threshold. And we define the threshold as 3, 5, or 10 pixels. And the relative error is greater than 10%. So the lower the matrix, the better. And we rank the leaderboard by the 10 pixel threshold. So the winner is clearly the MSMD net team. Congrats to their effort, but also congrats to all teams for their effort and participation in our challenge. We got some tech reports from MSMD net for fun and NPUIAP stereo. And so I'll next give a very brief overview about their methods, given we have a short time to do that. Okay, so let's see what the winners did. So they proposed this MSMDNet V2, which is an improved version of their work, deep stereo matching with multi-scale and multi-dimension cost volume. So basically, given a stereo image pair, the model extracts features at multiple scales, aggregates all features in a multi-dimensional cost volume, and performs a refinement on the disparate map using a 3D warped correlation volume. So if you guys are interested, please have a look at their paper for the details. The Forefun team proposed a multi-level aggregation network for high-resolution stereo matching, and they built on top of the stereo state-of-the-art LIA stereo method. And LIA is based on a standard stereo pipeline. So they perform feature extraction and matching, and then they build up a 3D cost volume, and then they estimate a disparate map. However, the authors of LIA perform this neural architecture search to find the optimal stereo matching architecture. Still, LIA is not lightweight in any way. So LIA is computationally expensive for high resolution images. And the Forefun team proposed a simple strategy where they split the 4D feature volume in the height dimension to process it sequentially. And it could get some pretty good increase in performance regarding time and memory consumption. So the team NPUIAP stereo didn't send us much information about what they did specifically, but the only thing that we know is that they employ this their method, the NLCANet, a non-local context attention network for stereo matching. And what's different in their method is that they propose this non-local attention matching module that seems to improve the global matching learning according to their paper. So please check their paper out if you guys are interested. And here's an overview of the methods that we have reports. Also included in the first line, the LIA stereo as a baseline. What we can see here is that all methods train their models on a synthetic data set, the scene flow data set, which is a pretty common thing to do for stereo matching algorithms. After that, they fine-tune their models on our stereo data set. And they also used a bunch of data augmentation techniques. The only method that used multi-scale features is the winner, MSMDNet, which seems to help when using high-resolution imagery. For the cost volume, MSMDNet rely on a multi-scale and a multi-dimension cost volume. Forefun proposed a strategy to split the single LIA cost volume into multiple chunks to better handle the high-resolution input. And NPUIAP stereo used a single cost volume. And most methods use the smooth L1 loss to supervise their methods, with exception to the winner that use an entropy-based loss. And an important advantage of the entropy loss is that it gives us the uncertainties of the estimated disparities. And Forefun also used a foreground loss term to, in addition to the smooth L1, to encourage the network to learn better at foreground regions. And in terms of memory and inference time, the winner has the least footprint. It takes about 14 gigabytes of memory and 1.8 seconds to infer a single high resolution image from Argoverse stereo using a GPU. So this is pretty good, but it's still not lightweight and fast enough for light applications or real-time applications. So, but hopefully we'll get there. So here we show the evaluation metrics for the top 5 methods, and we focus on the 10 pixel threshold. In the x-axis, we have the top 5 methods. In the y-axis, we have the percentage of disparate errors averaged over different regions. The blue bars are the metrics for all regions. The red bars are for the foreground regions, and yellow bars for the background regions. Clearly, the winner MSMDNet outperformed the other methods in all metrics. We don't show here our baselines, but they are about 10 times worse than these methods. In fact, our LIA baseline is 10 times worse because we got their pre-trained weights on the SynFlow data set and the weights of the fine-tuning on the Kitty data set, and just try to see how it would adapt to a new domain, and it performed pretty poorly. So these plots show the performance of the top 5 methods by range, evaluated on all regions, foreground and the background. So the x-axis shows the depth in meters, the left y-axis shows the percentage of disparate errors, and the right y-axis shows the number of rays, or the number of ground truth information that we have at different ranges, which is represented by the gray bar plots in the background. So all methods started to degrade in performance after about 100 meters. As you can see, the curves going up a little bit, especially for the foreground objects in the middle plot, as we start to have less and less ground truth depth in those regions. All right, so let's finally have a look at some visuals. Before I play this video, let me just break it down. On the top, we have from left to right the stereo image, the left stereo image as a reference, the ground truth depth, the ground truth overlaid with the image, and the winner method. On the bottom, we have the other top 4 methods. So let me play this. Hopefully you guys can see in high resolution. And note how the scene is dynamic, and we have multiple moving objects, multiple vehicles moving around. And most methods estimated this piecewise smooth depth maps, which is pretty cool. So here I paused on a single frame so we can have a better look at this, this comparison. So first thing to notice is that we don't evaluate sky regions, nor we have ground truth for that, and higher objects in the scene. So the methods mostly hallucinated depths for those regions. Still, MSMDNet and SMD stereo seems to hallucinate better depths. Also note that the scene has highly specular surfaces, as in the black truck, which is very challenging for stereo matching methods. Still, we have pretty good ground truth for it, and MSMDNet and Cicero stereo did a pretty good job at estimating depths for this vehicle. The other methods have some artifacts in some regions of the vehicles. For example, if you look at the back window region of this truck, you see that kind of the forefront, for example, just goes through the window. This transparent region didn't perform very well. And interestingly, there is a challenging car reflection on the side of the truck. Hopefully you guys can see the reflection well enough. That seems to trick some of the methods, especially for fun and SMD stereo. It seems that they try to reconstruct the car's reflection, as you can see in the circle red that I put to highlight it. And over here we have the point cloud recovered by our ground truth depth maps, and also for the top 5 methods. So we can have a better look at how the reconstructed geometries look like. So the winner is in top middle. And let me play this. So note how we do not perform any post-processing here. So some regions, especially in the sky regions, might be very, very noisy. But still you can see a nice geometry from the depth maps when we reconstructed. Here's another example where, let me play it. And in this scene is interesting because we have a pedestrian crossing the street. And then you can see that we still have ground truth for it. And some of the methods predicted pretty well. And here I just get a frame of it so you can have a look at the pedestrian. And also we have some regions, for example, in the squared red that I marked. For example, the MSMDNet just estimated pretty well those regions, while others kind of fail because it's very transparent regions from the windows of the vehicles. It's pretty tricky to reconstruct it if you don't have like some smart tricks in your model. And here is the point cloud recovered from the methods as before. So soon you guys will see the pedestrian crossing by. You can see this geometry. And here's another example, which is interesting because we have like this heavy truck also passing by, and we have ground truth for it. And some of the methods can estimate it in a smooth way. And here is just a snapshot of the video. So you can see how, for example, the MSMDNet predicted the truck. And here is the point cloud for it. We can see the nice geometry that we can recover from the truck region, for example. Which is pretty cool. And then finally, let's go over some takeaways here. Definitely some deep stereo methods are still far from being lightweight and fast enough for deployment in, for example, real-time mobile systems. Most methods employ these 3D or 4D cost volumes, which are computationally expensive. But still, that's what we get, the best accuracy so far. Multi-scale features to build the multi-resolution cost volume seems to help for high-resolution input, as shown by the winner MSMDNet. The entropy-based loss is pretty important to give the uncertainties for the predictions, and then we can improve the robustness of the methods. Most methods performed well up to a range of about 100 meters, then started to degrade. So the method should focus on longer ranges as well. Maybe how can we predict better at range? And definitely need more ablation. So for example, we would be very interested in questions like how much does pre-training on synthetic data matter? What happens when we train the model on Argoverse stereo training set only? Before we only have this such a small scale data sets like Kitty. So it was hard to train on like 200 images, but now we have more like thousands of training examples. So it would be interesting to see how it perform without the synthetic data set and more ablations like data augmentations and things like that. And that concludes my part, and I would hopefully I'm on time, and I'm going to hand over to Jagtit.
Awesome. Thanks, Johnny. Let me share my screen. I hope you guys can see my screen. Okay. Hi, everyone. I'm Jagjeet. I'll be presenting the 2021 Motion Forecasting Challenge. So during the course of this presentation, I'll first talk about what's different in the competition this year. It will be followed by some deeper analysis of top 5 teams. And finally, I'll summarize some takeaways from the approaches I've seen this far. Start with, this plot shows the number of submissions we have obtained on the Argoverse leaderboard over time. So the NeurIPS 2019 competition and CVPR 2020 competition, we saw active participation, but CVPR 2021 has seen the maximum participation so far. I'm glad to see the continued interest of the research community in this domain. We'll be using these notations throughout the presentation. So the orange here refers to the focal agent's observed trajectory, red refers to the ground truth future, and green refers to the multiple forecasted trajectories. The three metrics I will talk about are as shown. So I have the min FD, which is minimum final displacement error. It is the endpoint of the best forecast. We have miss rate, which is 1 if min FDE is greater than 2 meters. And we have Brier min FDE, which is the sum of min FDE and the Brier score. So if you have been following the competitions from previous years, you might already know this. In 2019, we had min FDE over 6 forecast as our target metric. Intuitively, it rewards methods that have low endpoint error. In 2020, we switched to miss rate as a key metric, which rewards methods if their endpoint is never too far away from the ground truth. And this year, we use Brier min FDE, which rewards for accurate forecasts as well as accurate probabilities. So far, we have received submissions from 229 teams. And since we announced the CVPR 2021 challenge, 70 teams have submitted during that phase. And this is the final snapshot of the leaderboard. I'll be talking about the top 5 teams here during different points in the presentation. Before we jump into that, this is an important observation I would like to make. So even though in 2021 competition, we're not using min FDE or miss rate as the target metric, the methods still significantly outperform the best methods from previous years. This just shows that methods this year were not just overfitting to a particular metric, they're better trajectory forecasting approaches in general. In fact, the winner of 2019 and 2020 challenge is currently 66th as per Brier min FDE and 19th as per miss rate. Coming to the exciting part, here are our 2021 winners. It was a very close call at the end. As per the position of the leaderboard, we have Team QCraft as the winner, and they will be awarded $2,000. We have 2 honorable mentions. They were selected based on the novelty of their work and how they performed in difficult traffic scenarios, which I'll be talking about later. So a huge congratulations to all the teams involved here. Next up, we'll be briefly explaining the approaches of some of the top methods. I apologize if we are not investing too much time on the methods, but hopefully it conveys the novelty and the highlight of each of the work. So starting with Team QCraft, this team shared their own video of the presentation, which is about 2 minutes, so I'll just be playing that.
Hello everyone.
Hopefully the sound is also there.
I'm Fang Da from QCraft, and we're here to briefly discuss our submission. Our main technical innovation is a new long-range graph attention mechanism for encoding lane graphs in the HD maps. This work is currently in submission for peer review, but we will try to outline the main idea here. The design is motivated by our observation that lanes in urban areas can form very complex arrangements from combinations of basic interaction types such as neighbors, successors, and predecessors. And in these arrangements, lanes would often interact with other lanes that are not directly connected to them. For example, in Argoverse, there are many scenarios where a car finishes a turn and enters a lane that's not connected through the turn. Here's another scenario where a car is about to finish a shallow merge. Here it could be interacting with traffic 2 lanes over to the left. Existing GNN structures such as graph convolution and graph attention would treat these non-local interactions as composition of local one-ring interactions. But these interactions are conceptually different, and such a composition doesn't really make sense. So we need more expressive power to capture the long-range interactions. This motivates us to develop a more flexible graph attention mechanism using the connectivity path between lanes. We find that encoding the HD map using this new graph attention gives us a significant boost across all metrics. Our overall prediction framework is built on top of Uber's lane GCN work. In addition to using the new graph attention we just talked about, we also changed the trajectory classification loss to a negative log likelihood loss on a Gaussian mixture model. And we built a model ensemble using k-means to aggregate the trajectory modes. We find that these 2 changes didn't make a whole lot of difference on ADE and FDE, but they improved the trajectory probability prediction, and so they improved the Brier scores a lot. That's all of our report today. Hello, everyone. Hello,
Okay. So moving to the next team, it's team Stefano Thomas from Hawaii, France. The core of their method consists of predicting the probability distribution of an agent position at a given time in the future, but they do it in the form of a heat map. This allows to represent the uncertainty of the prediction without constraining it to a parametric form. And therefore, it adapts very well to the road network. Using the estimated probability distribution, they designed a deterministic sampling method that exploits the heat map. It provides possible future locations, and thereby it optimizes the coverage. The thing that stands out is how well they do on the miss rate metric. Their miss rate is 25% better than the next best we have seen so far. This is their architecture in detail. They have a CNN encoder, which is used to encode the HT map. The scalar history of each agent is encoded using GRU, and attention layer is used to account for interactions. Subsequently, map features and interaction features are combined, and a CNN decoder is used to produce the heat map. The model is trained with a ground truth heat map consisting of a Gaussian around the ground truth pixel position. They make use of the heat map to sample k number of probable future locations. They design an algorithm that greedily finds locations that are minimizing the miss probability. Finally, usually ensembling various models for trajectory prediction is not straightforward because it could lead to mode averaging, as you can see in the figure. But if you have a heat map, it enables the ensembling with no risk of mode averaging. And that is evident from the figure you see on the bottom. Moving on to the next team from HIK Vision Research Institute. The backbone for the map encoding is lane GCN, which I'll be talking about later. Further, they take motivation from lane RCNN for predicting the goal points. You can see the references of both lane GCN and lane RCNN down there. There's one key difference with lane RCNN though. So instead of doing non-maximal suppression to come up with 6 most likely goals directly, they use goal distribution as an intermediate result. So they predict trajectories for the 70 most likely goals, and then they use a point net based approach to regress to final 6 goals. The last team we are looking at is Team Poly from Waymo. Here's their architecture from Team Poly, which they call multipath plus. At a high level, it takes lane polylines and actor states as inputs and generates Gaussian mixture model for the forecasted trajectories. It has the standard modules for encoding map using polylines, agent state, and interactions. They use several tricks to improve the performance, some of which include using multiple rounds of cross attention for infusing the encodings. They predict trajectories which are kinematically feasible. And one of the unique things about their approach is how they minimized Breyer-Min FTE as part of training an ensemble model. So that was for the presentation of the top 4 of the top 5 methods this year. In the next phase, I'll be talking about the performance of top 5 methods on some of the challenging scenarios that the Argoverse team mined. The first subset we are going to look at is the unanticipated turn. These are the cases where the input trajectory is straight, but the future ground truth trajectory can turn left or right. This is important, or this is difficult because the curvature of the input trajectory doesn't really convey anything about the upcoming turn. So methods need to derive from the map context and kinematic trend. In this example, a refresher on the notations, you see the orange trajectory, which is the input trajectory for the focal agent. The light green ones are the trajectories for social actors. They provide social context to the focal agent, but they're not themselves evaluated on. Blue is the AV, red is the ground truth trajectory, and you see a few green trajectories, which are the forecasted trajectories from the methods. And the numbers next to the green trajectories correspond to the associated probabilities. In this example, the method on the left can't predict any likely trajectories turning right, but the method on the right has. Even though it's a low probability trajectory, it still has a trajectory turning right. The next scenario is those test samples which our past winners have usually suffered on. They're potentially the long tail events, the outliers, the non-compliant actors. The methods can fail here for various reasons. For example, here, the focal agent is literally stationary at the intersection for the entire 2-second history. Since the data does not include the heading information, it is difficult to predict how the vehicle will exit the intersection. So all the methods that I looked so far, they predicted a trajectory which literally exits the intersection in the opposite direction. The next one are the cases where focal agent has a high acceleration or deceleration. The methods need to implicitly capture different reasons for which an actor might slow down or might accelerate. Example here, you see the focal agent crossing an intersection, and it decelerates and queues behind the lead vehicle. One of the methods that is on the right is able to predict that queuing behind and slowing down behavior, but the one on the left is not able to do that. The last subset we have is of lane changes, as evident from the name. These are the cases where the focal agent transitions to a left or right neighboring lane. If you see this example, the input is similar to the previous example, but the actor decides to change lane and accelerate instead of queuing behind the lead vehicle. And none of the methods were able to predict this lane change behavior. This is the summary of the performance of 2021 winner on as per Breyer-Min FD and Min FD on the full test data set on the leftmost, and these difficult scenarios, subsequent bar charts. Some subsets have very high errors on the metrics we chose, and some don't. But solving these cases is imperative to deploying self-driving cars which are safe and reliable. We probably need more expressive metrics for some of these cases, but these plots do convey that there is still a large scope of improvement in motion forecasting, especially in scenarios like these. Finally, I'll talk about the takeaways from each of the top 5 methods. If you're working on motion forecasting, you can consider trying out these suggestions to improve the performance of your methods. One thing that stands out is the emphasis on graph-based approaches for encoding the map information. Argos provides an HT vector map, and teams have come up with clever ways to encode that. Last year, Lane GCN, which is a paper by Uber ATG, they proposed a design which captured the topology and the long-range dependencies which are there in the road network. It had the best min FT in the 2020 competition. This year, 3 of the top 5 methods built on top of Lane GCN. So it is exciting to see how previous methods are helping new methods push the state of art even further. Some miscellaneous takeaways. First, ensembling helps. For heat map-based methods, it's intuitive how to implement, but it is also possible for non-rasterized parametric methods. One of the teams used k-means as part of ensembling. The other team, Poly, that I talked about, they used ensembling while optimizing the Breyer-Min FT. So it's neat to see how different teams have used ensembling as part of their training. Secondly, if the model, you can have the model predict in 2 stages. First, predict the goal, then predict the trajectory condition on that goal. So if your architecture allows it, it's definitely worth trying. Thirdly, put more thought to handcrafted features, particularly if they are relative to the local lane. The multiple papers in the past have shown the importance of doing that. One of the teams this year found that simply adding the velocity along and perpendicular to the lane gives them a boost compared to the Lane GCN baseline. And finally, many teams have demonstrated that it is easy to optimize a target metric as part of the training. So you need not constrain yourself to customary L2 loss or negative log likelihood while training. If you have a particular target metric for your domain, you can think of how to incorporating that as part of the training. That's all we have from the motion forecasting competition this year. And once again, congratulations to all the winners from this year. Thank you. And I'll pass it on to Martin.
Can you hear me?
Yep.
All right. Thank you for inviting me. So hi, everyone. I'm Martin Lee, a PhD student from CMU. I'm really excited to be here to talk about the first streaming perception challenge. This challenge is hosted by CMU Argo AI Center and UIUC. This challenge won't be possible without my amazing collaborators. They are Karthika Sherman, a master student from UIUC, and Yuxiong Wang, a assistant professor at UIUC. So this challenge is developed around a new way of evaluation. On the left, it's a standard evaluation where the nice looking visualization hides away the fact it might take a long time to run the algorithms. Are you guys seeing the videos actually?
It's not great.
Okay, let me try to restart the presentation. Sorry about that. How about now?
There is, oh no, it's actually good. There is also a setting for optimized for video if you have a lot of videos in your presentation.
Okay, got it. Thanks for the tip. All right, so on the left is a standard evaluation where the nice looking visualization hides away the fact that it might take a long time to run the algorithm. On the right is our kind of evaluation where latency is captured and properly penalized. The whole evaluation is actually based on a very simple intuition. So in this example video, at the first time instant, the sensor takes a snapshot of the world and the algorithm begins processing this observation. At the second time instant, the algorithm finishes, but the state of the world has already changed. So the evaluation we used in this challenge is the streaming evaluation. It was introduced in the 12th streaming perception paper, which got the Best Paper Honorable Mention Award at ECCV 2020. So streaming perception is a term for real-time online perception. And what's cute about this evaluation is that accuracy and latency are coherently evaluated in a single metric. So you don't need to manually assign artificial weightings like 0.6 for accuracy and 0.5 for latency. Everything is implicitly and elegantly handled by the evaluation itself. Furthermore, it allows us to measure the full stack performance, including detection, tracking, and forecasting. Let me explain this last point in more details. So our benchmark at time t queries the state at time t. This implies that it's impossible for the algorithms to make use of the latest observation. For example, if the algorithms takes delta t to perform its computation, then to make prediction at time t, it can only make use of data before time t minus delta t. In fact, this is the realistic setting for streaming perception, both in biological and robotic vision. Human vision systems associate the object across time and do forecasting. While human reaction time is 200 milliseconds, athletes are able to catch balls traveling at more than 100 miles per hour. Similarly, streaming algorithms can also track and forecast to achieve better streaming performance. Therefore, we claim that tracking and forecasting naturally emerge under streaming evaluation. Given this observation, we propose two tracks for this challenge. The first is the detection-only track, where we only allow single-frame object detectors. And the goal here is to simplify the problem and let people familiar with traditional 2D detection to participate in this challenge. The second is full-stack track, where we place no restrictions on the method. But most likely, tracking and forecasting will be used to compensate the latency of the detectors. We consider the full stack track as our primary track. One feature of this challenge is that it includes hardware in the loop evaluation. By construction, our evaluation is runtime and thus hardware dependent. One can consider this as a downside, since now using a better GPU gets us a better accuracy, which might complicate the discussion and evaluation. But from our perspective, it is something fundamental to embodied perception. The best algorithm should be intermittently tied to the body or the hardware used in this solution. To create a fair competition, we need to standardize the body. We did this through specifying a specific instance type and a software environment on the AWS clouds. At the end of the challenge, we also require code submission for our manual verification to check if the reported runtime is genuine. So in this challenge, we use Argoverse 1.1 as a dataset, and also we provide our own 2D bounding box annotations. There are 1.3 million boxes in total, a number comparable to that in MS COCO. We annotate densely at 30 FPS on high-resolution image frames. This is a challenge dataset, primarily due to the small sizes of the objects relative to the large size of the image size. As we can see in this dimension distribution plot, while there are very large objects, most objects are very small compared to the image resolution. Similar with other data sets, we also have a long tail distribution over the classes. This can be another technical difficulty for the participants. So for this very first challenge, we have 18 teams participated and 4 teams made the final submission to the test set. This is the demographic distribution of the participating teams. We can see many participants from Asia. On the right is the academia versus industry breakdown, which is about half and half. Okay, now comes the most exciting time. We're going to announce the winners and give out the awards. Let's start with the full stack track. So the first place is Team BaseDat from MegaV Technologies. Congratulations. And the honorable mention award goes to Team StreamDat from University of Science and Technology of China and Peking University. So this team scored the second place on the leaderboard of the full stack track. Okay, now for the detection only track. The first place is once again Team BaseDat from MegaV Technology. Congratulations again. The honorable mention award goes to Team Chanakya from Microsoft Research India, and they have developed a reinforcement learning method for tuning the trade-off. And you will see in the presentation in a bit. So from all the technical report submissions, we actually found some interesting technical observations. First, many participants has adopted this YuloV5, and they built their methods on top of it. That suggests that YuloV5 is a nice starting place for efficient object detection. And also, many people adopted Streamer, which is an algorithm introduced in the TWAS streaming perception paper. It's composed of dynamic scheduling and asynchronous common filter forecasting. It helps to boost the performance of the full stack track. Also, we noticed from the report that reinforcement learning can be used to dynamically determine the detector and the input scale. So that means you don't need to fix your detector throughout your entire inference. And all technical reports will be available on the challenge website. So now let me welcome the presentation of the first team, BaseDat. They won the first place in both detection only and full stack track.
Hello, it's my pleasure to introduce our solution for streaming perception challenge. We are a base detection team from MegaV Technology. This is our team. I deeply appreciate my teammates' hard work on this challenge. The streaming perception challenge focuses on realistic problem setting of an autonomous driving scenario. We think it's an interesting and valuable setting both for research and industry. The goal is to build a fast and accurate 2D detector for autonomous driving scenario. The larger model typically has higher performance. However, following the rule of streaming accuracy, longer inference time will introduce more serious mismatch. In our empirical analysis, using the I+1 ground truth to calculate the final AP for the I's prediction, can reintroduce 10 AP performance drop. More serious mismatch means unacceptable performance drop. Thus, in the detection-only track, our strategy is to build a real-time powerful detector. The best trade-off is to make the total inference time slightly less than 33 milliseconds. There are 2 common pipelines, RCN and YuLo. We first take the HTC as the initial solution, along with the ResNest 269 to achieve strong offline performance. However, such a model requires 0.5 seconds for inference, and many customers' operators require extra efforts for deployment. Thus, we adopt the YuLo model for this challenge. Specifically, we propose a new model called YuLo-X. We use the same backbone as the YuLo V5 LP6. It was nothing that we replaced the anchor-based UV5 detection head with anchor-free head and adopt advanced label alignment strategy (OTA) for training. Indeed, UX achieves about 1.5 higher AP than current UV5 on Coco. More details of UX will be released soon. For training, we first adopt the strong mutation as UV5, such as message, mix-up, EMA, and other techniques. We also use Coco dataset for pre-training. Furthermore, we use multiple autonomous driving datasets for fine-tuning to boost the performance. To speed up the inference, we fuse pre-process, inference, and post-process into one function and use TensorRT to optimize the whole inference process. We report detailed performance here. Adding validation for fine-tuning, we finally get 51 streaming AP on test set. We also report the relationship between inference image size, latency, and performance. Even equipped with the real-time algorithm, there exists 10 AP performance drop. We think leveraging temporal information for forecasting is a promising idea and is worth exploring in the future. Thanks to the hosts and audience, and wish the WAD a great success.
Okay, so the next presentation is from Team Chanakya, who won the Honorable Mention Award for the detection-only track.
Hello everyone, I'm Anurag Ghosh from Microsoft Research India. Today, I'm going to talk about our approach for the streaming perception challenge. Streaming perception is a challenging problem as imposed real-time constraints force methods to balance accuracy and latency together. Detection, tracking, and forecasting emerge as natural modules to enable streaming perception, but even within these modules there exist numerous choices and trade-offs, which make searching for optimal performance on the Pareto frontier difficult. Finding these trade-offs is difficult as multiple decision dimensions exist. The choice of the detector, tracker, and forecaster, the input scale, along with model-specific parameters, such as number of proposals in a two-stage detector, are some of the configurable decisions. This decision space explores combinatorially and is tough to manually optimize. Moreover, a suboptimal configuration can significantly degrade performance within the same latency budget, for instance, around 3 MAB points on the Argoverse dataset. Our approach consists of leveraging reinforcement learning to learn an execution policy that makes these trade-off decisions dynamically. We formulate the policy learning as a novel, deep contextual bandit problem, and our reward design balances both accuracy and latency. Firstly, we generate a context vector for a given frame. We employ tiny regressors that predict telemetry information such as the good scale the model should run at, along with other statistical scene aggregates. This context is then given to the agent, whose Q function predicts action values for each sub-action, which are then explored or exploited by the multi-arm bandits. Lastly, the predicted action is used to change the configuration and the reward is given to the agent. We now compare the results across various static and dynamic offline execution policies against our approach. As we see, our approach improves runtime streaming performance on two public datasets by around 10 to 15% on a designated hardware. It should be noted that the performance improvements are complementary to improvements in individual perception modules. For the streaming perception challenge, we begin by considering the public baseline, the meta-detector streamer. We then attempt to replace ResNet models with recently released twin transformers, which exhibit higher accuracy yet higher latency. We employ our RL approach to learn the trade-off between different model choices, inference precision, input scale, and number of proposals. As you can see, a fixed policy with twin transformer mass Carcinoid was able to improve the baseline by 39%, and our approach was able to select the optimal policy to obtain a 47% improvement over the baseline. To conclude, we have presented an approach that automatically learns trade-offs for streaming perception via reinforcement learning. Please visit the link to read our preprint for more details. Thank you.
All right, that's everything for the streaming perception challenge. I would like to thank all the participants for their hard work, and also thank you for listening.
All right, I'm gonna take over again and share my screen. Yeah, great job. It's so cool to see. Sorry, somebody saying something? sorry, what was that? Okay, I guess I'll continue. All of these challenges use Argoverse 1.1, which we released 2 years ago, almost to the day. Oh my goodness, the screen just disappeared. And Argoverse 1.1 is, it's been a great success, but it has some limitations, some of that I've highlighted here. The sensor data set, which was the basis of our stereo challenge and the streaming perception challenge, has a diverse taxonomy, about 15 different categories, but really most of those categories are not very well represented. So when we quantitatively evaluate on tracking and detection, we only use 2 or 3 of those categories just because the sample size is too small. A plus is that we have stereo imagery, which is rare among these modern data sets. The forecasting data set has seen a lot of use, but there's not a lot of information about each actor in these scenes. They're very abstract. You just have a centroid. You don't even know the category of the object. The time horizon's a little short, also 2 seconds of observation, 3 seconds of future, and you don't know traffic control measures like traffic light state while you're trying to forecast. And the HD maps that underlie Argoverse have lane center lines only. So when you see visualizations that seem to have full lanes, it's because some average lane width was used to sort of pop up that lane, which actually works very well in general, but some lanes are not quite, exactly 3.5 meters wide or something like that. So I am super pleased to announce Argoverse 2.0, which will be released soon, that spans 6 cities instead of the 2 cities in Argoverse 1.1. And it, for each of the data sets in Argoverse 1.1, they are, I think, improved dramatically. And I'll walk through them individually. And there's also 2 entirely new data sets that I think don't really have equals out there yet. Let me start by talking about the sensor data set. Let me put the quality up on this so it's actually visible. So we'll have a new sensor data set with 1,000 sequences instead of 100, so making it on par with new scenes or Waymo. But again, I think we'll be able to use a larger taxonomy and actually have enough objects of many types so that we can evaluate on 15 plus different categories, more than new scenes or Waymo do, for example. We are additionally introducing an unlabeled LiDAR data set, which is simply unsupervised LiDAR on top of HD maps, though, but without annotations. But there will be 10,000 plus of these sequences so that we can explore self-supervised learning of LiDAR representation. Self-supervised learning has been extraordinarily successful in things like natural language with these new GPT models. And it's been very successful in images. And it seems logical that we should try that in LiDAR space as well, but there's not really a data set out there which just has a ton of actual diverse self-driving LiDAR data. So we expect this to be the first. The forecasting data set will be richer. We'll have an object taxonomy now where you know whether something is a car or a bicycle or a pedestrian. We'll have lane graphs that have actual lane extents and not just center lines. And we'll have traffic light state. We'll also have a longer time horizon. Show one more forecasting scenario here. That's the same one. In this case, the agent being forecast as a bicycle, and it's weaving between cars and then making a turn. You can see pedestrians as well in the scene. And you can see that the lanes are not, neatly sized lanes either, and the new map representation captures that. And the final new data set is an actual data set of map changes. Level 4 autonomy efforts rely on HD maps that have lane level geometry, but lanes change in the real world, and it's not super rare. Here's an example of the AV encountering a new lane arrangement. And we have hundreds of these scenarios in a new data set so that you can evaluate how well you can tell if your HD map has gone stale or not. And all of these data sets will share the same HD map representation, which is richer than the one that we used for Argoverse 1.1. It has full lane geometry, it has crosswalks, it has lane marking information about what divides the lanes. It has ground height like the previous Argoverse, but it's higher resolution. So we're excited to be able to announce that finally, and we look forward to people using it in maybe future competitions in a venue like that. Okay, that's all for the Argoverse team. Thank you all for listening.
Thanks, James, and also you're spot on time. So congratulations to all to such a successful challenge. And I'm really looking forward to work with Argoverse 2.0. I saw that Boli is already among the participants.
Yes.
Hey.
Hello.
Okay, perfect. Can you share your screen?
Yes.
Okay, perfect. Good. It's an honor to introduce Boli. She's an assistant professor at the University of Illinois at Champaign, where she leads the Secure Learning Lab, which works on making machine learning and algorithms more robust, private, and efficient, as well as interpretable. So I'm really looking forward to your talk at this very interesting intersection between autonomous driving and kind of security, something we really have to figure out to make autonomous cars reality. Okay, the stage is yours. Thanks.
Thank you. Thank you for the nice introduction. Yeah, hello everyone. It's really my great honor to share my research about secure learning for autonomous driving in adversarial environment here with you. And I'm Boli from UIUC. And in this talk, I really want to share some research from a little bit theory and in practice how to make like autonomous driving more safe against different types of adversarial behaviors on different levels. So we'll dig into that in a minute. So first of all, we see that autonomous, like machine learning AI has been ubiquitous in the world. It has been applied to different domains in our daily life. For example, of course, autonomous driving, intelligent medical healthcare, smart city, etc., and a lot of safety critical area as well. But we can see the very interesting and important part here is that even though it has brought a lot of convenience currently, the machine learning or AI technique itself also brought a lot of security and privacy concerns. For example, in 2016, the Associated Press Twitter account was hacked with phishing emails, spreading the rumor that the White House has been attacked, which actually triggered the autonomous trading bot to dump a large amount of stocks and swipe about $136 billion within seconds. And of course, we always hear a lot of news about autonomous driving with potential accident because of the misrecognition of certain objects, such as bridge, such as trucks, or even pedestrians, right? So how we can dig into and understand such adversarial or even just real world attack scenarios better and try to understand and improve the robustness of it. And more importantly, I want to emphasize to say certify the robustness or safety for certain learning pipelines or learning predictions or decision makings is quite important in my opinion. So overall, in general, we can see we are still living in a very friendly world, right? So basically, we have a lot of convenient platforms to help us develop different scalable like machine learning pipelines or tools or models with our data. And but still, we are living in an adversarial environment. So a typical machine learner still have a very hard life to develop so-called secure or robust machine learning models. And therefore, as we mentioned, we really need to understand the like different types of attack strategies or threat models better, and therefore improve or develop robust or safe machine learning pipelines, for example, for different applications, including autonomous driving. And in general, we can see, for example, in our lab, our main goal is to develop the certifiability, which is very important in addition to empirical robustness, right? Robust, private, and expandable machine learning paradigms for different real-world applications. For example, take the general machine learning pipeline as an example. We actually want to definitely look at different types of adversarial attacks during different components like training, testing, deployment phase, or based on such vulnerability identification to look at how to improve the robustness or even certify the robustness of it. And of course, we also want some explanation to better understand why different types of prediction is made, and also different like how to protect the data, for example, collected by autonomous driving vehicle driven on the road, right? How do we protect such privacy and still can use the data to train our models? So in this talk, I'll mainly focus on the potential attacks as an example to give some examples on different levels of the attacks, and then talk about a little bit how to improve the robustness, and not to the extent of can definitely avoid such like a collision or accident yet, but hopefully can contribute to some ideas or promise that to improve the safety of the autonomous driving vehicles. So more concretely, we can see, given like when we talk about autonomous driving vehicle, at least there are, on the very high level, there are two levels, right? One is a single vehicle and one is based on the traffic scenarios. And given the single vehicle, there are several components. For example, perception, of course, is very important. And in our awesome challenge, we just show there are lots of good algorithms that can achieve even outperform human behaviors for, say, object detection or segmentation. And also based on such recognition and prediction, we will be able to make planning, control, and other decision-making for the later component, right? And in this talk, I will mainly focus on three levels, like the perception, the planning, and the traffic level, to give some examples about what the attack could look like against this component. And I will not dig into detailed techniques for them. And later on, because we want to save some time, for one types of defense method against such attacks. So that will be the whole talk. So first, let's look at some examples against the perception sensors in terms of attacking them. So first, we can see, I think many of you have seen such example from one of our work showing that under different physical conditions, for example, different rows here shows different physical conditions, including different angles, distances, and like lightning conditions, and different row show different, different color shows different types of perturbations in physical world. And we can see all the stop signs in these slides are misrecognized as a speed limit sign 45, which is the adversary target, which means that you will never stop at this sign, which you can see can cause severe consequences. And such right-hand sign here will be misrecognized as a stop sign based on certain optimization attack algorithm. And this is a static evaluation analysis. And of course, in a dynamic environment, we can see when we drive a car towards this sign, on the left-hand side, it's one of the perturbed sign we showed in the last slides. And on the right-hand side, it's a control experiment with a vanilla stop sign. And we can see from the caption that when the car driving towards this sign, it's consistently misrecognized the sign itself as a speed limit sign, but the control experiment can correctly recognize it. So this shows how severe or dangerous it could be, even with such simple like planar road sign as adversarial object in real world. And in addition to this classification model, as we mentioned, of course, different types of object detector models is very important and usually used and equipped in autonomous driving vehicles. And here, this example shows that still with these types of perturbed real-world stop sign, we can see even though all the rest of the object can be recognized, the stop sign itself cannot be recognized because of the perturbation on it. But clearly, human can see it. That's make it more stealthy, and human cannot identify it as adversary and replace it in real world. So that makes it quite dangerous. So such recognition only happens when we get very close to the sign itself and it recognizes the letters. But of course, we on purpose do not want to cover the letter. Otherwise, it doesn't it also fool human, right? And of course, here is a white box attack against YOLO. And you can also consider the transferability in a different environment, meaning that even we don't have access to the object detection model itself, it's still possible that you can never recognize this stop sign until you go to very close to the sign itself, which is too late for a car to stop. Right, and such like a physical attack, the stop sign is actually currently exhibited in the Science Museum of London. And if someone have opportunities, you can go to and check out. I think it's quite interesting, and it also brings up an important problem that shows people already recognize that this is indeed a potential severe consequence if later on we can largely deploy, for example, the autonomous driving vehicles for different purposes. Right, and after this work against the different classifications, object detections and etc. So people actually published several papers showing okay, maybe one types of perception system is not robust. It can be attacked either in white box or black box settings. So maybe multi-sensor fusion is a way, right? If we have different types of sensors and we fuse them together or aggregate the result together, maybe it's safer. And this is interesting. And we actually take a look at it with our awesome collaborators from UCI and Baidu. And actually we can see, we can generate, build up a pipeline and actually consider different types of sensors, including LiDAR and cameras, and generate kind of like adversarial 3D point clouds against the LiDAR, and also manipulate the texture and the colors onto the object itself against the cameras, and fuse such result together, and also minimize the distance between the like a vanilla object, which is a cone here, which is very common on like road or even on highway, right? And then make it stealthy and optimize over this whole pipeline end to end. Like even in real world, some pipeline is not, end-to-end or differentiable. We can approximate the model and with certain differentiable models. And we actually show in physical world testing, such approximation and attack is actually quite successful, unfortunately, right? And with a simulation environment against the different types of simulation, we can see in this row, it shows the adversarial object. You can see this car can never recognize this object which we generated, and then it go past it, which could cause some consequences, right? But in this control experiment, the car will stop as it can recognize this object on the road. And even more interesting, as we just mentioned, we can test this object, which is 3D printed out, and put it on the road and drive a car towards it, which is based on the Baidu Apollo system. And we can see against this adversarial object in the LiDAR system here, actually there is nothing can be recognized as an obstacle here. But if in the control experiment, if we put a box of similar size towards this position, we can see the LiDAR can recognize this green box here, showing that in the control experiment, LiDAR can recognize such a box with similar size. But if we optimize the 3D object in certain way, then it can be misrecognized by the multi-sensor systems, including LiDAR, camera, or even others. So this shows that these types of multi-sensor systems, fusion systems could also be potentially like vulnerable against some motivated real-world adversary behaviors, right? And the more interesting phenomena like simulations and examples can be seen from the webpage. And like towards so far after we identify such vulnerabilities, we actually have shown such vulnerability to different autonomous driving vehicle companies, and 11 of them have actually replied and start to investigate, which is a good news, to improve the robustness of their system against such potential attacks. Right. So this is some examples from the perception perspective of a single vehicle. And next, we can take a brief look at the planning and control pipelines, especially in terms of the reinforcement learning pipeline, and see whether in the whole like end-to-end reinforcement learning pipeline in real world, whether such models can be vulnerable or not, and where or what types of like adversarial attacks or behaviors could happen to manipulate such systems. So take a like a high-level brief look at the whole loop of the like reinforcement learning pipeline. We can see, of course, given the environment, we can have different observations, and the agent, for example, ego vehicle can take the observations and make certain decisions or for the actions, right? And here you can see the observation itself can be attacked in the sense of, like we just mentioned, either stop sign, or we have different colors of the wall, like some dots put on the road, etc. And not only for single frame, but also for a series of frame, it could be attacked as well consistently. And of course, based on the reward estimation, the action, like a decision, it can be attacked as well. And more interestingly, we didn't expect that, but actually we find that even for some small environment dynamics, including like the weights of the car or the friction on the floor, of course, it can actually derive targeted attacks for by manipulating such environment like dynamics or environment coefficients, which is a little bit surprising. So for example, here in the simulation environment, on the right-hand side, it's a virtual environment by manipulating like the car weights a little bit, which is still reasonable car and cannot be identified by direct, say, statistical testing. And actually, you can see on the right-hand side, this car already can achieve kind of the goal to hit the wall. So the goal of such attack is to let the vehicle hit the wall. So that is to say, you can see that even by manipulating the environment like dynamics a little bit, such control pipelines can also be like a fooled in certain way. And later on, we will discuss a little bit about the defense against such like reinforcement learning pipeline as improved robustness or certified robustness of it. So next, based on this, in addition to the single vehicle against a different component, I want to take a look at the example of traffic level. I think currently lots of work focus on the single vehicle behavior and the decision-making process, etc. But on the traffic level, we're already seeing potential severe or like adversarial behaviors, even though it's may look very benign to human, but it can like derive targeted adversarial behaviors. So I think it's very important to discuss at the early stage about what could be the potential severe consequences on the traffic level as well. For example, here, this is a simulation from the Sumo based on the data, real-world data collected from the highway near Nashville. And it's a collaboration with our awesome collaborators from Vanderbilt. And we can see here with like an agile vehicle that is equipped with ACC, the control following the front car. And what we do is just have a simple, like a slowdown based on certain conditions. For example, you can hit the brake for this many of times with this many strengths. And such attack can be easily realized by manipulating the CAN bus software, which we have done, or just you have adversaries sitting in the car and hit the brake. And the interesting phenomenon, we find many, but one thing I think worth to bring up is that, for example, if the under different driving speed conditions, if the driving speed is slower, the string instability or the speed fluctuation actually is more severe by doing such potential slowdown for such vehicles, which will cause all the, say, if all the vehicles are autonomous, right, then everyone, if the car have one brake and every car in the later part will have such brakes, and then the string instability is actually quite severe. And if the speed is slightly higher, the string instability is actually surprisingly lower. And one potential reason could be that with high speed, the distance between cars is actually larger than the low speed scenario, right? So maybe that's actually the case that why the string instability is less severe than this one. But of course, under this scenario, the accident could be more severe than the low speed scenario. So more work definitely need to be involved to understand this and try to avoid such speed fluctuation or such attacks. But one thing we find so far is that such attack, like for example, the slowdown on the traffic level, is very stealthy and very hard to be detected. We have tried all like the potential ways, for example, looking at the patterns of traffic and use generative models to detect it, or use the features of the speed and the distance between cars to train a model to identify such attack. But still, the detection is not as good as we expect. So such attack itself is quite stealthy, and how to identify them and defend against them is indeed a quite important problem, in my opinion. And in addition to this, these types of traffic level, we can actually even just generate the adversarial traffic scenarios or traffic scenes. And this is quite interesting. So basically we can see over years, the semantic segmentation based on different models has been improved a lot, right? But here we show it's possible to generate the whole adversarial traffic scene, which satisfy the real world constraints or knowledge. For example, we know the cars are always following the same line on the same direction, etc. We'll always enforce the traffic scenario to follow the real world constraint we have. And therefore it can be severe, adversarial, but very realistic, which is a very good scenario to test the robustness or safety of the autonomous driving vehicles. And this is collaborated with the awesome student from CMU. And one simple example we can see is that we can incorporate the knowledge I just mentioned. For example, the cars should follow such certain traffic rules or scenarios, and then incorporate that into the tree, and then use this types of tree structure as a generative model to generate the scenarios. And let me show some examples here. For example, compared with the standard, say, point attack or pulse attack, which are actually not quite realistic, because if we attack the point clouds, you can generate some object or positions which are weird, right? But if based on the scene attack, actually you can follow certain rules. For example, here is the rules we use to satisfy the real world scenarios, and therefore to make sure it's not only attacks or adversarial, but also can be realistic in real world. And we can see that such attack actually can attack the very state-of-art point cloud segmentation with high attack successful rate, and also with very high transferability, meaning it's find the very compact regions that can generate such adversarial behavior, which actually is severe for different types of models, and attack along them effectively. So this shows that indeed, from different levels, as we have already shown some example on the perception, planning, and even a traffic level, either slow down or on the high level traffic scenario in an adversarial way, it can always attack the whole pipelines or autonomous driving behaviors. So that sounds quite pessimistic, but basically what we really want to ask based on the examples we shown before is how to defend or ensure the safety of AV in adversarial environment that we mentioned, right? Of course, there are many work have been done in this area, including some empirical method to improve the robustness. But one drawback or limitation is that such defense or detections can always be attacked again by attackers. Assume the attacker knows your detection method, and they can do something else to attack it again, which always form a cat and mouse game in security domain, right? And therefore, a line of certified robustness work are so far very promising and develop very fast. For example, the high-level goal for the certification for robustness or safety is that you can give the lower bound of the accuracy for certain tasks you want to do, either perception, prediction, or control pipeline, action prediction, etc. You can give the lower bound of it under certain adversarial constraints. For example, the adversarial behavior should satisfy certain magnitude constraint or whatever constraint. So this is quite promising, right? Because once I can certify it, I know this vehicle will only with 99 accuracy lower bound, then I'm quite satisfied to use it, right? But if it's only empirical, 99 accuracy based on the existing test data, I still will doubt based on other domains or other test data whether it still can achieve such accuracy, right? However, so far, the certified accuracy itself also have one limitation, which is the considered perturbation constraint is very conservative. For example, it only allow the perturbation, say, within L infinity or L2 norm with a small distance or magnitude. That is not quite realistic yet in when we want to apply such certification in real world, right? And here I want to briefly introduce one types of method to certify the end-to-end robustness for the machine learning pipeline based on additional information. So now, so far, we always learn our machine learning model or train our pipeline based on pure data-driven method. But of course, there are a lot of information that cannot be modeled by data yet. And all the examples we've seen before, like the stop signs and etc., you can see for human, we are not attacked, right? But for like models or autonomous driving vehicles, it's attacked. So there must be some additional thing, for example, the domain knowledge or inference of human that make it more robust. But you know, machine learning model so far haven't incorporated that yet. So whether there is a way to incorporate it. So I will present one types of work or pipeline to incorporate it. I think there are additional other ways to do it. And I think that's a quite promising direction we can think about as well. So basically, the way to incorporate the domain knowledge, in my opinion, is that we can still train a lot of statistical models, for example, neural networks, right, which guarantee the benign accuracy. And then, given the input data, we can give it to different neural networks. But instead of directly ensemble them or aggregate them, we compose them with a reasoning component, which can be represented as probabilistic graphical models like Bayesian networks or Markov logic networks to make the inference. And the inference connection here represents the knowledge. For example, a cat belongs to an animal category, or for example, a stop sign should be of octagon shape. It could not be of other shapes, right? Based on such phenomenon, we can actually build this pipeline and certify the end-to-end certification. The certification definition is like this. Basically, we want to bound the change of the prediction probability, marginal prediction probability, even under certain perturbations. And such perturbation could be of high magnitude or of real world. And a little bit theory is that, of course, this is very hard to make inference based on a probabilistic graphical model is sharply complete. And but the interesting part is there are a lot of opportunities because there are structured models, there are interesting functionalities we can leverage to improve the robustness or certify the robustness of it. So of course here we can do something to approximate it and prove we can do a p-time algorithm. I will skip that part and give an example of based on the stop sign we mentioned before. Now we can see how we can defend against say the physical attack or whatever attack we have seen so far. So basically you can see given a stop sign, now I no longer use a single say neural network model or whatever machine learning model to make prediction. I still use one model, which is, we call it main sensor, to predict whether it is a stop sign, right? But I use a lot of other auxiliary sensors to predict other knowledge. For example, whether there is a stop pattern in it, or what's the color of it, or whether what's the shape of it, right? And there are two types of knowledge we consider, which can be represented as a first order logical rules. For example, if there is a stop pattern, you can infer it's definitely a stop sign. Or if it's a stop sign, it is indeed definitely an octagon shape. So two directions, right? And based on such knowledge, we can have some nice theoretical result guarantee to show the lower bound of this pipeline can be guaranteed by considering the weights learned from the inference pipeline. And some empirical result we show is quite interesting in the sense that we all know there is a trade-off between benign accuracy and robustness, right? But based on this pipeline, because it has additional information, we can see such pipeline have actually high benign accuracy as well, and of course high robustness as well. So it relaxes the trade-off between the benign accuracy and the robustness. It doesn't hurt benign accuracy, but it's improved the robustness a lot. So the x-axis here shows all types of attacks. There are 46 types of attacks. Some are physical attacks we have seen, like the stop sign. Some are unforcing attacks, common corruptions, etc. So you can see this is attack agnostic and could be quite robust against it. So based on such examples, we can see that indeed security and privacy problems are very common for different machine learning paradigms, especially for safety critical applications. And only beyond that data may be still dangerous, and using some knowledge may help to improve the robustness of machine learning pipeline. And they'll have some libraries you can play with about the robustness. And yeah, that's all my talk. Thank you, everyone. Happy to take questions.
Hey, Yeah, we got actually one questions regarding, I think it was the first part on reinforcement learning, where you you had the tax on the dynamics. How basically, can you maybe elaborate a bit more what you mean with attacks on the dynamics of the system? Are you basically changing the physics, or how is the attack really working?
Yeah, exactly. That's a very good question. So yes, there are a lot of dynamics. For example, the frictions of the floor, the color of the wall, like the weight of the car, and different types of things. We view such as physical dynamics. And in this particular example, we only change the weight of the car, and then it shows some severe consequences. Of course, this is optimized, so it's backpropagated so that the weight of the car can be changed in the sense to achieve the goal, which is hit the wall here. So this is one type of physical dynamics. And there are other, for example, friction. We can expect that if we change the friction on the floor for certain sections, then it should also induce certain behaviors, adverse behaviors. Yeah.
And actually, one very quick one was probably, you said that there are these kind of certified networks. What is kind of the computational penalty you need to pay?
Yeah, that's a very good question. Indeed, the computation could be high. I have one slide showing that if actually we certify, I didn't show it because of the time, but basically we want to certify the cumulative reward for different reinforcement learning algorithms. And you can see we can only run relatively low weight games, for example, Pong or Freeway, etc. But for very long episode games or even like real world autonomous driving, indeed that's expensive because we have expensive sampling and smoothing to do the certification. So that's a good question. It will increase the cost, but how to reduce it is actually indeed quite interesting direction to think about.
Yeah, definitely. Yeah, thanks a lot, Bo. It was a great talk, and it's always nice to have you here at the workshop.
Yeah, thank you.
And so it is actually my pleasure. Adrian, is the screen sharing actually working for you?
Give me a sec.
Then we can first solve the technical issues and then do the introduction.
I think it works, no?
Yeah, it works. Perfect. Okay. Yeah. It's an honor to introduce Adrien Didon. He's the machine learning research lead at the Toyota Research Institute. And he really tries to scale up machine learning for robot autonomy. And so, yeah, I'm looking forward to your talk, and the stage is yours.
Awesome. Thank you. Thank you, everyone. It's a pleasure to be here. So yes, my talk will be about how we do self-supervised learning for 3D vision and applications like autonomous driving, but also robotics in general. So just TRI, we're the Toyota Research Institute. Our mission is to develop automated driving. And as I mentioned, not just that, but also robotics and other human amplification technologies. It's not just about automation, but it's about also the human in the loop. We do a lot of cutting edge research published at various venues like CVPR with a large practical impact because we have many transfer opportunities. So as I mentioned, whether for cars or robots, we do things around scene understanding, self-supervised learning, which I'll talk about today, simulation auto-labeling, behavior modeling, learning for planning and control. So an example of a scientific challenge we are working on is depth estimation. For those of you that are not familiar with it, it consists in taking a single RGB image or multiple RGB images, feeding it through a depth network and predicting the depth, which is the per pixel range, how far objects are in the world. Now, a natural question in the autonomous driving world, where LiDAR is available very frequently, is a question: why would you care about molecular depth at all for driving and robotics? And the first answer is because camera is the most common sensor, as you all know. The other interesting point is that even if you have LiDAR or multiple different cameras, typically for self-driving applications, they are arranged, for instance, around the car. And so they might have a very wide baseline, which breaks typical stereo methods. And the other good reason in multi-camera or multi-sensor rigs is that redundancy. As we know from the Byzantine generals problem, you need multiple ways to arrive to the same solution, for instance, to be robust, including as the previous speaker was talking about. And finally, from a research standpoint, if you're looking at 3D detection from images today, monocular depth is the current major bottleneck, and why it's so far behind LiDAR 3D detection, for instance. So a key research question that really animates us is, can we get robust 3D vision thanks to large-scale self-supervision? And here's an example of what we're able to achieve. And in particular, what you see here is on the upper left is an image fed into a network that produces the depth map on the lower left. And we can actually reconstruct the metrically scaled point cloud, so points in 3 points in meters. And that's because we're using projective geometry as a source of self-supervision to predict the dense depth of a scene from a single image. Note that for those of you that are familiar with self-supervised learning, this is very different than your typical ImageNet self-supervised learning, because here we're not just pre-training for a task, like not just representation learning, but we're actually self-supervising the target task itself, meaning after self-supervised learning, the network produces the target output that you want, in this case, the depth. So we've done a couple of different papers on that, and one that we're particularly proud of is called 3D packing for self-supervised monocular depth estimation, which we covered last year in a CVPR or oral paper. And we presented the network, it's called PackNet, that you see here, this little encoder-decoder network, which is learned via the view synthesis approach of Zhu et al., which is called SFM learner. So in the SFM, structure for motion setup, so only from raw monocular videos. And basically, it's summarized in this diagram that you see on the left and the reprojection equation. For those of you that have taken basic camera, the pinhole camera model in your computer vision classes, you should recognize this equation. And our key contribution here in this paper was in replacing pooling and upsampling operators, which are typically done in the encoder and decoder, respectively, of those networks, and replacing them by learning compression and decompression modules that we call packing and unpacking in order to preserve details that are important for reconstruction. Because here you really care about like reducing the amount of photometric ambiguities, which means like reducing the areas of your loss that are like not giving you clear supervision for your model. And one way is to preserve details as much as possible. And one of the things that was interesting with this work was that it was the first, to our surprise, self-supervised method that was outperforming supervised learning on this task. And we've since then improved it. You can find code and data online for this. We're also organizing a workshop and a depth estimation challenge using our dataset called DDAD, Dense Depth for Autonomous Driving, which is happening at CVPR on the 25th of June, so this Friday, the last day of the conference. So as I mentioned, we've been extending that work in multiple different directions, actually, literally. One paper that we just recently put on archive is called FSM, for full surround monodepth. And the idea is the following. Most of the monocular depth or the depth estimation networks you're seeing, even 3D detection, is focusing on just the front camera, a single camera, single image, just looking in the front. But obviously, for driving, you need full situational awareness, so you need the full 360-degree understanding of the world. And as I mentioned before, why is it hard? Well, it's hard because you don't have like too many sensors. There's some redundancy, but you minimize it for cost reasons, obviously. And so what typically ends up happening, like in our cars, for instance, you have 6 cameras and they have really a minimal overlap. And this is really quite common in practice. So this is why we've been studying this problem and proposed this paper, full surround monodepth from multiple cameras. So here, for instance, is an example of 6 cameras taken at the same time, so time synchronized. This is actually from the new scenes data set. As I mentioned, this configuration is quite common in self-driving. And what we're able to produce, so what you see here in blue, the little blue dots that you might have a hard time seeing, represents the LiDAR points that are in the overlap between cameras. So they really represent the overlap between cameras, which is very minimal. And obviously here you have a very wide baseline, clearly not frontal parallel, generalized stereo problem, which is really difficult. And yet we're able to obtain with a single network the 360 point cloud that you see on the right. And the key insight to get there was when you're doing self-supervised learning for a monocular depth estimation, as I mentioned, you do the view synthesis approach, which is you're reconstructing a past frame from the present frame by predicting the depth and the ego motion, and then using this rigid warping to basically reconstruct the past frame from the current frame pixels. Here, we're generalizing this idea to spatiotemporal view synthesis, where we're leveraging a general spatiotemporal context. So what it means is that in typical stereo, you have two frontal parallel images. You reconstruct the left from the right, or vice versa. And they need to overlap a lot, which is a small baseline. But here, they're not overlapping enough. So you can't really recreate, let's say, an image from the second camera from the first camera, because they overlap too little. And so instead, you can reconstruct the image, let's say, from the second camera using the first camera at a different time. And so really, we're generalizing these spatiotemporal relations and leveraging that to learn a single network for all the cameras by reconstructing from different time instance and different cameras. We're adding a couple of different details, which I encourage you to check the paper. One is multi-camera pose constraints, and one which is actually very surprising in its simplicity and effectiveness is just masking, which to make basically to ignore some parts of the loss, which are wrong. And we know, for instance, because of some self-occlusions, which is also common in robotics when you have a mobile manipulator that's hiding part of your field of view. There's many results in the paper. I encourage you to have a look at it. We're also looking at the ablations of these different components. That's about it for FSM. How well does it work? So here, what you can see is 6 cameras from our theorized DDAT dataset. And you see the 6 cameras, the 6 depth maps produced, and then the point cloud, the 360 3D point cloud. And again, because here we're knowing the extrinsics, so the relation between cameras and calibration, we have some notion of metric scale. So actually our point cloud is metrically scaled. So meaning we feed the 6 images into a single network, and it produces 360 point cloud in meters. And that's consistent across cameras, even though they have very little overlap. All right. So one thing that's pretty neat in all I've shown you so far is that we can rely on prior knowledge from geometry to self-supervise, because we know the reprojection equations. But that's actually, and we assume that this reprojection equation is correct, because that way, if we make a mistake in the view synthesis, it's not because geometry is wrong, it's because the depth network weights are wrong, and backpropagation will adjust these weights to make it agree with geometry. But the problem is that geometry might be wrong, because everything is a model, right? And so the pinhole camera model actually doesn't work really well on certain weird or unknown camera geometries. Maybe you don't know the camera parameters, or maybe the camera is something like you see here, a catadioptric camera, a high field of view like fisheye camera. It might be, like not super rectified like pinhole camera. So you have like some distortions maybe on the sides. Another common application in driving is you have a dash cam, which sits behind a windshield, and the windshield acts as a very weird lens. Imagine this, you can make it even more complex with rain on the windshield, or even like crazy applications like underwater robotics, where water acts as a very weird changing lens. And so the cool thing about that is that you can actually make this approach of view synthesis work, self-supervised learning work. Again, supervising by predicting ego motion and reprojection, where you are also learning the reprojection. And that was like inspired by work by Anna Angelova and co-authors, where they were predicting the pinhole camera model parameters. But actually, you can just take a general camera model inspired by Grossberg and Nayar and just full-on predict the per pixel projection operator. And this is what we've done in this work called neural ray surfaces. That we presented as a NORAD 3V last year. Code is also available online and pre-trained models, and you can try it out. A couple of Redditors have had fun using it with like crazy cameras, like action cameras for like biking and stuff like that. So you can have fun. So, okay, that's great. All that is self-supervised learning. You can extend it from multiple cameras, even when they have weird geometry. But in practice, you're never always just without any label at all. You always have some form of supervision. And we've been studying like just scaling up these approaches and like how do we go beyond self-supervised learning in a sense. And so some approaches, like obviously that's very well known, is semi-supervised learning, where you have some of your data that is labeled, maybe let's say with an active learning loop, or maybe part of the environment, you have like a 4-beam LiDAR and you get some 3D points in the environment very sparsely. Another one is auto-labeling via differentiable rendering, where here the geometry you're using is a bit more complex. It's the geometry, the physics of light, and you're using those predicting parameters and re-rendering. And then the last one is sim-to-real, where you're using supervised learning, but in simulation. And what you have to do in an unsupervised way is overcome the sim-to-real gap. And through our research, we found that there's a general insight connecting these different approaches, and namely that self-supervised learning is what enables you to make the most of what little supervision you have. So this is why self-supervised learning is not just scientifically interesting for us, but also practically relevant. So I'm going to go a little bit more into details about how self-supervised learning is actually key for the scalability of those 3 types of approaches: semi-supervised, auto-labeling, and sim-to-real. So for semi-supervised learning, there's a traditional training setup, and we had a paper at Coral where we're looking at like combining some 3D supervision for some points. Let's say if you have a 4-beam LiDAR, which is common for automotive, with just cameras. And that's great. You train still a monocular network. But one thing that's interesting is what if you also have partial point clouds available for inference sometimes? After all, if you assume you have a 4-beam LiDAR and you're training data, why don't you use it if you have it, at test time, at inference time? And so here, that's one of the work we're presenting at CVPR this year, which is called Sparse Auxiliary Network for Unified Monocular Depth Prediction and Completion. And here we show that the same model, again, the same network weights, can be used to leverage partial point clouds, both at training time and at inference time, whether they're always present or only sometimes. And that's something we call dial-level perception, where you can turn on and off the LiDAR sensor, for instance, and the model is always able to predict what you want, which is the depth of the scene. And the way it works is you have the standard decoder depth network like PACnet or MonoDepth2. But in addition, we have sometimes a sparse point cloud as input. And then we're using sparse convolutions and learning a representation that we are then learning to inject into the skip connections of the encoder-decoder depth network. And these adapter weights to do this injection in the skip connections are able to learn to inject it when we have it, and then otherwise you just use the skip connections as normal. So these are some example results, and what you're going to see here is sometimes you're going to see some kind of color-coded height map flare up with some sparse points like right now, and this corresponds to when we turn on a sparse LiDAR and off. And this is literally like when we add an input to the network or turn it off. And if you can see, the network is still able to predict when it's off, and when it's on, it's able to predict quite accurately, matching the actual point clouds in the world that are sensed directly. In the case of auto-labeling, which is the second of the self-supervised plus approaches that I mentioned, once again, self-supervised learning is key for what's called analysis by synthesis, or also the approach called inverse graphics in general. And so in a nutshell, the idea of our recent CVPR and ECCV papers that are described here, they consist in feeding an image to a deep network that then outputs, some scene level parameters that can then be used as an input to a renderer. And that renderer can then take those scene descriptions and then re-render the input image that was fed into the network. And that way you have reconstructed the image. And if you are correct, again, assuming you have no bug in your renderer, then it's because your network that deconstructed the image into the scene parameters was wrong. The network works. And if the renderer is actually differentiable, you can backpropagate through, again, that photometric error, this pixel comparison, to optimize the weight of the network that is deconstructing the image. And so here is an example of the network in action. And again, these scene parameters, they correspond to object placements, they correspond to object shapes in 3D. And here you're seeing the optimization loop through the differentiable renderer of the cars and their shapes and the translation, rotation, and everything. This work, the CVPR oral that we presented last year, used LiDAR to add not just a 2D rendering loss, but also a 3D, more structured rendering loss using LiDAR and partial matching of the point clouds. But in our follow-up ECCV work, we had extended this to rely only on monocular depth and replacing basically the LiDAR by pre-trained detectors at training time to really go full vision. Beyond depth estimation and object detection, our research also covers other tasks that are crucial for autonomous driving and robotics, including learning them together and a multitask learning framework, which is very common for computational reasons, because you're constrained, so you have to plug multiple networks, like combine multiple networks together. And so an example is our work on panoptic segmentation, which combines instance and semantic segmentation in a unified model. And last year, we presented at CVPR a novel method that was both 4 times faster and slightly more accurate than the state of the art. And this year, we are presenting a new panoptic model that learns pixel-level embeddings to simultaneously represent instances and categories, both of objects and regions. So which means that you get every pixel can have like a latent vector, a vector, and the average of those vectors inside an instance represents the instance well, but it's also pretty close to other instances of the same category and far from other instances of other categories. And that's for objects, but we can also represent ground or building or sky with those embeddings too. More details in our paper that we're presenting this week at CVPR called Hierarchical Lovash Embeddings for Proposal-Free Panoptic Segmentation. One problem with that so far is I actually, if you haven't noticed, I drifted into supervised learning land, which is where does these labels come from? Because obviously semantics are defined by humans, so they cannot be purely self-supervised. Right, my face could be called a schmirg. We just collectively decide as human beings to call this thing a face. So here, this is basically this little parenthesis, detour through supervised learning is to bring me to SIM. Because instead of manual labeling, which we don't think scales, we're thinking a promising avenue to get scalable semantic supervision is simulation. But of course, there's no free lunch, so it comes at a cost, which is the domain gap that might hurt generalization performance. So overcoming this gap is called solving the sim-to-real transfer problem, which is a specific instance of what's more generally called unsupervised domain adaptation. And so very recently also, we put on arXiv a paper called Geometric Unsupervised Domain Adaptation for Semantic Segmentation, GUDA for short. And it works by multitask mixed batch training. So it combines synthetic supervision with real-world geometric self-supervision, the photometric loss that I talked about before, to learn a domain invariant network that predicts both semantics and depth. So as input, sim and real world. As output, you're getting semantics and depth. And you can only pay a supervised loss on semantics when you have sim samples. But on the real world, you can pay the self-supervised loss, which you also can pay in sim. And so we're basically having this combined multitask objective with mixed batch training to learn these joint features that work across the domain gap. And we show that combining semantic objectives in sim. So again, it's semantic. You're saying this is a face, this is a shirt, etc. With geometric ones that say warp this, reconstruct this image, because geometry tells me if you're right about your depth estimate. This is how geometry tells you how it should look like, the reconstructed image. So by combining these two, we can reduce the domain gap. And then performance, what we found is in this paper is that we find that performance, this is the graph you see on the upper right, performance improves linearly so far up to like 42,000 samples that we've been using with both synthetic data quality and quantity. And so one of the things that's interesting is that we've been using state-of-the-art synthetic data from a company called Parallel Domain to try to really push the limits of see how far we are from just replacing supervision for semantics by synthetic supervision. And I think in our experiments, we saw that roughly 6 or 10 times more synthetic data should be able to cover the gap if the trend follows. And of course, the trend is going to plateau at some point, but so far it's just linearly showing that it's improving. So to conclude, I've talked to you about first the self-supervised part, like purely self-supervised, where we are using geometry as supervision on videos, and again, direct supervision to solve the task. And then I talked about, like, in a more practical setting, you care about using whatever you have at your disposal, like self-driving and robots is just so hard that you cannot ignore things you have at your disposal. Even though they might be tricky to combine together. And so that's why there's some interesting research problems there to do scalable supervised learning or self-supervised plus. And what I've shown you is that actually self-supervised learning is the key to really unlock this like advantage of the extra little things you have. In the case of semi-supervision can be essentially phrased as self-supervised plus sparsely supervised. Auto-labeling of the differentiable rendering, it's basically you're injecting prior knowledge about objects and you're combining it with a differentiable renderer. In the sim-to-real transfer case, it's literally synthetically supervised plus real-world self-supervised. It's a bit like Neo learning Kung Fu with Morpheus inside the simulation, and then fighting it out and becoming better in the real world, where we know it's actually the Matrix. So it's another simulation. So that analogy doesn't really work very well. But anyway, there is a really nice saying from Alyosha Eifros, which is the AI revolution will not be supervised. And I definitely believe in that. And also known as driving is more fun than CAPTCHA. So you don't want to be clicking on pixels as human beings for the rest of our lives just to supervise machines. So yeah, we do a lot more work. This is just a slide with a lot of the research we do, and a big thank you to a lot of the collaborators. It takes a village to work on autonomous driving. And here's our presence at CVPR. Lots of people in my team, myself included, would be here. We released a lot of code and data. And yeah, just feel free to reach out and come to our workshop on Friday. Thank you.
Thanks a lot for this amazing talk. And we actually had a few questions in. The first one is, but yeah, if there are more, please write them in the channel. So the first one is on the kind of depth estimation. Would it be possible to use a stereo camera in a car with the same monocular model and increase the robustness?
Yes, you can. So actually, FSM kind of works in this way. But it actually does not assume frontal parallel, time synchronized, small baseline stereo. So actually what we show in the paper, we have an experiment on KT, which is the standard stereo setup. And we show that we can match the original Goddard et al., like left-right consistency. Like that was really the first paper on self-supervised learning of depth, but using stereo. And we show that we can match or even outperform along certain metrics like RMSE. For instance, we have less outliers when we do the general full surround mono depth without assuming precise calibration of a small baseline stereo. So yes, that FSM approach extends definitely in this case.
And yeah, the other one is actually on somehow more future work question, I would say. Can you actually do 3D detection and tracking on the FSM point cloud? And if you would do so, how well would this work?
Yes, so that's actually work that we have, we're currently working on, and we'll put on archive real soon. So yes, you can actually do that. The problem is that there's some sources of errors. So there's basically two paradigms for 3D detection from images. One is called pseudo LiDAR, where you're saying, hey, use monodepth as like this super awesome point clouds that I've shown you. They're almost as good as LiDAR, right? You could just use them as a replacement and use your favorite LiDAR-based 3D detector, like point killers would be mine, for instance, right? Except it doesn't work. I mean, it works kind of, but it doesn't really work. And the reason is because there is some noise in the output of your network, like some bleeding around edges of objects or things like that. And that noise can hurt you quite a lot. There's a cool set of work from Kilian Weinberger's lab and also Chris Kitani's lab, where they're trying to recover from that. But the problem is that they typically have a big overfitting issue. Like you typically like train the depth network, then you try it on your training data, and then you're learning on your training data to kind of overfit to this weird pattern or ignore the weird noises. But at test time, it doesn't generalize really well. PatchNet would be kind of the state-of-the-art approach, I think, for that. But very recently, we've been able, like in a paper that's coming soon, it's called Is Pseudo LiDAR Needed for 3D Detection, where we find that we can actually use the same benefits of pseudo LiDAR, namely pre-training at scale on depth, very unsupervised pre-training on depth. But we're just using that as a pre-training for an end-to-end network. And then we're just pre-training the network and then just paying a loss for 3D detection directly, not through the intermediate point cloud representation. And we find that we can substantially improve the state of the art using that. And it's still not at the level of LiDAR. Like if you look at KT, but KT is kind of a weird benchmark because KT is very small. So if you look at KT, state of the art for LiDAR 3D detection is 92%, something like that. For vision, it's around 13% before we push our paper, which is going to be a bit better than that. But on the test set, right? Because on the val set, lots of people publish only on the val set, ignore val numbers. There's overfitting, there's experimental protocol issues. I think there's a great paper by Peter Conchiter's group at Mapillary called Demystifying Pseudo LiDAR, and actually where they show there is such an issue of overfitting. So validation number is really good, test numbers drop a lot with pseudo LiDAR.
Yeah. So don't go via pseudo LiDAR, try to somehow get the benefit from self-supervised training, but then do direct object.
Yeah, I was a big believer in pseudo LiDAR as an intermediate representation, especially for the Colton paper also, like, is computer vision needed for action? This intermediate representation modularity is a really good thing in robotics. But in this case, so far, it seems that actually end-to-end works better.
Yeah, with kind of good self-supervised pre-training, and then do with the little data you have, get the best out of it.
Yep, exactly.
Okay, yeah. Yeah, thanks a lot for the talk and the interesting question, and a bit of some spoilers for a new paper, which sounds very interesting. Yeah, it was a pleasure to have you here, and yeah.
Thank you. I'll see you around.
Yeah, bye. Okay, so I can see Andre. Is the screen sharing working?
I hope so. Let's try. I'm embarrassed to say that I barely use Zoom. I know this is shocking.
Yes.
Let's see.
Okay. Yeah. Seems still to work, even with limited experience. Okay, so it's a pleasure to introduce Andre. I have to say, I think he doesn't really need a lot of introduction. But yeah, he is the senior director of AI at Tesla, and he basically supervises and leads the team responsible for all the neural networks in the autopilot. With this, it's a pleasure to have you here, and I'm really looking forward to your talk.
Yeah, great. Thank you for the introduction. And I'm very happy that I was able to display some impressive zero-shot learning on Zoom. Okay. Yeah, so I'm very excited to be here. Thank you for the introduction. I would like to talk a bit more about what Tesla has been up to over the last few months. So first to start, I guess we are here at the CVPR workshop on autonomous driving. So I think I'm preaching to the choir a little bit, but I'd like to start with some slides on like why we're doing all of this. And I think, unfortunately, we're kind of like in a bad shape when it comes to transportation in society. And basically the issue is that we have these metallic objects traveling incredibly quickly and with very high kinetic energy. And we are putting meat in the control loop into the system. And so this is quite undesirable. And really fundamentally what it comes down to is people are not very good at driving. They get into a lot of trouble and accidents. They don't want to drive. And also in terms of economics, we are involving people in transportation. And of course, we'd like to automate transportation and really reap the benefits of that automation in society. So we all, I think, are on the same page that it should be possible to replace the meat computer with a silicon computer and get a lot of benefits out of it in terms of safety and convenience and economics. So in particular, silicon computers have significantly lower latencies. They have 360-degree situational awareness. They are fully attentive and never check their Instagram, and alleviate all of the issues that I presented. And so I think this is not super shocking, and a lot of people have been kind of really looking forward to this kind of a feature. This is a frame from iRobot, a really good movie if you haven't seen it. And here, Will Smith is about to drive a car manually. And this other person here is shocked that this is going to happen. This is ridiculous. Like, why would you actually have a human driving cars? And so I think this is not very far from truth. And this movie is taking place in 2035. So I think by then, I actually think this is a pretty prescient prediction. So what I think is kind of unique about Tesla and in our approach to autonomy is that we take a very incremental approach towards this problem. So in particular, we already have customers with the Autopilot package, and we have millions of cars, and the Autopilot software is always running and providing active safety features, and of course, the Autopilot functionality. So we provide additional safety and convenience to our customers today, and also the team is working on full self-driving ability. So I would briefly like to very quickly speak to the value today that we provide, just to give you some examples of what the team is up to and what we're sort of doing today. So here's an automatic emergency braking scenario. So the driver here is proceeding through an intersection, and you can see trouble coming here. So the person kind of crept up from here, and the car sees the pedestrian, object detection kicks in, and we slam on the brakes and we avert collision. Here's an example of a traffic control warning. So this person is probably not paying attention, potentially on the phone, is not braking for the traffic lights ahead, but we see that these are relevant traffic lights. They are red, and we beep, and the person immediately starts slowing and probably does not actually enter the intersection. These are examples from pedal misapplication mitigation, PMM. Here, a person is unparking from their driving spot, and they are trying to turn, and then they mess up, and they accidentally floor it. So they floor it right there, and the system kicks in. It sees pedestrians ahead of us, and it slams on the brakes and averts what would be a very gnarly situation in this case. Here's another last scenario I can show briefly. So this person is trying to park, and they turn to the right here, and they intend to press the brake, but they actually floor it. And the system again sees that there's no driving path forward and actually slams on the brakes and averts. In this case, this person is not going to be swimming in this river imminently. So these are some examples of the value that we are providing today in this incremental autonomy fashion. But of course, the team is actually sorry about that. The team is working primarily on the FSD functionality, which is our full self-driving suite. So here we have we have the FSD beta product, and it's in the hands of about 2,000 customers. And this is an example from one of the customers driving around San Francisco. And these people are posting videos on YouTube, so you can check out a lot of videos. But what we're showing here on the instrument cluster is we're showing all of our predictions. So you're seeing some road edges, some lines, some objects, and the car, of course, is navigating around autonomously here in San Francisco environment. Now, we, of course, drive this extensively as engineers. So it's actually fairly routine for us to have zero intervention drives, I would say, in like sparsely populated areas like Palo Alto and so on. I would say we definitely struggle a lot more in very adversarial environments like San Francisco. A lot of people working in autonomy, of course, know all about that as well. So this drive ends up being a fairly long drive, and it's zero interventions in this case. Now, one thing I like to point out always whenever I show the video of Tesla driving around autonomously in these city environments is you've seen this before, and you've seen it for a decade or more. So here's a Waymo taking a left at an intersection. And this is actually a pretty old video, I believe. And so you've been seeing stuff like this for a very long time. So what is the big deal? Why is this impressive? And so on. And I think the important thing to realize, and that I like to always stress, is that even though these two scenarios look the same, so there's a car taking a left at an intersection, under the hood, and in terms of the scalability of the system, things are incredibly different. So in particular, a lot of the competing approaches in the industry take this LiDAR plus HD map approach. And so the idea is that you take an expensive sensor, a LiDAR, on the top of the car, and it basically gives you range finding around the vehicle in 360 and gives you a point cloud. And what you have to do is you have to pre-map the environment with the LiDAR sensor, and you have to create a high definition map. And then you have to insert all of the lanes and how they connect and all the traffic lights and where they are. And you basically have to create a high definition map. And then at test time, you are simply localizing to that map to drive around. And so the approach we take is vision-based primarily. So everything that happens for the first time there in the car based on the videos from the 8 cameras that surround the car. And so we come to an intersection for the very first time, and we have to figure out where are the lanes, how do they connect, where are the traffic lights, which ones are relevant, what traffic lights control what lanes. Everything is happening at that time on that car, and we don't have too much high definition sort of information at all. And this is actually a significantly more scalable approach, because if our product is on a scale of millions of customers on Earth, and so it's actually quite unscalable to actually collect, build, and maintain these high definition LiDAR maps. It would be incredibly expensive to keep this infrastructure up to date. And so we take the vision-based approach, which of course is much more difficult because you actually have to get neural networks that function incredibly well based on the videos. But once you actually get that to work, it's a general vision system and can in principle be deployed anywhere on Earth. So that's really the problem that we are solving. Now, in terms of the cartoon diagram of a typical sensing suite of an autonomous vehicle, these are kind of like the typical sensors you would see. And as I mentioned, we do not use high definition maps and we do not use LiDAR. We only use video cameras. And in fact, the vision system that we have been building over the last few years has been getting so incredibly good that it's kind of leaving a lot of the other sensors in the dust. And so actually, the cameras are doing most of the heavy lifting in terms of the perception that you've seen in the car. And actually, it's gotten to the point that we are able to start removing some of the other sensors because they are just becoming these crutches that you start to not really need at all. So actually 3 weeks ago, we started to ship cars that have no radar at all. So we've deleted the radar, and we are driving on vision alone in these cars. And the reason we are doing this, I think, is well expressed by Elon in his tweet. He's saying, when radar and vision disagree, which one do you believe? Vision has much more precision, so better to double down on vision than do sensor fusion. And what he's referring to is basically like vision is getting to the point where the sensor is like 100x better than, say, radar. Then if you have a sensor that is dominating the other sensor and is so much better, then the other sensor is actually starting to like really contribute, it's actually holding you back, and it's really starting to contribute noise to the former system. And so we are really doubling down on the vision-only approach. And actually in this talk, what I would like to primarily talk about is how we have achieved vision-only control without radar, and how we have released this quite successfully so far to the fleet, and what it has sort of taken for us to do that. So here I wanted to show a video, basically showing what the input to the system is. So we have 8 cameras surround, and these are fairly high definition cameras, and we have 36 frames a second. And you can see that basically you can actually understand a lot about this environment from this input. It's extremely information rich. You're getting a huge amount of constraints, 8 million bits roughly of constraints per second on the state of the surroundings. And so it's incredibly information rich compared to any other sensor you may want to have in a car. And so this is the one that we're doubling down on, because this is ultimately where all the difficult sort of scene interpretation challenges lie. So we prefer to just focus all of our infrastructure and development on this. And we're not wasting people working on the radar stack and the sensor fusion stack. We only have one team, the vision team. Now, typically when we talk about vision, the reason people are squeamish about using vision is, and the sort of challenge that almost always is pointed out, is people are not certain if neural networks are able to do range finding or depth estimation of these objects. So obviously humans drive around with vision. So obviously our neural net is able to process visual input to understand the depth and velocity of all the objects around us. But the big question is, can our synthetic neural networks also do the same? And I think the answer to us internally over the last few months that we've worked on this is an unequivocal yes. And I'd like to sort of talk about that. So in particular, the radar API, or like what the radar really gives you, is it gives you a quite accurate depth and velocity measurement. It's a pretty direct measurement of the car ahead of you in very nominal situations. So here I'm showing a random image on the left, and you are seeing the depth, velocity, and acceleration reported by the radar stack for this car. And you can see that it's a bit wiggly on the velocity, so this is some kind of a stop and go scenario. Now, when radar has a good lock on the car in front of you, it's given incredibly good depth and velocity. But the problem with radar is, like, once in a while, at random, it will give you a dumb measurement, and you will not know when that is. And so it's incredibly hard to fuse with vision in our experience. So it might suddenly see a spurious stationary object because of a manhole or because of a bridge, or crossing objects are not very well tracked, or oncoming objects are not very well tracked. And it ends up contributing noise. I'll go into more detail in a bit. But for our purposes, what we want to do right now is we want to match the quality of these predictions using vision alone. So the question is, how can you get a neural net to predict depth, velocity, acceleration directly and do it with a very high fidelity, matching that of radar? So the approach we're going to take, of course, is we're going to treat this as a supervised learning problem, and we need a massive data set of depth, velocity, acceleration on a lot of cars, and we're going to train a large enough neural network and do a very good job at that. That's the standard vanilla approach, and that actually works really well if you do it properly. So here's what it took. So the first component that you need is an incredibly good data set. So, and when I talk about a good data set, I believe it has to have 3 properties that are critical. It has to be large in millions of examples. It needs to be clean. So in this case, we have to have a very clean source of depth, velocity, and acceleration for all these cars. And it must be diverse. So we're not just talking about a single, driving clip of going forward on a highway. We really have to get into the edge cases and mine all the difficult scenarios. And I'm going to show you some examples. And when you have a large, clean, diverse data set, and you train a large enough neural network on it, what I've seen in practice is, in the words of Ilya Sutskever, success is guaranteed. And so let me show you some examples of that. So first of all, how are we going to achieve this data set? So of course, we need to collect training data. The typical approach might be to use humans to annotate cars around us in 3 dimensions. What we found actually works really well is an auto-labeling approach. So it's not pure humans, just like annotating cars. It's an offline tracker, as we call it. And it's an auto-labeling process for collecting data at the scale that is necessary. So we need, again, millions of hard examples. So this is where the scale comes from, is that it's not labeled purely by humans, although humans are involved. It's labeled automatically. So here's an example of some automatic labels we were able to derive for cars on the highway. And the way you do this is, because you are offline and you are trying to just annotate a clip, you have a large number of benefits that you don't typically have if you're at test time under strict latency requirements in the car. So you can take your time to fully figure out exactly all the objects and where they are. You can use neural networks that are extremely heavy, that are not deployable for various reasons. You can use benefit of hindsight because you know the future, not just the past. You can use all kinds of expensive offline optimization and tracking techniques. You can use extra sensors. In this case, for example, actually radar was one of the sensors that we used for the auto labeling. But there's actually a massive difference between using radar at test time and using it in the offline tracker. And that is that at test time, a radar can just report a stationary track immediately in front of you, and you have 20 milliseconds to decide if you're going to brake or not. If you're offline, you have the benefit of hindsight. And so you can do a much better job of calmly fusing if you really want to. And so there is a massive difference there. And in addition, you can, of course, involve humans, and they can do cleaning, verification, editing, and so on. And so we basically found that this was a massive lever to allow us to reach the scale and the labeling quality. And then to get the diversity, that was also a massive fight. So here's some examples of really tricky scenarios. So here, there's some, I don't actually know exactly what this is, but basically this car drops a bunch of debris on us, and we maintain a consistent track for the label. And of course, if you have millions of labels like this, the neural net, if it's a powerful enough neural net, will actually end up learning to persist these tracks in these kinds of scenarios. Here's another example. There's a car in front of us, and I actually am not 100% sure what happens in this case, but as you'll see, there's some kind of a dust cloud that develops here and briefly occludes the car. But in the auto labeling tool, we are able to persist this track because we saw it before and we saw it after, so we can actually stitch it up and use it as a training set for the neural net. Here's one more example of an adversarial scenario from heavy snow. Again, we can auto-label this fine and create a large collection of examples. Now, as we were working on this over a duration of, I want to say, of roughly 4 months of really just focusing a lot of the team on this problem of achieving really good depth, velocity, and acceleration, we've ended up developing 221 triggers manually that we were using to source data from our customer fleet. And this is just an example, some examples of the 221 triggers that were used to collect all of these diverse scenarios. So for example, we have shadow mode, where we deploy a neural network that is pretty good at predicting depth and velocity. And what we do is we run it silently in the cars of our customers, but it's not actually connected to control. What's driving is the legacy stack. But we're basically running the new measurements of depth and velocity, and we're, for example, looking at whether or not they agree or disagree with the legacy stack or with the radar. We're looking for other sources of jank, like for example, if there's bounding box jitter, detection jitter, the main and the narrow camera disagree. We predict that there's a harshly decelerating object, but the person seems to not mind. All kinds of disagreements between different neural network signals. And there's a long list here. It took us a while to actually perfect these triggers, and all of them are iteration, and you're looking at what's coming back, you're tuning your trigger, and you're sourcing data from all these scenarios. So basically over the last 4 months, we've done quite extensive data engine. We've ended up doing 7 shadow modes and 7 loops around this data engine here, where on the top right is where you begin. You have some seed data set. You train your neural network on your data set, and you deploy the neural network in the customer cars in shadow mode. And the network is silently making predictions. And then you have to have some mechanisms for sourcing inaccuracies of the neural net. So you're just looking at its predictions. And then you're using one of these triggers, like I described. You're getting these scenarios where the network is probably misbehaving. Some of those clips end up going to unit tests to make sure that we, even if we're failing right now, we make sure we pass later. And in addition, those examples are being auto-labeled and incorporated into a training set. And then as a asynchronous process, we're also always data cleaning the current training set. And so we spin this loop over and over again until the network basically becomes incredibly good. So in total, we've done 7 rounds of shadow mode for this release. We've accumulated 1 million extremely hard, diverse clips. And these are videos. So these are, you should roughly think about, say, 10-second clips, 36 FPS, something like that. In total, we have about 6 billion objects labeled cleanly for depth and velocity. And this takes up roughly 1.5 petabytes of storage. So that gives us a really good data set. Of course, that by itself does not suffice. So we have an incredibly good AI team that is designing the neural network architecture that is basically the layout of the synthetic visual cortex in order to efficiently process this information. So our architecture roughly looks like this. We have these images coming from multiple cameras on the top. All of them are processed by an image extractor, like a backbone, like think ResNet kind of style. Then there's a multicam fusion that fuses the information from all the 8 views. And this is a kind of a transformer that we use to fuse this information. And then we fuse information first across all the cameras and then across all of time. And that is also done either by a transformer, by a recurrent neural network, or just by 3-dimensional convolutions. We've experimented with a lot of kind of fusion strategies here to get this to work really well. And then what we have afterwards, after the fusion is done, is we have this branching structure that doesn't just consist of heads, but actually we've expanded this over the last year or so, where you now have heads that branch into trunks that branch into terminals. So there's a lot of branching structure. And the reason you want this branching structure is because there's a huge amount of outputs that you're interested in, and you can't afford to have a single neural network for every one of the individual outputs. You have to, of course, amortize the forward pass for efficient inference at this time. And so there's a lot of feature sharing here. The other nice benefit of the branching structure is that it decouples at the terminals, it decouples all these signals. So if I'm someone working on velocity for a particular object type or something like that, I have a small piece of neural network that I can actually fine tune without touching any of the other signals. And so I can work in isolation to some extent and actually get something to work pretty well. And then once in a while, so basically the iteration scheme is that a lot of people are fine tuning, and once in a while we do an uprev of all of the backbone end to end. And so it's a very interesting sort of mechanism because we have a team of roughly 20 people who are, I would say, training neural networks full time, and they're all cooperating on the single neural net. And so what is the workflow by which you do that is pretty fascinating and continues to be a challenge to actually design efficiently. So we have a neural network architecture, we have a data set. Now training these neural networks, like I mentioned, this is a 1.5 petabyte data set, requires a huge amount of compute. So I wanted to briefly give a plug to this insane supercomputer that we are building and using now. For us, computer vision is the bread and butter of what we do and what enables the autopilot. And for that to work really well, you need a massive data set. We get that from the fleet, but you also need to train massive neural nets and experiment a lot. So we've invested a lot into the compute. In this case, we have here a data set. We have a cluster that we're just building that is 720 nodes of 8x A100s of the 80 gigabyte version. So this is a massive supercomputer. I actually believe that in terms of flops, this is roughly number 5 supercomputer in the world. So this is actually a fairly significant computer here. We have 10 petabytes of hot tier NVMe storage, and it's also an incredibly fast storage. So I believe 1.6 terabytes per second. This is one of the world's fastest file systems. And we have also a very efficient fabric that connects all of this. Because of course, if you're doing distributed training across your nodes, you need your gradients to be synchronized very efficiently. And of course, we are reading all of these videos from the file system, and that requires a really fat pipe as well. So this is a pretty incredible supercomputer. So this is a GPU cluster. Next up, we're really hoping that we're currently working on Project Dojo, which will take this to next level, but I'm not ready to sort of reveal any more details about that at this point. What I would like to do is I would like to just briefly plug the supercomputing team. They've been growing a lot. And so if high performance computing for this application and for training these crazy neural networks excites you, then we would definitely appreciate more help. So please contact the supercomputing team at supercomputing at Tesla to help us build these clusters. On the left here, we have the compute nodes, and on the right, this is a network switch, actually. So the wires here is kind of like the white matter of this synthetic cortex, I guess. The other thing I wanted to briefly talk about is I wanted to also mention briefly that this effort basically is incredibly vertically integrated in the AI team. So as I showed you, we own the vehicle and the sensing, and we source our own data, and we annotate our own data, and we train in our on-prem cluster. And then we deploy all of the neural networks that we train on our in-house developed chip. So we have the FSD computer here that has 2 SoCs, FSD chips here, and they have our own custom NPU neural processing unit here at roughly 36 TOPS each. And so these chips are specifically designed for the neural networks that we want to run for FSD applications. And so everything is very vertically integrated in the team. And I think that's pretty incredible because you get to really co-design and engineer at all the layers of that stack. And there's no third party that is holding you back. You're fully in charge of your own destiny, which I think is incredibly unique and very exciting. And then we have a deployment pipeline here where we take these neural networks We do a lot of typical graph optimization, fusion, quantization, threshold calibration, and so on, and deploy it on our chip. And this is in the customer's cars, and these neural networks run there. So now what I'd like to show is, I first would like to show some qualitative examples of some of our results in terms of the depth and velocity predictions that we were able to achieve by putting all of these pieces together and training these networks at scale. So the first example here, I have a video where this is on track testing. So this is an engineering car, and we asked it to slam on the brakes as hard as it possibly can. So this is a very harsh braking here in front of us. Even though it doesn't look like that in the video, this is very harsh braking. So what you can see on the right here is you can see the outputs from the legacy stack, which had radar vision fusion, and from the new stack, which is vision alone in blue. So in the orange legacy stack, you can actually see these track drops here when the car was braking really harshly. And basically the issue is that the braking was so harsh that the radar stack that we have actually ended up not associating the car and dropping the track and then reinitializing it all the time. And so it's as if the vehicle disappeared and reappeared like 6 times during the period of this braking. And so this created a bunch of artifacts here, but we see that the new stack in blue is actually not subject to this behavior at all. It just gives a clean signal. In fact, here, there's no smoothing, I believe, on the blue signal here. This is the raw depth and velocity that comes out from the neural net, the final neural net that we released with about 3 weeks ago. And you can see that it's fairly smooth here. And of course, you could go into the radar stack and you could adjust the hyperparameters of the tracker, like why is it dropping tracks and so on. But then you are spending engineering efforts and focus on a stack that is like not really barking up the right tree. And so it's better to, again, just focus on the vision and make it work really well. And we see that it is much more robust when you train it at scale than something like this. Here's another example, fairly infamous example of slowdowns when there are cars going below a bridge. The issue here, again, is that the radar does not have too much vertical resolution. So radar reports a stationary object in front of you. It's as if like the radar doesn't know that there's like a stationary car in front of you or if it's the bridge above. It cannot differentiate those two. So radar thinks that there might be something stationary in front, and it's just like looking for something in vision to tell it that it might be correct. And then we create a stationary target and brake. And so in this case, in the legacy vision predictions, which were already producing depth and velocity, but because we were using radar, the vision inaccuracies were being masked because your bar is only at radar association. Your bar is not at actual driving. And so the depth and velocity were not held up to a high enough bar. And so basically what happens is vision reports for a few frames, reports a slightly too negative velocity for the car. And then it associates to the stationary object. And the stack is like, oh, that must be the stationary thing. And then we brake. And so this, of course, is much cleaner. And you see that the new stack does not see this at all. And there's no slowdowns in this case. Because we just get the correct depth and velocity, and vision obviously has the vertical resolution to differentiate a bridge from a car and whether or not the car is slowing or not. So again, you could go into the radar stack or the sensor fusion stack, and if you have an improved depth and velocity, you could change the fusion strategy. But again, you're just kind of like doing dead work. Like this signal is so good by itself. Why would you do that? So in this setting now, we've improved the situation quite a lot. Here's another last example. We have a stationary approach. Again, this is in track testing environment. This is an example of a test that we would run. And we are just approaching this vehicle and hoping to stop. What you see in orange in the legacy stack is that it actually takes us quite a bit of time for us to start slowing. And basically what's happening here is that the radar is very trigger happy and it sees all these false stationary objects everywhere. Like everything that like sticks out is a stationary target. And radar by itself doesn't know what actually is a stationary car and what isn't. So it's waiting for vision to associate with it. And vision, if it's not held up to a high enough bar, is noisy and contributes sort of error. And the sensor fusion stack just kind of like picks it up too late. And so again, you could fix all that, even though it's a very gross system with a lot of if statements and so on, because the sensor fusion is complicated because the error modes for vision and radar are quite different. But here, when we just work with vision alone and we take out the radar, vision recognizes this object very early, gives the correct depth and velocity, and there's no issues. So we actually get an initial slowdown much earlier. And we've really like simplified the stack a lot and as well. So just speaking very briefly to the release and validation, we've extensively validated this before we, of course, ship this to customers. Just some example numbers for the validation itself. We've handpicked about 6,000 clips in about 70 categories of scenarios, like harsh braking, crossing vehicles, different vehicle types, environments, and so on. And we run these tests on all the commits of the build, and we run them also every day periodically as we were trying to drive up the performance on these clips. We also use simulation extensively for validation. We've also used simulation for training, although I haven't gone into that, but we've had some successes there. But we use it primarily for validation at this stage. And that's, again, like diversity of scenarios, trying to make sure that the stack is performing correctly. We've done a lot of track testing, and I've shown you some examples of that. We've driven this extensively in the QA fleet, and we've also deployed this in shadow modes and seen that this stack performs fairly well. So in particular, for example, for the automatic emergency braking, we actually see a higher precision and recall compared to the legacy stack that is a fusion stack. And so having seen all this, we've actually released this. We've accumulated about 15 million miles so far. And 1.7 million of those have been on autopilot. And so far, there have been no crashes. Now, of course, we're running at massive scale here. And so we do expect some crashes at some point. The legacy stack has a crash roughly every 5 million miles or so, I believe. And so we do expect some incidents at some point. But the improvements for the vision stack are not sort of stopping. So I think we're very confident that we're barking up the right tree here, and that we can actually get this to work really incredibly well. I also wanted to briefly give a shout out to auto labeling as an incredibly powerful method for sourcing training data. So we're applying auto labeling to all of the FSD tasks, not just to depth and velocity of the car in front of us. Here's an auto labeler for pedestrians. You can see that the tracks are very smooth. And this is, again, a completely offline process that we are applying not just to objects, but also to a lot of static environments. So this is some example of a 3D reconstruction. So here we see a clip, and this is a vision-only estimate of the depths of all the points. And of course, you don't actually want to really deploy these measurements directly into a car because they are too raw. So what you actually want to do is you want to, again, auto label, and you want to really think about what is the information I really need at test time in the car, and what is like as close as possible to action, right? So you want to do all this work at training time, figure out exactly what happened in the clip, reconstruct the entire environment, and then you want to actually like post-process the curb at training time. So you want to do as much at training time and labeling time as possible. And then you want to figure out what are the tasks I really need at test time. And that's the thing that happens in the car, subject to very strict latency requirements. You want to do as little post-processing there as possible. We see that this is a very powerful lever on creating data sets. So in summary, what I try to argue and give you a sense of is vision alone is actually is our finding that is perfectly capable of depth sensing. It is an incredibly rich sensor in terms of bandwidth of information. And doing this and matching radar performance in depth and velocity is incredibly hard. I believe it requires the fleet because the data set that we were able to achieve was critical in all these performance improvements. And if you do not have the fleet, I'm not 100% sure how you can source all the difficult and diverse scenarios that we did source, because I believe that was critical to getting this to work. So it's hard, it requires massive networks, a supercomputer, and a data engine, and the fleet. But all of these components are coming together in a vertically integrated fashion at Tesla AI. And I believe that this makes us sort of uniquely positioned in the industry, where we are barking up the right tree, and we have all the puzzle pieces to make this work. And so if you are excited about the approach that we're taking and the networks and the work that we're doing, then I would encourage you to please apply and join the team and help us make this a reality. So you can go to tesla.com/autopilotai. It's a very simple process. You upload a resume and you have a blurb about some of the things that you've done that are impressive. And then that comes directly to us. And we'd love to work with you to make this a reality. Thank you.
Thanks for this very, very interesting talk. We actually got quite some questions. Since we are already over time, I will limit it to a few. We are at the kind of nice point at the end of the workshop, so you are a bit of a rough spot that you have to answer more questions than maybe other speakers. And kind of, I would like to go as the first one into the, kind of the maybe a bit the auto labeling, but actually the thing which really is necessary for the auto labeling, and this is these, this definition of these triggers. Yep. Did you ever try to investigate if you can automatically generate those triggers?
That's an interesting question. So the triggers are kind of like, they're designed based on what we're seeing and what's coming back in the telemetry from the cars. So we are seeing clips where maybe we didn't brake, but the person did, or vice versa. There's all kinds of disagreements with like human driving and the legacy stack. And we're looking at this, and typically we try to have signals of various generality. So for example, like a vision radar disagreement is a very general trigger. It can source all the disagreements. And then there are very specific ones, like maybe we struggled actually for a while when we were entering tunnels and exiting tunnels because there was a lot of brightness variation. So we struggled a lot there as an example. And we had to specifically design some triggers for that because we were not catching it with a high enough frequency. Because for any of these situations, you actually need to make sure they're represented well in the training set. So for us, this was a fairly manual process, but we do have a team basically dedicated to doing this full time, and they did this for 4 months. So I don't, like, how do you automate this? I think is a very tricky scenario because, again, you can have these general triggers, but I think they will not correctly represent the error modes. And I think it would be really hard to, for example, automatically somehow have a trigger that triggers for entering and exiting tunnels. That's something semantic that you as a person have to like intuit that this is a challenge for whatever reason and actually go after it specifically. So yeah, it's not clear how that would work, but I think it's a really interesting idea.
Yeah, so, I thought it sounded very interesting. The question sounded very interesting and not easy to answer.
Yeah.
Maybe another one which actually in somehow, let's say, 2 version showed up a bit was kind of in your vision only approach. Kind of, could there be other sensor like, for example, thermal image, kind of thermal cameras, which could help you in low light situation, or actually even the radar, which could kind of give you some very specific information. I think there was an example of radar signals bouncing through basically the car before you, and then you still get somehow a signal of the car, one ahead, things like that. Do you think really vision is enough, or kind of, maybe some special sensors which could give you a certain edge?
Yeah, I think it's an interesting idea. I would say, like clearly people use vision and the visual spectrum, and they make it work. And so there's an infinity sensors of varying economic costs. Actually, vision and in the visible light spectrum is incredibly cheap sensor, right? So the economics of this are very appealing, and you can actually manufacture and include this at scale. So it's a very cheap and nice sensor. And I would say that basically we have proof from humans that it is sufficient. And I would say also that vision has all the information for driving. So I would say that basically vision is necessary and sufficient in my mind. And so we're primarily focusing on that. And you could go crazy with a lot of sensors, but I think we're definitely currently just like doubling down on that alone.
Yeah, thanks a lot. I think we are now already more than 5 minutes overtime. So I let you go and don't ask other evil LiDAR versus camera questions. With this, I would actually like to give some kind of concluding remarks on the workshop, or better, move over to the last part. So before, yeah, I would really like to thank the whole team. Without them, this would have never been possible. You see how many people it takes to organize such a workshop, to get all the people here, to get all the amazing, speakers invited, convince them that they should show up, but also to, organize a paper track, review all the papers. So yeah, I'm extremely grateful for all these people, and that they gave me the opportunity to host the workshop. And with this, basically, it's a pleasure to end the main part of the workshop. If you are interested, we have still the Gatherly town, where you can go and see if there is anyone interesting around, have a chat, maybe, discuss about what is the, maybe we should go with LiDAR. So yeah, it was a pleasure to host this event, and I'm looking forward to see you all in the next years, hopefully again at our workshop.